a space deformation that would preserve, you know, the metric of the surface. And while the results that you see on screen kind of look plausible, in fact, actually, they're not developable at all. I really failed in my attempt back then, and I left this topic for a while. And what I did instead in the end in my PhD is working on more general deformations of general surfaces, so not only developable ones. And I've developed some approaches for variational surface deformation. So, you know, in general surface editing, what we typically have is our shape that we place some constraints on. So in this case, the user constrains all the purple areas to be exactly where they're prescribed. And then the yellow part of the surface is optimized to minimize some objective functional or loss functional, as we would say these days, I guess. And this energy function somehow describes what a good deformation is and tries to preserve local details and smoothness and things like that. So over the years, many different proposals for these deformation energies were happening. So a very famous shell energy from Terzopoulos is from the 80s. And in the 90s, Leif Kobelt and colleagues proposed the Laplacian energy. And also myself and colleagues of mine have worked on the subject and proposed some evolutions of this Laplacian energy. So they all try to basically mimic elasticity and create elastic looking shapes that whose deformations are detail preserving. And then when I was a postdoc in Berlin with Mark Alexa, we were still thinking about this deformation and isometry problem on meshes. And we came up with one particularly simple energy formulation for as rigid as possible or isometric as possible surface deformation. That somehow stuck, and this is what I would like to show you. So the energy functional looks a little bit uninviting. It has maybe too many letters in it, but the idea is actually very, very simple. So if we have a mesh surface, what we do is we look at some cells, local neighborhoods on the surface. It can be single triangles or one rings of vertices, as you see here. And then for each such local cell, we look at what happens to it during deformation. So if this is its original configuration and this is its deformed configuration, we want to measure how much that local deformation differs from a rotation. So what we look at is we take all these vectors, all these edges coming out of the vertex, and we see how much the deformation that they undergo altogether is different from a rotation. And this rotation here is the best fitting rotation, like the best that we could do in this situation. So it's a nonlinear energy because this best fit rotation depends non-linearly on the unknown deformed vertices, so vertex positions, obviously. But the nice thing is that there is a very, very simple minimization process. And that's why I think, I'm guessing that this work kind of became popular because it's just so simple to implement and there are no parameters to tweak essentially. So, so what we do is we pretend for a second that the rotations are independent variables. And we do a very simple local global optimization process where we, in one iteration, we fix these rotation matrices locally and only optimize for the vertex positions. So then you can see that it becomes a just a quadratic energy that you can readily optimize by solving a sparse linear system. So it looks something like this. And then in the second step, we fix the positions of our deformed vertices and only optimize locally for the rotations for these RKs. That amounts to, on a per one ring basis, we just need to solve a small 3x3 SVD problem to find that best fit rotation. And then we repeat the process until it converges. And the nice thing is that in each step we decrease the energy, and actually it decreases quite quickly in the first few steps. So it's very simple to implement. And in 2007, it looked something like this. So it works at interactive speed on small meshes. Or back then it worked on such meshes. Now remember, this is 2007, so this is historical footage here. And since then, actually, Alec Jacobson, my former PhD student, he improved by a lot this whole approach, and he showed how to do it in, at an interactive speed on very large, high-resolution shapes, in fact. So the interesting part for us here is to look at what As Rigid as Possible, or ARAP, does to a flat sheet. Because when I was working on it, my hope was that it would create isometric or nearly isometric deformations with which I could finally model paper or developable surfaces like paper. And indeed, you see that when we apply it to a flat sheet, it looks sort of like paper or cloth maybe. So that's already a bit less good because cloth is not developable. Oh, I see that. I think maybe, is it possible that my computer got stuck?
Olga, yes, sorry to interject. The video stream, the camera webcam stream seems to have turned yellow, yes. But also we seem to have had a technical hiccup at the very beginning, and the live stream lost the first 9 slides. Okay. So if you need to do a restart or restart the slide deck, that would actually be great for our conference attendees.
Yeah, let me try and reset the computer, because actually it's completely, the screen is stuck. I cannot do anything. So let me just quickly restart, okay? I'm sorry about this.
Yeah, thank you so much, Olga, and apologies for the technical hiccup.
So sorry, so sorry.
And many apologies for our attendees as well for the hiccup at the beginning. For some reason, the live stream did not boot as intended for the first few minutes of the talk, despite everything seemingly being fine. So many apologies, and we will resume shortly from the beginning of Olga's talk.
All right. I'm so sorry about this technical difficulty. I have no clue what happened. Let me
No
try.
worries. There were difficulties on our end as well. It seems like on both sides there were difficulties. And thank you so much, Olga. Please go ahead and let's try to resume from the beginning.
So would you like me to restart from the very beginning?
Yes, please. It seems like the first few slides got dropped in the live stream, unfortunately.
Oh, okay. Then I'll try to do it a bit faster so I don't screw up your schedule completely.
Thank you
so much. Manolis, do you want to do the introduction as well?
Because I will do that as well, real quick. Yes, for the audience who missed it. Sorry, Olga, but let me really quickly do the introduction again. It will be a deja vu moment for most of us here. So today we're delighted to have a keynote talk by Olga Sorkina-Hornung, who is a professor of computer science at ETH Zurich, where she leads the interactive geometry lab at the Institute of Visual Computing. She does research in the fields of computer graphics, geometric modeling, and geometry processing. And she has received numerous awards and recognitions, including the ACM SIGGRAPH Significant New Researcher Award in 2011, the Eurographics Outstanding Technical Contributions Award in 2017, and recently she was nominated as a fellow of ACM. We are very fortunate to have Olga with us here today. Please take it away, Olga. Thank you so much.
Thank you so much for the kind introduction. So let's try this again. Hopefully this time there won't be technical difficulties. So I would like to talk to you today about developable surfaces. These are basically surfaces that we can form into 3D shapes by starting from a 2D sheet and bending it or folding it. This is one of my most favorite subjects recently, and I guess the motivation comes really from fabrication, because, you know, unlike in 3D printing, in more traditional forms of fabrication, a lot of times we start from a flat sheet of material such as paper, cardboard, or metal, and then a 3D object is formed either by piecing together small parts of this sheet material or maybe even larger parts. So many shapes can be created in this way, from very fancy architecture by Frank Gehry to everyday objects such as, you know, basic mechanical parts and packaging and clothing and so on. Developable surfaces that are formed by bending paper or sheet metal are also quite common in art, and you see some very nice examples here from Eric Demain and from Zaha Hadid and Frank Gehry again. So really there are so many different areas of application for developable surfaces. I guess one serious advantage of developable shapes is that you can fabricate them with way less energy than you would require when you stretch material. So here's a comparison of two quite mundane everyday objects. The one on the left is a kitchen sink. Actually, I have to laugh when I see this photo of a kitchen sink, because we just installed a sink like that in our own home, and it was a big ordeal to have it custom fabricated for that kitchen. Anyhow, so this sink is made by taking a sheet of metal and pressing into it until, you know, the basins of the sinks are created. And this is a quite expensive process that requires a lot of labor, you know, a lot of energy invested into this pressing, and has to happen over an extended period of time in order to prevent material fatigue and ensure equal thickness, or more or less equal thickness, of metal everywhere. By contrast, on the right side, we see it's actually a piping nozzle, you know, for piping cream on cakes and things like that. So these nozzles are also made of sheet metal, but because of their conical shape, all you need to do here is bend them to sort of to create that cone, and then solder, you know, the seam that's created so that you have a closed shape of this nozzle. So the bending takes less energy and is faster to do and is more gentle on the material. So quite a lot of advantages here. So to say a bit more formally, mathematically, what are developable surfaces? These are surfaces in 3D that flatten perfectly, meaning that we can unroll them onto the 2D plane without any stretching or squishing. So they have, in graphics terms, they have perfect distortion-free parametrizations. A little bit more precisely, there are several different characterizations of developable surfaces. The one that's most familiar is what I said just now, but to say it more precisely, locally, a developable surface is isometric to the plane, which means that at every single point, we can find a small neighborhood, a small disk around that point that we can flatten to the plane isometrically, meaning without any distortion. Of course, globally, it might not be possible because of topology. Like the cylinder, we cannot flatten it, we cannot unroll it to the plane because we have to cut it first. But locally, it's always possible. And another also quite familiar, I think, characterization of developables is that their Gauss curvature is 0 everywhere. Or said differently, their Gauss map has 0 area. So it's a one-dimensional object. The Gauss map is basically the collection of all the normals of the surface. And so when seen as points on a unit sphere, these normals for developable surfaces form a collection of curves or a single bifurcating maybe curve, and it has 0 area. And then the third characterization is that developable surfaces are ruled surfaces, which means that at every point we can pass a straight line that is entirely contained in the surface. And not all ruled surfaces are developable, but for developables, they're always ruled if they're smooth surfaces, and the normal along the ruling is constant. So that's the characterization of developables. So, of course, not all surfaces in the world are developable. For example, a lot of common objects with non-vanishing Gauss curvature cannot be wrapped perfectly. That's, I think, a familiar problem to many of us. But still, I would say that the space of developable shapes is quite rich and interesting. And as I mentioned, a lot of fabrication advantages as well. So it's interesting to think about how to model this shape space and maybe even how to approximate general shapes that are not developable by such surfaces. So this is the subject of my research for several years now. And actually, I started quite long ago in my PhD. I tried to create a space isometry approach to model paper, folding and bending of paper. And you can see some of my attempts here. And while it looks kind of plausible, in fact, it wasn't working. I can tell you immediately. Basically, what I tried is to create a freeform space deformation that was comprised of rigid transformations, but I couldn't quite get it to be isometric. In retrospect, for obvious reasons, but back then I was still learning, as a young PhD student. So at that time, I abandoned this line of research of paper bending, and I turned to more general surface deformations of more general surfaces, not just paper. And I have worked on variational approaches to surface deformation, which is basically formulating some kind of functional or energy or loss, as we would say today, that quantifies how good the deformation is, and then trying to minimize that functional under some user-defined constraints, which are typically positional constraints. So in these examples here, the user fixes the purple areas and prescribes the positions for those. And the yellow areas are then optimized to minimize some elasticity measure, basically. So over the years in computer graphics, many different such energies were proposed. I guess the starting, the most famous one is by Terzopoulos that researched such shell bending energies. And also in the 90s, like Cobalt and colleagues worked on Laplacian-based energies, which is kind of like linearized elasticity. And also myself and my colleagues, we have worked on these Laplacian-based deformations. So basically trying to model something that looks like an elastic surface and preserves local details. And then when I was already a postdoc at the Technical University of Berlin with Mark Alexa, we worked on yet another deformation energy that turned out to be pretty popular in hindsight. And the goal was to find a so-called as rigid as possible energy, or as isometric as possible. So basically my hope behind the scenes was that if I find an energy that models isometry, then I could finally bend some paper, you know, because it starts as a flat sheet, and then if we're isometric, then the shapes that we create are developable through such isometric deformations. So the idea of this as rigid as possible, or ARAP energy, is the following. The formula might not look very pleasant, but actually it's super simple. So what we do is we look at cells on the surface. These local cells could be one rings or single triangles. We looked at one ring, so a vertex and its neighbors. And we take the original rest shape of the cell, of a cell, and then we look what happens to it when it's deformed. And the deformation energy measures the deviation of this local deformation from a best fitting rotation. So essentially, we look at all the edges emanating from a vertex. These are these guys here. And we try to see if we can fit a rotation to the deformation that happened between x0i and xi, or these edges, the original edges and the deformed edges. And everything else that cannot be explained by that rotation, that's what goes into the deformation energy. So it's a nonlinear energy, because this best fit rotation depends nonlinearly on the deformed vertex positions. But actually, it has a very simple way of minimizing it. Essentially, what we do is we pretend for a second that the rotation is independent of the vertex positions, as if it's like another variable, set of variables that we have here. And then we do a local global optimization process that first fixes the rotation, so it takes the current ones and just leaves them be, and only optimizes for positions. And then you see that if these RKs are fixed, then optimizing for positions is just a quadratic energy that we can minimize by solving a sparse linear system, something like this here. This L is actually the mesh Laplacian matrix. And then in the second step, we fix the deformed positions and find best fitting rotations for every cell, so every one ring on the mesh. And that amounts to solving 3x3 SVD problems for each one ring. And then we have these best fit rotations. And then we alternate these two steps over and over until convergence. And actually every step minimizes or decreases the energy value, both the rotation step and the position step. And it tends to converge quite quickly, or at least decrease quite quickly after the first couple iterations. So here's some historical footage of how it worked in 2007. Back then, we could do interactive shape editing on small meshes, but then it really ran in real time. And I have to say that later, my former PhD student, Alec Jacobson, actually really improved this technique, and with very smart subspace optimization, he managed to perform such deformations on very high resolution meshes of very high quality. So what was really interesting for me, though, was to look at how as rigid as possible or as isometric as possible deformation, how it performs on sheets, on flat pieces of material, such as this piece of the plane here. And as you can see, it looks not bad. It looks kind of like paper or maybe cloth. Cloth is already not so good because we know that cloth is not, it tends to stretch. So that's already a bit disappointing. And indeed, when we put as rigid as possible deformation to a hard reality test, it does fail. So in this experiment, what we did was take a surface that was produced with airwrap from a flat sheet. We 3D printed a kind of sandwich with which we can press a sheet of copper. And you see what happens. The sheet of copper buckles. That basically shows us that the surface is not developable. So there is really some stretching or deformation going on here that's undesirable. So that was another fail. In terms of developable surfaces. And then I had to actually wait for quite a long time, for 10 years, until I, had the honor of working with very, very talented and smart people who managed to solve the problem. So the work that I will show you now is mainly from the PhD thesis of Mikhail Rabinovich, and it was done in collaboration with Tim Hoffman, who is a professor of mathematics at Munich, Technical University of Munich. So basically, Mikhail in his PhD developed this concept of discrete orthogonal geodesic nets, which is a model for developable surfaces that is discrete, that's based on nets or specialized meshes, as I will show you now. So basically the point of departure was to say that, well, we know that as rigid as possible doesn't work. And the reason for its failure is probably this minimization here, that it's only as rigid as possible or as isometric as possible, but it's not truly isometric. So it has this energy has an error. When we find a minimum, that minimum is not zero. Right, and what we would like is really a model of perfect developability and not, approximate. So some constraint here is necessary that would create that shape space that we're looking for. And then actually, Mikhail and we came to the realization that modeling specifically isometry can be even limiting. Because some deformations of developable surfaces are not isometric. For example, this is a trivial example, but if we take a flat rectangle and we stretch it in the plane, then all the surfaces that we create this way are developable, but this is not an isometry, this is stretching. So it's surprising that stretch can preserve developability, but it is true. And also the deformations that you see on the right are not isometries, but all the shapes in between are still developable. So it's a deformation that moves inside the developable shape space, but it's not an isometry, it's bigger than that. So I guess that kind of ruled out for us this attempt to model developability by deformation. Is the video again stuck? Hello?
It appears to be stuck again, but we hear the audio.
Oh, I can't believe it. It's cursed. Huh? How about the live stream? Is that working?
That appears to still be working fine.
Okay. Well, I apologize profusely. I guess I will have to restart again. I'm so sorry about this. Yeah, just give me 1 second. I'm so super sorry.
No worries, no worries. Thank you, Olga.
Okay. Let me try again. Can you guys hear me?
Yes.
Perfect. Yeah, I'm so sorry. I have no idea what's causing this issue, but at least the live stream is hopefully working. Maybe it's a cursed slide.
Let's hope that the third time is a charm and everything will go smoothly from that one.
Indeed, indeed. So are my slides visible? Is everything okay?
Yes.
Okay, great. Then let us continue. So we decided also not to use a ruling-based representation, which is what many of the previous works did. That's because rulings are not invariant to bending. They basically change as you bend the surface, and then you also have to adapt the representation, and that's quite difficult, in fact. So here's an example of a developable surface that has a certain structure of its rulings. And topologically, it looks something like this. There is the planar part, and it's connected to four cylindrical parts. And as you deform the surface, so in an interactive editing situation, we can imagine that we would, deform this four-cornered surface into a cylinder, for example. And these two are actually isometric surfaces even, but the first one has this structure of the rulings, and the cylinder has a different structure of the rulings. It's actually one single ruled patch. And you see that if the representation is explicitly encoding the rulings, then it would have to really make a significant topological change here to go from here to here. And that's not really feasible for interactive shape editing. So what we propose is to work with a new discrete model. Basically, we don't insist on taking, any arbitrary triangle mesh, but we propose to work with very specific quad meshes, namely with so-called nets. Nets are simply completely regular quad meshes, so like grids or parts of a grid in 2D, so parts of Z2. So they can have holes and they can have cuts, but generally every interior vertex has degree 4, so it's connected to 4 quads. And another thing that we decided on is to give up the so-called real mesh developability, meaning that the meshes that we model, we agree that they're only approximations of smooth developable surfaces, and the meshes in themselves are not necessarily developable as polygonal objects. Yeah, and this is motivated by the fact that it kind of happens in nature, let's say. So if we have a straight or a flat sheet and we discretize it, it might look something like this here. And then as we smoothly bend that sheet, then when we create curvature, obviously these points come closer together. And as a result, edges on our sampled mesh will get shorter. Right, so this is what also happens in our model. So it doesn't preserve edge lengths as the developable surface deforms, but the edge lengths can actually change, and still we approximate a true developable surface. So we talked about the 3 different characterizations of developables, and we kind of ruled all of them out, and actually Michael in his PhD came up with a 4th characterization that is way less known, I would say, in computer graphics, but it's still valid. And that is that developable surfaces are the only kind of surface that can be locally parametrized by orthogonal geodesics. So you can find a parametrization whose parametric lines are all geodesics and they are orthogonal everywhere. So what does this mean? A bit more explanation is perhaps good. So geodesic lines are like the extension of shortest path or straight lines on curved geometry. So for example, on spheres, the geodesics are great circles or parts of a great circle. And this is some general curved surface where you see the geodesics. And on developable surfaces, it's very interesting. So because developables are isometric to the plane, geodesics on developables are actually straight lines that got bent as the surface got bent. So if we look at this cone, for example, when we unfold it to the plane, then a geodesic on it becomes a straight line. And the same thing happens to all the different developable surfaces. Okay, so what this means is basically that an orthogonal parametrization of geodesics is like taking a grid, a rectangular or orthogonal grid on the plane, and then mapping it into a 3D shape. And if you manage to map it in such a way that all the lines remain geodesics and orthogonal to each other, then you created a developable surface. And I'm gonna give you a spoiler here. Basically, the work comes down to describing discrete developable surfaces or nets, as I mentioned, so these regular quad meshes. Basically, the definition is very, very simple. A quad net is a discrete developable if all the angles around each vertex are equal. So different vertices can have different angles around them, but for each vertex, all the 4 angles around it have to be equal to each other. And that's it. That's the whole definition. So it sounds kind of surprising, very, very simple. And let me explain maybe where it comes from. So it comes from a theory in mathematics of discretizing various surfaces. And already very long time ago, mathematicians looked at discretizing general geodesic nets. So parametrizations by geodesics, not necessarily orthogonal ones. So this would be a surface parameterized by geodesics, and this would be a surface parameterized by orthogonal geodesics, and then it has to be developable. So what is a general geodesic net? In 51, Wunderlich came up with a definition. Basically, a geodesic curve is as straight as possible. And that on a discrete surface means that we have equal deviation from angle pi on both sides of a curve. So if we look at such a curve in our discrete surface, in our net, then we want the sum of the angles on the left side to be equal to the sum of the angles on the right side. And the same for the other direction, the other family of coordinate curves. So this green one should have these 2 angles, alpha 2 and alpha 3, should be equal to alpha 1 plus alpha 4. And when we take these 2 equations together, what comes out is that opposite angles should be equal. And then that means that this net is a generalization of a geodesic parametrization. So these lines, the coordinate lines in such a regular grid are geodesic lines, discrete geodesic lines. Okay, so we took this definition and now we want to add orthogonality to it, and that would force the thing to be developable and discrete developable. So let's look at such a discrete coordinate curve. So now we put it, you know, in 2D. So we can, you know, generally we can pass a plane through these 2 edges. It's the osculating plane of this curve. And now let's look at the edge vectors normalized and define a normal. So how can we define a normal? Now we can, we know that the difference of these 2 normalized edge vectors could be seen as a tangent, a discrete tangent. And the normal would be then 90 degrees rotation of the tangent, or in other words, the sum of these 2 normalized direction vectors. Right, so now we have a normal definition and a tangent definition. And to say that 2 intersecting the coordinate curves at the vertex are orthogonal is to say their tangents should be orthogonal, right? So we have the discrete tangent of the first one and the discrete tangent of the second one, and we just ask these 2 tangents to be orthogonal, right? So that could be one condition. And note that if we assume that this is already a discrete geodesic net, meaning that opposite angles at each vertex are equal, then we are guaranteed that the two normals of the two intersecting coordinate curves coincide. It's actually the same normal n, which is also the normal of the surface. And then what actually Michael proved in his first paper is that the following three conditions are equivalent to each other. So assuming that we have a geodesic net, a discrete geodesic net, meaning opposite angles are equal, it is equivalent to say we want the osculating planes of the surface of the coordinate curves to intersect orthogonally, or that these coordinate curves projected onto the tangent plane should form an orthogonal cross. Or the third and the simplest condition is that all angles around the vertex should be equal. And notice that this condition already also subsumes the fact that it's a geodesic net, because in a geodesic net, opposite angles are equal, and here all angles are equal. And you know, so it's a geodesic net, and it's also an orthogonal geodesic net. So basically, this is a super simple condition that we can plug into any surface optimization, right? So we can take some regularizing energy, like a Laplacian energy, for instance, and we can also add isometry regularizer, so something that softly asks mesh edges to remain equal in length to the original mesh edges. And the hard condition here, though, is that all angles around each vertex are equal. And that is what makes it constrained to the shape space of discrete developable surfaces. And then we can, we can minimize this energy using some nonlinear technique like LBFGS or second order majorization, and create interactive editing tools basically with it. So here you see one example of just deforming a sheet, a flat sheet, into a 3D shape, and this is a discrete developable shape. But it doesn't have to be such boring shapes. We can also create more exciting ones. For example, mimicking paper bending. We can also have different topologies, so we can cut and create holes in our surface, and have different ones. And here you see an example of comparing a simulated or discrete developable surface with a real one created, just from paper, and you can see that they look quite similar. Maybe, unfortunately, I'm running out of time, but let me just show you a couple more examples of how this deformation looks like. So remember how we lamented that rulings change with the deformation, and we cannot really, we cannot change the topology of the rulings, but with the technique that I presented, because it's completely agnostic of the rulings, it's free to change and rotate them and change their topology in any way it likes. So this is what you see here in this interpolation example. So yeah, we validated this technique by fabrication, and we managed, to rectify the problem that we saw earlier with as rigid as possible. And perhaps I'll finish with some, very, very quick advertisement. So the code for these discrete developable surfaces is on GitHub. You're very welcome to check it out. It's in Mikhail Rabinovich's repository. And we also checked, that analytically it makes sense, and there are some convergence properties of these objects. And let me maybe finish with a couple of things that we are doing now that I'd like to show you. One work with my current PhD student, Flora Fairhoven, is to remesh these discrete developable surfaces into a ruling-based representation at the end. So that's actually something that's quite desirable for fabrication if you want to create surfaces made with flat panels. Then it's actually useful to create a remeshing that aligns to the rulings or to the curvature directions, because then the panels that are created are guaranteed to be planar, in fact. And in addition, we've investigated curved folding with Michael, and here are some examples of that work. So we don't have to model only smooth surfaces. We can actually make surfaces that, sorry, here's a better example. Surfaces that have sharp features and sharp creases in them. So here are some examples of such surfaces, and we've characterized what it means to have a curved fold in such a discrete developable surface. And currently, what I'm very interested in is approximation of general shapes with developables. So there have been a number of fantastic works on the subject by Oded Stein, by Sylvia Celan and colleagues. And we have also published some work of how we can wrap a general object with pieces of these discrete orthogonal geodesics and create shapes from that. And also we have a new work on this subject, but it's not published yet. So I'm only putting a small teaser here to show you. So basically it tries to thin the Gauss map of a general object and create a one-dimensional Gauss map, and that creates a piecewise developable approximation. All right, so unfortunately, I can't show many interesting mathematical details here, but let me stop here, and perhaps if there's one short question, I guess we could still maybe answer, and if not, well, thank you very much for your attention here.
Thank you so much, Olga. Thank you so much. And apologies for the technical hiccups.
I guess my computer's fault. I'm sorry about that.
And unfortunately, due to the little bit of time lost, we will not have much time for Q&A. So we will need to move almost immediately to the next session. But thank you again so much, Olga, for giving
Thanks a lot. Have a great remainder of the conference. Thank you. Bye-bye, guys.
Okay, we have to move to the next session, unfortunately. I'm delighted to introduce Florian Alt for our next invited speaker. Florian Alt is a full professor of usable security and privacy at the Bundeswehr University in Munich, Germany. His research is at the crossroads of human-computer interaction and IT security. In particular, Florian is interested in how novel, secure user interfaces can be built that blend with the way in which we interact with computing devices. Specific research areas include, but not limited to, behavioral biometrics, social engineering, usable security in smart homes, and secure physiological user interfaces. Florian co-authored more than 200 publications, many in leading venues of his field, such as SEM SIGCHI, SEM WIST, and SUPS. Florian holds a diploma in media informatics from LMU Munich and a PhD in computer science from University of Stuttgart. Let's give him a big virtual hand and let's hear from Florian Alt.
Thank you very much, Ahmed. And thank you so much for this nice introduction. So this will be sort of quite a leap in terms of the topic I'll be talking on, but still I hope you'll enjoy this. So this is actually my first time in the Graphics Interface Conference, and I appreciate having been invited here. And so in my 20 minutes, I want to take you on a brief journey through the world of behavioral biometrics, a line of research that I'm working on with my group. And in particular, I want to talk about challenges and opportunities from an HCI perspective. So you already introduced me, so I think I can just keep that short. So I just wanted to say that, well, my background is in media informatics. I then basically left university for a while after graduating, working in industry, in particular for 1.5 years in the US, but then came back to do a PhD in various locations in Germany, and ultimately, as you said, graduating from the University of Stuttgart. And then I accepted a faculty position at LMU in human-computer interaction before 3 years ago. I decided to transfer to a research institute for cyber defense, where my work is now more at the intersection of IT security and HCI. And this sort of research area is commonly referred to as behavioral biometrics. All right, so my work has very long since been inspired by Mark Weiser and his vision of a world in which computers are ubiquitous. And so he was the one who, at the beginning of the 1990s, predicted that we would soon be living in a world that would be dominated by different types of output devices, which he referred to as taps, pads, and boards. And if you look back at that vision today, 30 years later, we see that this vision has, well, largely become true. So we have those devices. We call them a bit differently, but I think it's fair to say that they have become ubiquitous. But the interesting thing here is that this is not the end of the story. So because today we witness that, that there is more and more technologies that at least do have the potential to also become ubiquitous entering the market. And I just brought a few technologies here, many sort of intelligent devices, smart home devices, AR, VR, HMDs. And now taking the perspective of the security researcher here, what is quite striking is that the development of security mechanisms is not keeping up with that pace at which those technologies sort of emerge. And the reason for this is that we as designers, and I include myself here, are I guess quite good at adding exciting new features, at exploring new application areas. But then we rarely think about the fact that such technologies are often dealing with sensitive data that need to be protected. And often this need to protect data only becomes apparent as technology starts to, well, being used in daily life. And as a result, what you often see is that people try to fix security post hoc. And this in many cases leads to sort of, poor usability. And just to bring one example, thinking about TVs, so as they became connected to the internet, became smart TVs, well, the need for security mechanisms was not really anticipated or addressed. And so what happens today, if users want to authenticate with their favorite video streaming platform on their smart TV, is that they're required to enter a password with their remote control. And we all know that this is pain in the neck. And as a result of this, what happens then often is that security is sacrificed, in this case, for example, by just asking the user to authenticate once when they sort of set up the application, but then never again. And this is sort of understandable because security is something that is annoying for users. It's something that just gets into our way while we're trying to actually do other things. And I would argue that the same is to a certain degree also true for designers, because security, well, is just not the most exciting part of creating new technologies, right? And so what we often see is that we just stick with what has established itself as being just good enough. And just to stay with this example of passwords and text-based passwords. So this authentication mechanism was developed in the 60s. We're in the mainframe era and people have at most access to one computer, right? And then during that time, it was fine to sort of type in a password like a few times per day, like when you came in the morning or after your coffee break or after the lunch break. But what is striking now is that this mechanism is still one of the most popular security mechanisms we have today, despite the fact that the way in which we interact with computers has really changed fundamentally, right? So today we can access sensitive information anytime and anywhere on personal devices, in the cloud. So the average user has 90 different online accounts, so many more than passwords than the user can remember, actually. And also we authenticate much more often, which means that there is a massive overhead in authentication time. And now I think you agree with me that this is not something that is very likely to change in the near future. And it raises the question how we can consider security early on in the design process. And from a user perspective, how we can manage to better integrate security with how we naturally interact, and optimally in a way that doesn't require us to think about security anymore. So what if, for example, our workplace, by the way in which we are using all the objects on it, and if I look around myself, I have a laptop, a mouse, a keyboard, some speakers, but also like analog things such as a coffee mug, a pen, a stapler. What if all those objects could be used to, well, understand or verify that it was actually me who is working at that desk? And so what you can see here is a prototype that we built to actually explore such concepts. So we did it like a few years back, and what it actually allows is to make literally any object that we have on the desk touch sensitive, simply using capacitive touch sensing. And this is just one technology, and we could also use cameras. But what it does is that it allows us to sort of prototype and try out new interaction and authentication concepts. And I will in the following talk a bit more about one of the underlying concepts, that is behavioral biometrics. And well, behavioral biometrics are enabled through the fact that our environment, as well as our personal devices, are increasingly being augmented with sensors. And in particular, wearables even move those sensors closer to the body. So what does behavioral biometrics actually do? Well, in comparison to physiological biometrics, where people are identified based on, well, for example, fingerprint or visual appearance, behavioral biometrics try to find unique patterns in human behavior to identify people. And so, for example, people can be distinguished based on how they walk. So by looking at features such as gait length, or walking speed, or type of walking. And in a similar manner, we can try to distinguish people based on how they write text on a smartphone, by looking at finger position, the applied pressure, typing rhythm, typing speed, and so on. And now, this basically allows us to build new authentication mechanisms that work seamlessly in the background. And in this video, and I hope you can see that well, this is just an example where I play an attacker who tries to access personal information on the smartphone of another user. Now, what the system does is that in the background, it analyzes how the current user picks up the phone, how they hold it, how they type in a search query. And then the system detects that the user seems to not be the legitimate owner or a legitimate user of the device, and hence locks it. I just want to briefly mention on the side that security isn't but one application area of behavioral biometrics, but we can, for example, use it also for other things such as building adaptive user interfaces. So this is just an example from our work where the smartphone considers the user's physiology or their behavior to basically adapt the slider. But that's just sort of a side note. So how do we build such a behavioral biometrics system? So simply speaking, what we do is we observe users' behavior. More concretely, we look into specific features of human behavior and then take these features to create behavioral models of the user. And we then compare the behavior of any user of a system to these models and try to make a prediction on who is currently interacting with the system. And then, well, we can do additional things such as, for example, calculating an identification accuracy, which could serve as an indicator for the security of such a system, but I'll come back to that a bit later. Well, so this sounds as if this is sort of, well, straightforward, but actually it is not. And there is a lot of challenges, many and more of which you might think are related to human-computer interaction. And what I'd like to do in the remainder of this talk is to sort of show you some of those aspects. So let's assume now that we design a smartphone application that we want to be using behavioral biometrics as an authentication mechanism. Now, when you look at the current smartphone interface, we see that there is, well, many different user interface elements. App icons, keys, links, buttons of different sizes. And the question is now, how should we create and position elements on this user interface such that a behavioral biometric system can verify the user's identity in real time with an as high accuracy as possible, or in other words, well, which design parameters of the user interface play an important role here. And so in order to find it out, what we did was we looked into how different user interface elements influence identification accuracy. In addition, we also looked into the influence of hand posture. So for example, whether the user is just sort of typing with their thumb or holding it in one hand and typing with the index finger. And we also looked into the influence of the position of the element on the screen. And what we found was basically that targeting with the thumb leads to a much higher accuracy for identifying the user, apparently because our behavior is much more unique when using the thumb. The second interesting thing is that the smaller the target, the more accurate the results. And the third thing is that in particular, when interacting with the thumb, if the elements are closer to the edge of the screen, the system gets more accurate. So what one can conclude from this now is that in order to build an interface that optimally supports user identification based on behavioral biometrics, it would be good to have a user interface that uses rather compact elements, that is thumb friendly, and where the elements are rather close to the edge of the screen. Now, what's interesting, if you look at, for example, current Android designs, is that they, to at least a certain degree, seem to fulfill these requirements quite well. There is one interesting observation here. So behavioral biometrics, or in general authentication mechanisms that reside in the background or are implicit, hold a lot of promise due to their ability to cope with the usability security trade-off. So if you think about a password, generally speaking, the longer your password is, the more secure it gets. But at the same time, this negatively influences on usability because it's more difficult to remember. It just takes longer to enter it. Now, but what is interesting here is that there seems to be a similar trade-off, because what we found was that elements that are smaller and closer to the edge of the screen lead to a higher accuracy. But then at the same time, this means that the interface might be more cumbersome to be used. So this was something that was quite surprising. The next question is, and I get this asked quite often, is, well, how secure are such schemes based on behavioral biometrics actually? And to briefly recap, I mentioned that the biometric value can basically be used as a means to assess security. But this metric is not really based on a realistic attack model, because it assumes that the attacker would try to hack the system by just showing their personal behavior. However, if I was a smart attacker and I was to break into a system that is protected with behavioral biometrics, what I would do was I would observe the victim, how this victim is behaving, and then try to imitate this behavior, making the system think that I'm the other person. And the question is this possible? And we try to find that out for a particular type of biometrics, which is keystroke dynamics, so behavior while typing on a smartphone. And what we did was we developed different visualizations that communicate to the user how they should sort of behave while typing on a smartphone. So how did this look like? We in total sort of communicated 4 different features. The first one is the size of the area of a touch, or like abstractly speaking, how hard you press. And this is visualized by the size of this red dot you see here. The second feature is the time for the keystroke, so how long the user presses, and this is visualized through the width of this gray box. Then we have the so-called touch to key offset, which is sort of the distance from the center of the key to the touch point. And we visualize that just through the position of this red dot on the key. And then finally, the flight time, which is actually the time between 2 consecutive keystrokes. And this is visualized through this white space in between 2 gray boxes. And so we showed this to users and asked them to sort of try and elicit and show exactly that behavior. And we tested then those 4 features in various combinations. And what we found out was that, well, mimicry, so we refer to this kind of attack as a mimicry attack. And we found that this is generally possible, but it really strongly depends on the nature of the feature. So if the feature is spatial, so meaning that people are required to aim precisely, so for example, the touch to key offset, then people did quite well in sort of mimicking this behavior. But as soon as they were asked to sort of attack or mimic a temporal feature, such as the time of flight, it became really difficult because people had to act under time pressure. There were more findings. So apparently when you want to modify multiple features, it gets more difficult. But yeah, people certainly became better over time. And again, so there are several implications, and just one that I want to point to here, because I thought that was interesting as well, is, so, well, the interesting thing is that spatial features have a higher biometric value, but then at the same time, they're also easier to attack. So again, you're running in sort of a trade-off here. All right, so the last aspect I want to talk about here is, well, how can we understand behavioral biometrics in the real world? And I didn't make that very explicit, but in the past 2 projects, what we did was that we invited people in the lab and sort of let them work in a very controlled environment. And the same is true for most of the work that is done in this field. And so the question here to us was, how can we collect data in a more realistic scenario? And the motivation or the assumption behind this is that behavior in the real world might be quite different from what people show in the lab. And so on one hand, we wanted to observe real contexts, and we also want to collect data from non-artificial tasks. So for example, while people are really typing instant messages or emails, rather than predefined texts that we generally use in the lab. And well, what we did was we implemented a custom keyboard app that allows us to study such natural typing behavior. And now, if you think a bit closer about this, you might sort of ask, whoa, wait, what you're doing here is you're sort of essentially building a keylogger. So how about privacy here? Because you would be able to sort of reconstruct what the user is typing actually. And so part of this contribution of this app here is that we provide a filter mechanisms to sort of cope with this issue. And so one thing this concept does is that it excludes obviously sensitive data, such as passwords. The second thing is that the user is empowered to explicitly turn off login by means of a private mode button that is integrated with the keyboard. And then the third thing is that we apply a filtering algorithm that obfuscates the logged text. And we do this by what we call n-grams, or what is called n-grams. And the idea is not to log the entire text written by the user, but just some of the touches. And so here's a specific example of what we did in the studies, how we log so-called n-grams, meaning 3 consecutive characters, which are sampled with a 10% chance. And this is sort of the text describing the Chi conference. And when you apply this filter, this is basically what you get. And I'm not claiming that it's impossible to reconstruct this text, but at least it makes it kind of, very difficult. And so we could then sort of take this keyboard app and sort of really give it to people, install it on their phone, and sort of really start collecting data in the real world. Right, so slowly coming to an end. So what I showed here is just sort of 3 examples, but the interesting thing is that there is really a lot of HCI challenges here, many more, that partly some that we are working on, some that we were thinking about. And it includes things such as thinking about how we can really integrate behavioral biometrics in everyday life, also beyond the security perspective, what the role of the user's physiology is, how we can account for changes in human behavior, and what really the user's view on mechanisms related to behavioral biometrics are. So very brief summary. So I think I have convincingly shown or demonstrated that in order to build more secure and at the same time usable interfaces, we need to really look at different stakeholders. not just end users, but also designers, developers, administrators. Then there is a need to really better understand the implications of using such mechanisms in different application areas. Today, we use them not only in workplace, but at home, in public space, in cars. And the interesting thing is that current technologies usually do not account for this. So the smartphone doesn't care whether, like which information the user accesses, whether what the user is currently doing, who is with the user, and where the user is. Closely related, going into new application areas, of course, also sort of requires us to think about how we can study and understand them. The keyboard is just one example, but yeah, there's apparently many methodological challenges. And then the last one is that really this usable security is at the intersection of many different disciplines, and there's really a need to think about how we can mutually benefit from each other. So thinking about user behavior, certainly social sciences and psychology have a lot to contribute. For data collection, I mentioned computer vision, probably. For user modeling, that's apparently sort of close to machine learning, and so on. And so just to close, if this was a really just very high level overview of challenges in this area. And if you're interested in that and want to read more, I just recently co-edited a special issue with Emanuel von Setschwitz. And in the editorial, you can find the aspects I talked about later in more detail, and you can just access it freely on my website if you're interested. All right, so yeah, with that, I'm at the end. But I don't want to close without mentioning that apparently lots of the things that I showed you here are a result of working with a lot of really great people. We don't have an actual picture because in last year apparently we haven't gotten together. But yeah, they certainly take credit for much of the things I showed here. Yeah, so that is it. I'm looking forward to the discussion. Thank you very much.
Thank you, Florian, for the excellent talk. We already have some questions lined up. I'll try to group them up based on common themes because of time limitation.
Sure.
We have a question from Celine Latulipe, who asked that how diverse are your participant pools for this type of work? Do you include older adults? So this is involving overall diversity in the population pool. On the other hand, Carl Gutwin is asking about individual variability. He's asking that if techniques like typing analysis are used for continuous authentication, how much variability is there in users' normal typing behavior? Could this cause authentication error?
Mm-hmm. Okay, yeah, so yeah, just try to answer that. So yeah, this is both really excellent questions. And simply because apparently, so if you're building those models, you, depending on whether you want a person or a person independent model, you might want to sort of then, yeah, account for things such as age. And this is particularly important because apparently with age, your sort of abilities might change. And then the question is sort of how you account for this. And apparently, yeah, as we usually do as university or often is that we sort of take convenience samples, even though, I mean, I really have to lie because I would need to go back to the paper and really look into the demographics of those 30 people. I think that was certainly a much more diverse sample because this was sort of something out of the lab where people didn't really need to come in. Yeah, so I can't really answer how the sample looked like. I would need to go back to the paper, but yeah, certainly I agree that this is an important point. Okay, the second one, can you just sort of recap what the second question was?
Yes, so the second question was about individual variability, that if the techniques like typing analysis are used for continuous authentication, how much variability is there in users' normal typing behavior? Could this cause authentication error?
Yeah, so I mean, this entire technology is built on the assumption that behavior of people differs. but then, and I think this is one of the questions I just sort of raised in the end, is how much is physiology and how much is behavior, right? And this is something that is quite difficult to separate. And that's something we are currently looking into. So we published a paper this year in CHI where we did a study in virtual reality where we changed the physiology of the user. So we sort of increased arm length or the height of the user, I think. And by doing so, what we were trying to do was to take out the physiology of the user of the behavioral model and make the model really focus on behavioral changes. And what we saw there is that this increases accuracy, which first sounded a bit counterintuitive to us, because one would argue if you have an additional feature that distinguishes people, that should make it actually more accurate. But it seems like there is really a lot of noise being introduced. And I think we have not really completely understood it because apparently behavior might still be closely linked to physiology. So you might behave in a certain way simply because you're, for example, taller. So you might not take this extra step because things are at your arm reach if you grab them, for example. And yeah, I think this is really something that we need to dive deeper in the future to really understand how those two things relate to each other. I hope this to a certain extent answered the question.
Thank you, Florian. There's another question which also falls under this variability topic, I think. Tawaki Takikawa asking, can this sort of interfaces be made robust to change in behavior over time, or if there's a long gap between authentications?
Mm-hmm. Yeah, that's also a really interesting question, and a very good one. So from our experience, I think models that you use to identify people have to be updated really frequently. And this might strongly depend probably on the task during which you're authenticating people. Just there's such a huge design space that we couldn't really deep dive into there, but apparently there is so many things that influence on how you behave, starting with you cut your finger, which certainly has an influence on your touch typing, or you exercise and have sort of muscle fatigue or things like this. And I mean, the easy answer to this would be, if you have enough data, this will be part of your model. But apparently, I guess the question is then how you sort of get to this point. And my well-educated guess would be that in the beginning, you sort of need to do a lot of sort of sampling and retraining.
Thank you, Florian. I think we can take one short question. Fabian asking that bit of a tangent question, but did you investigate whether there are groups who are better at imitating typing characteristics better than others? For example, piano players or surgeons come to mind.
That's an excellent question. We did not, honest answer. But I could totally see this, that some people might be better attacker than others. And I would also argue that this strongly depends on the type of behavior you're looking at. So I gave a workshop at ETRA, so the eye tracking conference yesterday on gaze-based security. And there we were actually just thinking about or discussing about, so what about if you use eye movements as a behavioral biometric? How difficult would that to be mimicked? And I would argue this is way harder as opposed to typing. So I guess the kind of answer is that this really strongly depends on the behavior and the task. And I could definitely see that also the ability of the attacker here might play a role. Yeah, absolutely.
Thank you, Florian. That's all the time we had, unfortunately. We really appreciate you accepting our invitation to speak.
Thank you for inviting me. It was my very pleasure. Thank you.
Thank you. Thank you very much. With this, we're going to move to the next session. Maulis, take it over, please.
Yes, thank you, Ahmed, and thank you, Florian. So we are very happy to have Angela Dai with us here from the Technical University of Munich, who will be giving the next invited talk. Angela is an assistant professor at the Technical University of Munich, where she leads the 3D AI lab. Her research focuses on understanding how the 3D world around us can be modeled and semantically understood, leveraging generative 3D deep learning towards enabling understanding and interaction with 3D scenes for content creation and virtual or robotic agents. She received her PhD in computer science from Stanford, and she has been recognized through several awards, including a Center of Digitization of Bavaria Junior Research Group Award and an ACM SIGGRAPH Outstanding Doctoral Dissertation Honorable Mention. So without further ado, Angela, please take it away.
Thanks for the great introduction. I'm very happy to be here today, and I'd like to talk about the path towards democratizing content creation. So being able to capture real-world environments and convert them into 3D models, 3D content that can be then used for various types of applications, such as for content creation, being able to start off with a 3D model of a real environment and then tweak and refine, as well as mixed reality kind of scenarios where you want to be able to create things like mixed virtual interactions with real world kind of environments, or augment real environments and objects with extra kind of information. And so for that, we want to be able to capture these kinds of geometric models of real 3D scenes and be able to understand the objects and interact with them. So one very promising way to capturing 3D reconstructions of real world environments is by 3D scanning with commodity range sensors. So here you have a Microsoft Kinect that is capturing color and depth streams and localizing where the camera frame was, where these frames were taken, enables us to fuse all of the observations together into a 3D model of the scene that's being captured. So this is an example of real-time 3D reconstruction work that we've done that's basically globally optimizing for all of the camera locations during the capture of this particular scene. So you can see the dynamic updates according to the global optimization in the reconstructed scene geometry here. It's all adapting according to new camera observations. So this is pretty nice in terms of capturing geometry of these observed frames, since we can actually have geometric estimates from the range sensors, depth measurements, and you can actually get a fairly faithful reconstruction of these kinds of environments. On the other hand, there's still a lot of things that are missing from these kinds of reconstructions. For instance, if we're taking a look from a different view of this particular scene, you see there's actually a couple of large challenges here. So one is that the observation is not fully complete. And in practice, when you have a complex scene, there will always be some kinds of occlusions, like for instance here with the monitor on the wall, or many different objects that block each other under the tables. So you'll end up with this kind of incomplete geometric observation, as well as the fact that we actually don't have currently any kind of semantic knowledge about which objects are actually separate from each other, or what can be done in order to interact with the objects in the scene. So let's take a look at some of these challenges. So how can we estimate what's the geometry in areas that we haven't actually observed? This is a task that people are particularly good at when they see only a partial observation of a scene. It's easy to estimate, well, if you've seen the chair back and maybe a little bit of the chair legs, what the entire chair and the seat look like from just a partial view. So here, an interesting challenge is that with real data capture, we're in the end capturing incomplete reconstructions, but we can take a look at formulating a machine learning-based data-driven approach to learning these kinds of geometric priors for what complete geometry might look like. In this case, we can do this in a self-supervised way from incomplete scans as a target supervision. So here an RGBD scan is being fused together from a set of depth frames. So these can be fused together with a volumetric fusion approach into the target reconstruction that still has some holes in occluded regions. And then we want to create an input scan corresponding to this target with similar kind of characteristics that you see in real world kind of scanning. So here we can do this by removing some of the frames from the original set of depth observations. And so that allows us to pair together this kind of incomplete scan with a more incomplete one. So we can learn this pattern of how to go from more incomplete to less incomplete geometry. So that gives us a chance to learn these kinds of structural geometric priors for what might actually be missing. And since, of course, this target scan is actually not a fully complete observation, we actually can figure out what has been unobserved space just based on the camera visibility. So basically, regions in front of an observed surface are known to be empty, but regions behind the observed surface are unknown and have been unobserved. So these regions, we know that we don't actually know enough information about them and can actually mask them out from any kind of reconstruction loss. So this allows us to form a self-supervised approach towards this geometric scene reconstruction task. And so we also want, in this case, to be able to generate fairly high resolution geometry, which can be a challenge when operating on these kinds of voxel-based representations like volumetric TSDFs. So in this case, we have an input scan that's represented as a sparse truncated sign distance field. So everything only within truncation distance of the surface is actually being stored here. And we can encode it with sparse convolutions that operate only on known surface geometry areas. And then in order to be able to actually generate geometry in new regions that we haven't seen, we can do this in a coarse defined fashion. So we make a very, very coarse prediction densely so that we can actually generate geometry in new regions and then continue to upsample and refine the geometric predictions at every hierarchy level, upsampling by a factor of 2 and basically progressively generating the geometry of the final output scene, which is then represented actually as also a sparse truncated sign distance field. So then we can extract out the mesh at the isosurface of this distance field at as a level of 0, which is what you see here being visualized. And so the combination of this kind of sparse generative approach along with the self-supervised formulation, what's cool about this is because we actually are ignoring unknown, unobserved regions and target scans, we can learn to generalize across the entire set of trained data in observed scans. And if we've seen different kinds of partial observations of various different types of objects like sofas and chairs, we might be able to generalize across these patterns to be able to generate something more complete than any single target scan that's used during training. So you can see that here where this is an input observation and the generated complete version, as well as the target scan corresponding. So here there's actually some holes here in occluded regions in the target scan where we can actually predict what the complete geometry would be like based on these partial observations. And here you can see a few more examples in terms of this ability to actually generalize the generation of geometric structures in these scenes. And so quantitatively, this is also a very effective kind of approach. If we use an L1 error metric in unknown regions in these scans, we can outperform state-of-the-art learned and traditionally optimization-based approaches towards this kind of task. So here you can also see this effect of the masking of these unobserved regions in the target scans, which is pretty important because this is what allows us to actually learn to generate geometry in regions that are often seen or unseen because they're occluded in the training set. So without that kind of masking in this second column here, you end up actually generating these kinds of patterns of occlusions in the output because that's kind of the learned target distribution. And so this is also fairly robust actually to the degree of target incompleteness of the observed scans that we use for training, where here you have a couple of different levels of incompleteness for the train scans, where the blue bar represents using all data available, and the orange bar actually uses only 60% of the frames to generate target frames or target scans, and green for 50% of the frames. So here you only get a very slight drop in performance when using more incomplete target scans. So this lets us pretty effectively learn how to understand and estimate geometry in unseen regions. But we don't yet have really an understanding of the objects inside the scenes. And so this is what we've taken a look at with this part-based understanding, since in order to really enable interactions and high-level understanding, we not only want to know what objects are in the scene, but actually what are their part decompositions, because people usually are interacting only with certain parts of an object, like the seat of a chair, and the top of a table are supporting different kind of actions than the other parts of these kinds of objects. So in this case, we're taking a look at going from this kind of incomplete observation of a scene and predicting every individual object instance along with its part decomposition that estimates the complete geometry of that object, even in some of these regions where we haven't observed the full geometry of the object so far. So this is based on state-of-the-art object detection in 3D, coupled with a part decomposition prediction, where we basically are leveraging knowledge of part priors in order to be able to predict the part decomposition. So here, this is what these part priors look like, which are basically clusters of known annotated parts from PartNet for a couple of different categories here. You see for chairs and tables and beds. And so we learn a weighted linear combination of these different kinds of parts together as a strong prior for what the actual shape can look like, and then learn to refine that estimate. So here you can see the full overview, where we have an input scan observation, and we run a state-of-the-art object detection approach. And that results in proposals for every object in the scene. And for each object, in order to be able to estimate the complete geometry of that object, we first predict this intermediary representation of that, the part structure of that particular object. So in this case, these chairs are being represented by the semantic labels of the individual parts in the chair. And each part is then being decoded into the geometry of that part based on a linear combination of these priors, which are then being refined with 3D convolutions. And so this is basically producing an estimate of the complete geometry of these objects decomposed into the individual parts. So this is also a visual comparison to prior approaches like point group and StructureNet that can perform state-of-the-art part segmentation on objects, where we can actually estimate jointly this kind of part structure, which helps a lot with generating the complete structure of the object from these incomplete observations, as well as the fine-grained geometric structures here. And this can also be seen in terms of the geometric evaluation here. This is for basically this semantic part completion task, where we're trying to generate basically the part decompositions of complete geometry of these objects. And so this gives us a nice kind of understanding of the objects in a scene and their complete geometry from these RGBD scans. But more commonly these days, a lot of people are, taking photos and videos with cell phones, but not necessarily scan observations. So can we actually do the same kind of thing from a 2D image observation, as opposed to having this depth-based observation that we want to be able to generate the 3D from? So can we estimate the 3D from an image, which also people are quite good at doing? When they see an image, they can have a fairly accurate estimate of the geometric structures of the objects in that image. And so this is something that we are looking at from the perspective of a retrieval problem. So if we have all of these objects detected in an image, can we find a similar CAD model that represents the geometry of that object, such that we can align and pose it to that particular image and have it represent the geometric structure of all of the objects. So here we have an input image that's being having the 2D instance segmentation, which state-of-the-art methods are quite good at this particular kind of task, but they give you just that 2D estimate and not necessarily the geometric structures. So then from the 2D mask of the segmentation, we want to be able to embed it in a joint embedding space along with CAD models, so that we can actually perform retrieval when these kinds of image observations and rendered CAD models, despite their fairly different domains that they come from, the objects that are structurally and semantically similar should lie close together in this embedding space, where we can then do a nearest neighbor retrieval in order to find the right object, and then we can predict also its pose with respect to the image. So this is being, this space, this shape embedding space, is being constructed with a contrastive learning approach in order to establish that basically objects that are close together should stay together in this space, despite the fairly dramatic domain difference of an RGB observation as opposed to a rendered CAD model. And then we can regress the pose parameters of the object in the pose of the image. So this actually works fairly well in terms of representing object geometry. So we can evaluate this on the Pix3D dataset, which has very accurate CAD model to image associations, where you can get close to perfect matches in terms of CAD model geometry with the image observations. And this retrieval-based approach also allows us to always be able to get a valid kind of shape geometry, because it's been hand modeled by somebody in order to place it into the database. And so here you can see what this looks like visually in terms of the objects that are retrieved and posed with respect to the image. And the nice thing about this particular approach is also that we don't necessarily, if we manage to acquire basically more CAD models for the retrieval, we don't necessarily need to retrain. We can just embed them into the space, and if they're actually better representative of new scene objects, we can actually get better reconstruction performance from simply embedding more objects into the space. So here we can also apply this to more challenging kind of real world scenarios where you have lots of objects arranged in these kinds of situations, and still end up with a nice kind of estimate of the geometric structures of all of these objects actually in the scene. So this is just, I think, a very exciting start towards commodity content creation, because we definitely still have a lot of steps forward that need to be addressed. before people can start actually capturing really, compelling content, perhaps on their cell phones, of real world environments. And so some of the interesting, challenging problems I think that are here are in terms of capturing colors and textures, because of course this is very important for sort of the visual experience of captured content, and this is still a very challenging problem to get basically the geometry as well as color appearance of objects and scenes in a realistic fashion. And then finally, moving from part segmentation and classification to really understanding dynamics and interactions and what kind of actions can be taken with the objects in a particular scene. How can people themselves actually interact with the objects and their parts? That's definitely what would be required to really move the environments to a scenario like a virtual video game, where we can then actually move all of the objects around and have virtual avatars and characters be able to move around in these scenes. So with that, I think there's a lot of cool things that are still to be done here. And I'd like to conclude and thank my students, particularly Alexei, whose work on the part-based understanding, as well as collaborators on these works. So I'm happy to take questions now too.
Thank you so much, Angie, for the talk. Really cool work. A reminder to the audience to post questions using the YouTube chat feature, and I'll get things going from my end while people think of any questions. It was really cool to see the work on part priors, Angie. Do you think that approach could actually be kind of extended up a level, where we kind of start to treat areas of rooms or entire rooms as parts which have priors in the context of an entire house, considering things like wall and door connections, placement of windows, and so forth? Do you see any benefit to this approach, at a higher level?
Yeah, I think what it would be really nice is to be able to and learn these kinds of, like structural priors in terms of base primitives that we might want to be able to interact with. So like that's object parts, but then also individual objects themselves might be well characterized by a couple of different template types of that particular object that can then be specified to the actual observed instance and the geometry that's being seen. So I think that would be pretty nice, and maybe an interesting way to sort of more efficiently use the training data that we actually have available to us, rather than fully baking everything into learned weights of deep neural networks that might also help us actually get more of an intuitive understanding of what's actually being learned in this kind of generative process as well.
Yeah, that makes a lot of sense. The other thing that I found really cool was this in the earlier part of your presentation, the idea of self-supervision by removing some information, right, for data where you have it, and then using that to predict missing parts of the data. And so I was wondering there, the work that you described was for the static scene setting, right? I was wondering, would it be interesting to consider how to extend this approach to the dynamic setting, right? What would self-supervision, this kind of idea look like in a dynamic scene setting?
It's a good question. Dynamics is an interesting challenge in a lot of scenarios. I mean, I think what I think is pretty nice is being able to try to construct these reconstruction tasks to be able to learn more kind of base primitive features in terms of shared geometric kind of parts of scenes. And in the dynamic scenario, there's also, I think, a lot of work that's pretty interesting in terms of these kinds of cycle consistencies, since at least for one deforming shape, you know that it should maintain the same kind of geometric identity. throughout the deformations. And so maybe we can be able to formulate self-supervision more in terms of always being able to preserve these kinds of geometric volume, being able to map locations one-to-one, since we know approximately these kinds of deformations. It's, I think, an interesting question at some point, though, with dynamics, how much physics knowledge to actually try to inject into these kinds of formulations, because ideally, I think a lot of the deformations that you'd like to learn are in fact actually based in sort of real-world physics. And that actually controls a lot of the kinematics and constraints and stuff of deformations, which would be nice if we can also insert this actually in as part of the process. And maybe there's something to be said, which is getting a little bit further away from the original question about still being able to learn geometric part correspondences, where part here is being used kind of ambiguously as just similar things geometrically, that might be able to be applied towards dynamic correspondences as well, since usually things that are dynamically deforming are actually not, they're still moving locally rigidly. So there might be something to be said about also learning some of this information from static environments as well.
Got it, got it. So there's a question from the audience. This is a question from Katayun, who asks, do you think it will be possible to categorize the scanned objects based on their material and use that information to help out with the set of problems that you described?
Yeah, I mean, I think this is a pretty natural approach towards kind of assigning textures to objects in a scene. So being able to sort of estimate and maybe use like this part knowledge, since often I think objects are actually being constructed with different materials on different parts, like the arms of a chair are usually maybe a different kind of material setting than the seat or the back of a chair. So that can potentially give you a very strong prior in terms of what the material will look like. I think there's already a few works along this line. What would be really nice would be to then, because I think like many retrieval-based and dictionary-based approaches, including the ones that I've also talked about, the main kind of limitation there is always the ability to actually represent all possible objects, or in this case, materials and textures with the database of knowledge that's being used. So maybe starting from something like a material classification and then still being able to refine and synthesize, especially if you have an actual real world image observation. A material classification or material retrieval probably is not going to look exactly like the actual image being observed. So then being able to refine and synthesize that to actually match this particular image would be really nice to being able to actually capture the appearance characteristics.
Yeah, that makes sense. So we're pretty much out of time, unfortunately. Once again, thank you so much, Angie, for the great talk and for taking the time to join us here at Graphics Interface 2021. Thank you so much. A virtual applause, I'm sure, from the audience as well. And
thanks for inviting me. It was a pleasure.
Yeah. All right. So we will be taking a short 10-minute break, and then we will be resuming with the next session, which will be an early career research award talk coming up shortly in about 10 minutes. So see you all very soon.
Hi, everyone. We're very excited to present I'm very excited to present the next speaker. He is one of the 2 inaugural winners of our new award. So the CHCCS Graphics Interface Award for Early Career Researchers. So I'd like to just talk to you about this award for a minute. It is meant to recognize, support, and encourage outstanding early career faculty members in the fields related to Graphics Interface Conference. So that covers all aspects of graphics, HCI, and visualization. The award is meant to be given annually to up to 2 individuals and presented at the conference. And we had many great applications this year, which was fantastic for our first instance. And so one of our 2 winners is David Levin, who is a Canada Research Chair in Simulation-Driven Graphics and Fabrication and an assistant professor at the University of Toronto. When we looked at his application, it was obvious that he was a leader in graphics research, sustained a record of high quality, high impact research on the topics that are core to computer graphics, specifically numerical simulation for fabrication and animation. And the value of his work was clear from the adoption of his techniques in real world films and game applications. He exemplifies the goal and missions of GI. So it's really fantastic that he gets to present his research to all of you today. David, the floor is yours.
Great, thanks, Audrey. Thanks for that great introduction. Hopefully everyone can hear me and see me. So I really couldn't be more pleased to be invited to talk at Graphics Interface.
Apologies to interject. We see the presenter view on the screen share.
Oh no, my notes, my precious, precious notes. Now I'll have to come up with a whole bunch of new jokes. Is that showing the slides now?
Yes, now it's perfect.
Perfect. Okay, I'll skip that part. So yeah, I mean, despite the fact that I had to write it down, I really am thrilled to be here at Graphics Interface 2021. And it's a huge honor to be awarded one of these inaugural Early Career Research Awards by the CHCCS. And I just really love getting to talk about 2 of my favorite things, which are physics and computer graphics. But before I do that, I want to start by thanking all my amazing friends and colleagues and collaborators, students, for getting me here to this point in apparently what is still my earlier career. At 41, I'm probably the oldest early career researcher ever. So there's really like a lot of people on this list. And you know, I'm very cognizant of the fact that I'm a product of my environment, and I've been very lucky to always find myself in environments that are supportive and inspiring. So this has really been the case for all stages of my career so far. So from my time working at Forward Imaging, which was a medical imaging startup in London, Ontario, to my master's in biophysics at Western University, all the way through to my PhD at UBC and my postdoc at MIT. And I want to just pause here and say like a huge thank you to Dinesh Pai, who was and continues to be just a phenomenal teacher and mentor. You know, it was Dinesh's willingness to take a risk on me as a PhD student to let me come switch fields to graphics, and his guidance over the course of my degree really like put me on the road to much of the success that I've enjoyed ever since. And of course, none of what I'm going to talk about today would be possible without my amazing graduate students. These are the students that I directly supervise, but really everyone back at the DGEP deserves a little bit of recognition. If I could break up the award Mean Girls style and give it to each and every one of you, I would. And finally, I want to thank my family, including my super talented partner, Maria Shagrina, my daughter, Yana, and our 2 cats, Seema and Tanya. Maria won the Alan Fournier Prize this year. So if you missed her talk, you should definitely go and check it out on the GI YouTube channel. But before you run off and do that, hopefully you can stick around for a little bit, because you know, I want to tell you a story. And this story starts way, way back in 2006. Just to set the scene, the critical darling, the Fast and Furious Tokyo Drift, raced to number 41 at the box office. And I was working on building real-time surgical simulations for prostate brachytherapy. And if you don't know what that is, definitely don't look it up on the internet right now. More or less, this involves doing 2D simulations of poking people with needles. And the algorithm that we had come up with was this funny thing that did mass spring simulation because it was very fast. And then it kind of iteratively visited each spring and applied some constraints to limit their deformation. It worked pretty well, but it was sort of chock full of hyperparameters, which I, as the student, had to manually tune. And more out of frustration than anything, I wrote this in the paper, that a physically based model with meaningful material parameters could have saved me all of this time. And while I was trying to figure out how to make this more physically based, I stumbled across this paper by Doug James, Dinesh's former PhD student, now Stanford University professor. And this kind of blew my mind. This was an amazing real-time physics simulation. It wasn't coming out of numerical methods or the engineering community, but from computer graphics. So I saw this and I thought, look, this is where I need to be. This is what I need to do. And I applied to work with Dinesh, and then the rest is basically history. And so at the University of British Columbia, I got introduced to the field that essentially has defined my career up to this point, which is physics-based animation. And when I arrived, I was a neophyte. And so in order to try and catch up a bit, I went looking through old literature. And that led me to this paper from 1987. This paper by Dimitri Terzopoulos really introduces physics-based animation to the field of computer graphics. And it looks pretty good, actually. They simulate cloth, they simulate volumetric objects, they do collisions using penalties. It's actually a really, really impressive paper. And if you're at all interested, you should really go in and read it, because it sets the stage for still what is like a lot of the modern techniques that we use in the field. But what caught my eye most was in the text. Terzopoulos points out that active models, their name for dynamic physics-driven models, could potentially produce realistic, diverse interactions simply by implementing the rules of physics. In other words, we could be free from hand coding or hand animating every possible interaction between objects in a virtual world. The correct behavior would just emerge from the physics. And for me, this resonated. I had been in the trenches hand tuning parameters to try and match a real world result. And it was awful. The power of physics simulation and animation was that this complex behavior could arise naturally from, relatively simple rules. And over the years, I think it's safe to say that these kind of ideas have permeated most subdisciplines of computer graphics. So this isn't an exhaustive list. Please don't get upset if your favorite area of graphics isn't on here. But if we look at some of the major sub areas of the field, things like geometry processing, rendering, fabrication, and animation, we see that large subsets of them are using ideas from computational physics. Physics-based animation, including fluids, physics-based character animation, and the control of those characters is sort of the obvious adopter of these ideas, but I'm always chuffed to see physics interpretations of algorithms in geometry processing, fabrication, and rendering. And I kind of believe that these ideas from physics disseminate for the reasons that they were originally attractive in animation, that complex behavior can emerge from simple rules. It's so prevalent now that I sort of think of large parts of graphics as a kind of computational physics, but one with very different motivation and vision than standard fields that dabble in this kind of thing. Graphics and the use of physics within graphics is special. And what makes it special is that whether we are talking about geometry, rendering, animation, simulation, or fabrication, we set this incredibly high bar in terms of complexity, fidelity, and performance. So graphics is almost like an extreme version of computational physics. And this is why I think you get so much incredible work coming out of the field. It's in reaching for this high bar we set for ourselves that we discover all sorts of magnificent bits of math, computer science, and really much, much more. And for someone who really loves to look at things through a physics lens, all of this is really exciting. But lately I find myself looking back to that original Terzopoulos paper and asking how we're doing and living up to those original goals. And at least in my sort of little animation simulation corner of the world, this kind of visual computational mechanics community I'm part of, I think the answer is that, things could be better. And I submit that rather than make things easier, as we intended when we adopted this approach, we've kind of made them difficult, but in a different way. So I'm going to give you, my favorite example of this now. So in this example, here I am, I'm pressing down on a simulated shape with a force F. The shape is an elastic solid, and I've gone to Wikipedia and I've looked up the appropriate physical parameters to make this simulated object behave like it's made of a soft plastic. The simulated result kind of looks reasonable. The object is deflecting, and most of the deformation is happening in the thin part of the geometry. There's really only one problem here. It's a problem you can't see, but I've used a very, very high resolution simulation mesh, and that's very slow. And so, okay, fine, no problem. I'll do the whole thing again. I'll make the mesh coarser. It's going to be much faster. And if I do that, if I keep everything the same except the mesh resolution, the result of the simulation will be quite different. Now, keep in mind that the simulated material is the same, the applied force is the same, everything is the same except the number of little cubes that make up this mesh. Now, even if you're an expert in simulation, this is not what you'd expect from a class of algorithms that is aiming for sort of simplicity and to get things right in an emergent sense simply by correctly implementing the laws of physics. And actually, things get a lot worse once you start to consider contact between objects. So here we have a thin sheet of cloth sliding over the edge of a box. And if we represent this cloth using an unstructured mesh, we get these kind of ugly artifacts because our fake cloth can't bend where it needs to. And if we align the triangle mesh with the edge of the box, the fold looks great, but actually the cloth gets stuck since it can't actually slide around the edge. So, once again, this unexpected behavior occurs. And this is really weird because if you did all this in real life, the cloth would slide along the edge perfectly and it would look fantastic. And this really all ignores the fact that just to get to the point of making these mistakes, there's still the problem of generating the geometry in the first place. Even with really stellar and robust solutions like Tetwild, which I really want to stress is a miracle worker in terms of building volumetric tetrahedral meshes, we run into problems. So, if we aren't careful, we're going to get these unexpected failures. This kind of blobby character was modeled by my grad student, Ty. It's made out of NURBS, built in Autodesk Fusion 360, and we exported the surface triangulation, and we can generate a tetrahedral mesh because Tetwild is awesome. But, certain features like the collar have been irrevocably perturbed. And, if you were a designer, you might not expect this to happen. So what's the solution? What is the current solution to all of these issues? Well, the best thing we really have to solve a lot of these problems is just to let artists and graduate students kind of engage in a WWE style wrestling match with all possible parameters and variations of algorithms for these problems. And we do this in order to produce really beautiful results. And don't get me wrong, this works. We see the evidence of this in countless movies, video games, and yes, even graphics interface paper submissions. But all this is time consuming. And that's part of the reason you see the same meshes and tests over and over again. We sort of overfit the problems where we can assume this is possible because we want to amortize content creation effort. But arguably now, we actually need more expertise to rein in physics simulation since the effective parameters is often indirect. And so the game just sort of changed to focusing in on increasingly narrow use cases. And it moved away from the larger goal, which was to leverage a physics-based approach to generate diverse and emergent behavior quickly and easily. To be sure, there is lots of work being done by myself and others to try and remedy some of these issues. And so, what I'd like to do now is talk a little bit about some of that. So for instance, there are now a myriad of what we call numerical coarsening techniques to mitigate things like simulation mesh dependency. And these, when used in the right scenarios, can be extremely effective. They're so good, in fact, that you can use very coarse simulations to get results that not only look good, but match real world outcomes in particularly challenging scenarios. So these 3D printed jumping mechanisms were in fact optimally designed using a coarsened simulation that is orders of magnitude faster than what we would have required to get the same accuracy without coarsening. Now, if you've seen me give a talk before, you've definitely seen this video because I just love showing it. The agreement between the simulation and the fabricated result is unbelievably good. It's every time I see it, I still can't believe it works so well. As an aside, this paper was actually rejected from the Transactions on Graphics before it was narrowly accepted to SIGGRAPH. So there's a bit of a lesson buried in all of this about stubbornly sticking with ideas that you have faith in, even if maybe others don't at first. And, you know, we've since refined the technique a little bit to work on a wider variety of mesh types in geometry. Here, the fine tetrahedral simulation mesh is an order of magnitude slower than our eigenfit method, but you can see that the results are almost identical. And my former master student, Honglin Chen, had another great follow-up to all of this with Alec Jacobson and Derek Liu. That was much more general than our previous approaches, but focused on sort of geometry processing applications. The nice thing about this paper is that it had some notion of finding an optimal solution to this coarsening problem. All this work taken together is in service of mitigating the effect of mesh resolution as a hidden parameter and making the output of a physics simulation solely dependent on its physical parameters. This is not only great for someone like me who hates manually hunting around for parameter values, but I think broadens the use cases where physics-based animation can be applied. Interestingly, like numerical coarsening, our collision problem is also sort of a form of discretization failure. We've just learned that if you naively coarsen the simulation mesh to get more performance, you introduce an error in the material parameters. Well, it turns out that if you introduce this type of collision error, but if we introduce just the right degrees of freedom back into the system, these errors vanish. In our case, it turns out that the right degrees of freedom are the texture coordinates of each vertex. So, you know, if you change the texture coordinates on a triangle mesh, you can make an image drift or move along on the mesh. And by letting the physics simulator itself control the drift and combine it with a bit of remeshing, you know, we can solve this problem. And we get both this beautiful sharp crease and smooth sliding around the edges. We can even do previously impossible constraints like this sliding pup tent. So here, the string of the pup tent is represented by just a single line. And, you know, this example will immediately break on a standard cloth simulator. And we can even, you know, poke this cloth with a bunch of spikes for some reason, and you can see it's happily sliding along unperturbed. We also capture some sort of nice detail like these buckling artifacts that make everything look a little bit more realistic. And this kind of comes for free just by fixing the discretization problem. However, even with fixes like these, we still have the problem of generating simulation geometry from some input representation. There are a couple of important questions on this front. One, you know, what sort of input geometry should we be trying to convert? And two, what should our output format be? The most common form of input geometry in my field, at least, is a triangle mesh. So, you know, we want to be able to convert triangle meshes to volumetric representations, but it doesn't necessarily have to be a tetrahedral mesh like the one pictured above. One potential alternative is what we call a cut cell mesh. And here we generate volumetric cells by clipping the input surface against a volumetric hexahedral grid. And if we're really careful about how we do this, we can robustly generate these cut cells for a wide variety of input geometries. So here's an example of using our robust cut cell generator called Mandolin on a subset of the Thingy 10K geometry dataset. And in the corresponding paper, we show it works on the whole dataset, as well as on meshes that are non-manifold, open, and self-intersecting. there's still a price to pay, and that the output of the volumetric cells are much more complicated than just tetrahedra. And we're still really working on the accompanying simulation technology. But this is this is a preliminary airflow simulation run on a particularly ugly Jeep mesh. And I'll just say, watch this space, as there's more coming on this front that I'm very excited about. However, things like Mandolin are only going to get you so far. What if you want to deal with models that aren't represented by triangle meshes? Something like this wheel, which has been designed as a NURBS model. Well, an alternative is to abandon explicit volumetric meshes altogether and use a mesh-free method. This method, which we call the shape matching element method, skips the volumetric mesh generation step entirely. And it requires only the input surface description, curved or not, to work, which makes it really, really fast to design things and then simulate it. So it's a lot of fun to play with. So this is really, really new work, and you'll be able to learn more about this at SIGGRAPH in the summer. So we have all these individual solutions to various issues with simulation, and they're all geared towards making things as simple and parameter-free as possible to let the physics shine through in the way it was originally intended. But the truth is, I'm still not sure how to put them all together. To be honest, I don't even know if all these puzzle pieces are even from the same box. What I really want for computational mechanics is kind of a general function that generates physically simulated output. It should consume arbitrary geometries and material descriptions and produce simulations. And that's a really big ask. But I have some confidence that it's possible. In areas like geometry processing, we're seeing good progress in building algorithms that provide obfuscated geometry queries. So for instance, winding numbers allow you to do inside-outside tests robustly on almost any input geometry format. For algorithms that require only this test, they don't need to care what input a user is providing. And that's definitely a step in the right direction. But I feel like in computational mechanics, we don't quite know where to go next. And we're just exploring. And the thing about exploring all this stuff is that it's slow. And that's partly why we take relatively small steps. Each experiment means building a simulation, and that's a difficult manual process. That's because there are not just computer science challenges to solve, but mathematical challenges and even experimental challenges. So the more I think about this, the more I feel like we have to turn this into this. So how do we do that? Well, the first thing to consider is geometry. Whether it's thin sheets, volumetric solids, fluids, triangles, NURBS surfaces, or particles, in simulation, the algorithm you use is heavily dependent on the form of your geometry. And this is a bit like, still having to program an assembly code. Ideally, we should be abstracting all of this away. So I'm pretty excited about meshless methods coupled with efficient sign distance representations to kind of completely hide all of this stuff from both researchers and users of physics simulations. For what it's worth, this combination of tools is starting to see some use in video games in order to simulate pretty large scale and pretty degenerate geometry, and the results are really promising. There are still a lot of open questions about how exactly to do all this stuff for highly deforming geometries with complicated material properties, but it feels like it's within reach. However, even if we solve the geometry problem, there are still even basic scientific questions about how we model complex materials. One of the reasons you tend to see the same sort of simulations over and over again in computer graphics papers is that we're still learning how to deal with all the material complexity inherent in the real world. There have been some previous attempts to automate this sort of
the UBC active measurement facility.
And then directly simulate results. And this is only going to get more important as we seek to broaden the range of output of physics-based methods. So, what's shown here is Dinesh Pai's Acme robot, which could automatically poke and prod an object to generate a simple virtual facsimile. And this is really like seeing the first camera that captures a truly physical object rather than just a 2D image or 3D scan. And just as computational photography has benefited from the miniaturization and proliferation of cameras for acquiring photographic data, I think we need to follow a similar path, but concentrate on capturing more of reality than just photons. And finally, I think we have a massive systems problem in the field. Unlike other fields like machine learning or even geometry processing, simulation doesn't have a widely accepted framework for easing the implementation of performant code. 33 years after the first paper in the field, we are still basically rolling our own stuff for each and every project. And you only need to look at the success of deep learning fueled by tools like TensorFlow and PyTorch to see how useful a community-wide engineering effort can be. So there's some hope. There are custom languages like TaiChi, but there are still some real questions about how to get necessary technical features like automatic differentiation to play really nicely with the type of sparse data structures we typically encounter in computational mechanics. So full disclosure, I really started thinking about this after my daughter was born. I had a significant reduction in the amount of time I had for kind of esoteric C++ or GPU hacking. So this is really like a very self-serving goal, but I still feel it's the case of what's good for the goose is good for the gander. And so these are the problems I think are important to solve and the things that I think we need to build to solve them. And for me, this is all in service of kind of a great quest. And that quest is really to understand how the world works. And mechanics, especially as it's done in computer graphics, is a fun, satisfying, and useful lens through which to do that. But we have to be forever on guard of getting lost in the details. And here, I'm as guilty as anyone. As fun, useful, and intellectually satisfying as all this has been, the goal was never just to understand how some bunnies or penguins bounce down the stairs. The goal was to build and comprehend a world, and the world is much bigger and much more complex than any of that. So I just want to thank you all again for inviting me to speak, and I'm happy to take any questions now.
Okay. Thank you so much, David, for the great presentation. Is there any question from the audience on YouTube that you want to ask David? Or from people in Zoom? Yeah, so David, you mentioned that you have you can actually work with different types of inputs. Like it can be nerves or meshes or something like that. And then you mentioned that for neural networks, we actually have made a lot of contribution. It's working very well, but here in simulation, maybe you are not working as well. So my question is for neural networks, for example, we have some agreement on the input. So the input should be a tensor, right? What is the right input for physics simulation?
Well, I think the right input is defined, by its interface. So in general, when you want to understand the physical properties of an object, the object itself is really a container. It's a blob of Euclidean space, and that blob has to be able to answer some questions for you. It needs to let you know if a point is inside or outside of the blob. It needs to let you know what are the material properties at that point in the blob. And so, in some sense, I don't really care how those query functions are implemented. I just want the interface. And I think, once we start thinking of things in terms of just having this interface, it becomes a lot cleaner. Essentially, this is like standard. This is like object-oriented programming, but for real life physical objects.
Yeah, pretty cool. So maybe the last question, because we need to go for the next presenter. So you probably know that Alec Jacobson is actually working to maybe use the latent vectors to represent the shapes, right? Only latent vectors that you can have a very compressed version of your model or shape. Do you think that the physics-based simulations that you have can be transferable to those types of representations?
So for us, in physics simulation and mechanics, things get very interesting when you have to consider deformation, because in the sort of things that happen on this side of the fence, it's not just enough to represent the object in a single state. We have to represent it in multiple states, right? We have to represent its change in shape over time. And this can get really complicated. Like if you consider, a fluid, like if you go to Christopher Batty's webpage and you watch some of his amazing videos, you can start with a bunny and it can turn into something completely different. There's shape change, there's topology change. And so it's unclear, even if there is a compressed representation that can handle that with, sufficient expressivity, right? I think it's a really wonderful idea, but it's this idea that there's no free lunch, right? If you compress your shape space, well, you better hope that everything that you've excluded is not actually needed to represent the proper behavior of the object. And it's, I think it's going to be really fun to see, how far we can push these things, where that all starts to break down.
Awesome. Thank you so much for the great presentation. And I'm going to give you applause, and you received a lot of virtual applause on YouTube as well.
Great. Thank you. It was wonderful to be here. Thank you.
Yeah, thanks so much. I think Audrey, the stage is yours.
Hi, thank you for the talk. So we are very excited to present to you the second winner of this award in no particular order. This is the inaugural Graphics Interface Award for Early Career Researchers, for those of us who are just joining. And I'm very happy to present it to Rita Orji. She is a Canada Research Chair in Persuasive Technologies and an associate professor at Dalhousie University. And Rita has established herself as a world leader in HCI and persuasive technology research. Her exceptional publication record demonstrates substantial contributions to technologies for health, personalization, and behavior change. In addition to being a Canada Research Chair, recognitions for Rita's contributions include Best Paper Awards, numerous keynotes talks, and panel appearances, as well as being named one of the top 150 Canadian women in STEM. So very happy to have her talk about her research today. Take it away, Rita.
Hi, everyone. It's my voice coming through? Okay.
Yes.
Hello, everyone. Thank you all for being here. I am very excited and honored to receive this award. I don't know how I feel. I really feel so honored to be recognized by my colleagues with this award. I don't know, there are so many people that have contributed towards my journey of what I have become and what I would be. And I cannot really thank everyone, but I want to start by saying thank you to my family who believed in me when it was not a norm. And I said I'm gonna push ahead, and everybody was behind me. And there's people that have mentored me over the years. My supervisors from my PhD, Regan and Julita, and then to my colleagues and collaborators who have stood beside me and mentored me to be what I am today. I don't want to forget my students who are so amazing that none of this wouldn't have been possible without them. When I receive an award like this, what comes to mind for me is 2010, when I was heading to Canada. This is what kind of 10 years x-ray of me and the journey so far. I like looking back at that because most times it's easy to forget what has come over the years. The 2010 was exactly me at Venice Airport, Italy, when I was heading to Canada for my grad school. I mean, that was my first time. I didn't know anybody in Canada. It was just totally a journey of faith. And the one thing stood out here is that, I was coming to Canada without even much knowledge of what the research is all about and what I'm going to be working on. And I didn't have any publication at this time. So it was all about, yeah, we're going to do it. I just have that conviction and that determination that things are going to work out. And 2012 and 14 was me at University of Saskatchewan doing my PhD. And then 2017 was doing my postdoc and searching for faculty position at University of Waterloo. And 2019 and 20, it's me at Dalhousie University. And I don't want to finish this without thanking my colleagues at Dalhousie University, and a special shout out to Derek, who's been a very senior colleague and mentor, and then been so supportive all the while. So with this, I'm going to go on to try to show you a bit of an history of the kind of research I am excited about and the kind of thing I do. I remember coming to start my PhD. I mean, when I met my supervisors, the only thing I said is that I'm not exactly sure what I'm going to work on. I only had a course about HCI during my master's. I felt like, oh, this looks like the kind of thing I want to work on, you know. And when I came, I kind of told them, I'm not sure what I want to work on, but I'm sure that whatever that would be, it involves human, you know. And then I sat for the first few months of my PhD trying to unravel what that would be, and eventually saw the field I'm working on today, the persuasive technology field. And after reading a couple of work in that field, it felt like exactly me, the type of thing that could sustain my interest. So that's how I ventured into that field. And today it's a history. I mean, I didn't know most people that have worked on it then, but I just know that it's resonates with the kind of thing that could actually keep me and sustain my interest as a researcher. So at the Persuasive Computing Lab within the Dalhousie HCI group, I tried to investigate, and me and my group investigate how to design interactive systems, such as mobile application, games, and web application, and all that, to support and motivate people for actions and causes that are beneficial to them and their communities. I tend to see my research in 3 different places. I see that one of them is where we call the personalization models. Here, I develop models for personalizing technologies to various user types using both objective and subjective data of users' behavior, their motivation, and their system use gathered using many means, including sensors, user studies, and interaction log. And the models can be used by designers to inform the personalization of their systems to suit the user group or the user type they are designing for. The second area of interest I work on is what we call technology for underserved population. I'm very passionate about designing technology for the underserved population. That is people that usually tech designers do not think about when they are designing. So here, I'm more passionate about designing technology to solve problems among underserved population. For example, in 2019, I spent around 3 to 6 months in a very remote village in Africa, trying to work with the doctors, the nurses, and the pregnant women and all the villagers who actually have low-tech knowledge, are illiterate, most of them can neither read or write in English, probably survive another $1 a day. And they were trying to come up with a technology that could help in the area of infant and maternal health. And this was an internationally sponsored project. So that's the kind of thing, it gives me joy trying to work with these people to see how technology can accommodate this type of a group that are usually not thought about. Because I mean, usually when you think about technology, think about people that have smartphones, people that really can read and write, and people that are tech savvy. These are not part of the groups that I looked at here. So the third part of where I see my research is in technology for health and wellness. Here we design and evaluate various applications using the user-centered approach and data-driven approach to promote health and wellness. So my presentation today is mostly going to come from this third category. And I'm going to basically try to show you the various dimensions of what we do. But before, for the benefit of people who probably don't know what persuasive technology is, let me give you a bit of background. I'm sure that many of us here have used things, various applications to try to change our behavior or keep us on track. Things like activity trackers, calorie counters. So these are the type of thing we can actually call persuasive technology. So persuasive technologies are designed for the primary purpose of motivating people to adopt behaviors that are beneficial to them and their communities using various techniques. And the studies have actually shown that this type of technology can be effective. They find application in various domains, including safety and security, environmental sustainability, volunteerism and social action, and of course in health and wellness. And in the area of health and wellness, persuasive technology have been applied in managing addictive behaviors and discouraging risky behaviors, achieving personal wellness, managing disease, and making healthy choices, such as healthy eating and physical activity. So in the Persuasive Computing Lab, we try to investigate various ways that persuasive systems can be designed to increase their effectiveness. And one way we've done that is to investigate how these technologies can be personalized or tailored to individual users or user type. Let me give you an example. These two quotes are from two participants. The quotes we obtained while we were evaluating a persuasive application for discouraging risky alcohol drinking behavior. And the quote highlights the importance of personalizing technologies for health and wellness. And according to participant 3, and I quote, "The app allows me to see the short and long-term consequences of heavy drinking, and it is educational and motivates me to change." However, according to participant number 27, and I quote, "The application shows real life consequences. It is frightening and make me feel crappy and scared. I would quit using it." So with this in mind, we tend to look at the overall hypothesis that one size does not fit all, that tailoring persuasive systems can actually increase their effectiveness. And we investigate the various ways that these applications can be tailored. And one of the applications I would show you today is how we have tried to tailor just-in-time applications to health condition. A typical recent application in that domain that we worked on is an application called Prosit. Prosit was developed in collaboration with a psychiatrist called Sandra Mayer at Dalhousie. And it is an application that was initially developed to help promote mental health and then monitor different things that impact people's mental health, and also give clinicians insight into how their patients are doing. So the mobile sensing app passively record daily life routine of people, thus making them aware of maladaptive behaviors that needs adjustment. It helps patients to get involved even in self-management. So the main motivation here is that psychiatrists often look for a way to gather data for the clinicians to monitor the clinical outcome of their patient. That is how their patients are doing. Assuming someone is having a mental health issue and has been coming to the hospital, the clinician wants to be able to monitor them even without having them come to the clinic all the time. So we hope also that the data can also be used to predict onset of mental health issues and facilitate timely intervention and help the patient to get timely help. And above all, we want to use this app to get patients involved in the self-management of their mental health, so that it's not only that what the clinician is telling them, they can also have input, be able to visualize their various behaviors that might have impact either positively or negatively in their mental health. So on a very more specific note, we use various inbuilt mobile sensors. The app is able to track over 20 different data points about people's behavior, such as their movement, the sleep duration, the quality, the social interaction, and the emotion. We also track their location using things like GPS, the type of calls they make, that's whether they received or they are making the call, the SMS and the length of the SMS they send, nearness to other people, other applications users are using, such as are they using social media and other things. We also capture their emotion via speech sample. So what is interesting here is that we already designed this app and is being used by some people already tested on. at the time before COVID came. So when COVID came and interrupted us, they come this social distancing and social isolation. We repurposed the app to study the impact of social distancing and the counterbalancing behavior on mental health. Preliminary studies apparently showed that some of the precautionary measures that we use during the COVID, such as social distancing, have impact on mental health, such as anxiety, depression, abuse, and self-harm. In addition, some people with mental health disorder might over-engage in social distancing measure and completely self-isolate without actually trying to connect with people either online or so to compensate for the lack of physical connection. So our main hypothesis is actually try to see if mobile sensing data will predict compliance with social distancing. We want to see the various ways that people are using to cope, the various compensatory strategies that people are using to make up for lack of physical contact and physical connection by monitoring people's social interaction, other social interaction via their contact, calls, messages, and app logs. We also want to be able to determine whether social distancing and the counterbalancing measure that people are using to cope can actually be able to predict incidents of mental health crisis. So these are some of the sensors that we collected in detail. Like I said, we have over 20-something sensors that we got in the app. This project is done by a team. So we have the machine learning people who are actually trying to, at the moment, the project is being used by over 1,000 people in the clinical trial. The app is being used by over 1,000 people in the clinical trial, and it made headline in over 40 different countries for its use in social isolation and the COVID-related thing. And we are currently still collecting the data. But this is why the visualization of daily calls, text messages, average use of the phone would look like. And this is how you visualize the location and the movement data. This is also how we visualize the nearby devices and record speech sample of the people for their emotion dictation. So the initial pilot study, the paper will be out in the next week, and you'll have one of the papers already published, so you can check it out. The initial pilot data shows that the app is effective. We observe that people with more severe depression are less mobile. That is meaning that they are more sedentary. However, in contrast, people with high anxiety symptoms are associated with high mobility. People with high depression symptoms have very few social interaction, such as a very few number of outgoing calls. Likewise, those with high anxiety also recorded fewer number of outgoing calls. We also saw from the preliminary data that poorer sleep quality was correlated with high depression score. Remember, people always have this, are always skeptical about anytime you talk about sensing data, tracking stuff like that, things about privacy, people gonna use it come to mind. We actually investigated whether that is applicable in our case, and we saw that majority of the participants perceived that mobile sensing app are either very or extremely helpful in managing mental health, especially during the COVID-19. And people with history of mental health disorder found that mobile sensing app to be helpful compared with those who do not have history of mental disorder. The perceived helpfulness of the mobile sensing app was also higher among people who experienced a stronger health impact of COVID-19. And those who are more knowledgeable about technology actually found the app to be more useful. So with respect to privacy and app acceptance and people's comfortability with using the app, we saw that like for app features, perceived control, trust in people behind the app that's people who developed it and people who are using it, who are actually recommending it, had the most relevant impact on how comfortable people are with using mobile sensing app and their intention to accept app permissions. So people were more comfortable with sharing their data and more willing to take the risk of using the mobile sensing app if they like the features. And it is highly important for users that it is highly important for users that they can trust the people that provide access to the app to manage their data. They also want to be able to have control of how their data is used. So another way we've looked at how application can be tailored, this is a very recent work, so I'm just gonna touch it briefly, is how it can be tailored to user stage of change. You know, there's a popular theory that people move through various stages of change to be able to arrive at a desired behavior. It is not an automatic process. It undergoes through stages: pre-contemplation, contemplation, preparation, action, and maintenance. Our CHI 2021 paper actually investigated this. You can check that out. However, in this particular case, which I'm going to present, is that we designed an application which we call COVID-19 Pacman. Apparently, this application was designed by my master's student, is aimed at creating awareness about COVID-19 and then motivating people to adhere to the precautionary measures. So the game apparently simulates how COVID-19 spread, the consequences of violating the precautionary measures, such as the social distancing, not wearing masks, and the sanitizing. And we designed 2 versions of the game tailored to people at the early stage and the later stage of behavior change. So what we saw based on evaluation on 200 people is that we find that the game was effective both for people at the early stage and later stage of behavior change when they played their tailored version of the game. However, it was not as effective for those in both early stage and later stage that played the untailored version of the game. We also believe that culture is an important aspect that needs to be considered when designing persuasive application. And one of the ways that we showed that is by designing a game called STD Pong. So STD Pong was designed by one of my master's students. It is an African-centric persuasive game for discouraging risky sexual behaviors among African youths, designed by one of my master's students. And in many parts of Africa, just to give you some context, sex is still treated as something sacred and not to be talked about. It's not a popular topic, and hence people are often naive and make a lot of mistakes when they encounter situation. So in STD Pong, we targeted some of the conflicting belief about sex and sexual risky behaviors among African youths, including the use of contraceptives such as condom and the reality and seriousness of sexually transmitted disease. We tailored STD Pong to be appropriate for the African audience in many ways. For example, the game narrative, the storylines, the in-game characters, the skin tone, and the hairstyle, body shape, game environment, soundtrack, and other in-game objects apparently reflects Africanness. We iteratively developed both the game and the game objects in consultation with different stakeholders. So we modeled several sexually transmitted infections in the game, how they are transmitted, their symptoms, and how to get treated and tested, how to avoid them. For example, the scene you're looking at is the scene about scabies disease. So we apparently evaluated this game and we saw that it is effective as it's led to an increase in knowledge, attitude, intention, and self-efficacy to avoid risky sexual behavior. We went further and applied the same knowledge in developing a new game about COVID-19 that is also targeted at African called COVID-19 Dodge. And that is the most recent one that I wouldn't be able to present the result at this point. Another way we've looked at how persuasive application can be tailored is tailoring them by matching people's ability level, right? This is a persuasive application called TreeCare. It is application designed to promote physical activity. Here, physical activity is operationalized as step count here. So what happened is that in this game, a people's step count is depicted as used to decorate a tree. Is the energy level, which is the amount of step they take, is used to flourish, make their tree flourish or wither, depending on whether they are active or not. So if they are active, the tree grows leaves and flowers, but when they are not active, it dies off. So in this particular application, there are 3 modes to it. We have the starter mode where people can actually just give themselves, create a goal for themselves and say, hey, I'm gonna do 10,000 steps daily, or challenger mode or tournament mode. In the challenger mode, you can create a challenge and invite other people to compete with you and see who wins. However, in the tournament mode, you actually work in group. In your team, you work as a team and try to compete against another team. So it's not only your physical activity level that counts, but the physical activity level of other people in your team. So you want to not only be active, but also try to motivate others. This is what it looks like. But let me go straight and show you what we want to invest, what we try to do here. Like I said, matching people's ability level, how to form the best way to form a group to actually motivate each other to lead to the optimal performance is a continuous research challenge. So here, what we did is we tried to create 5 different groups. 3 of those groups consist of people that have similar activity level. For example, people in SO1, all of them are people with low activity level. SO3 and SO2 are people with moderate activity level. However, MO1 and MO2 comprises of members with dissimilar, that is mixed activity level, a combination of low, moderate, and high activity. And this is what we saw in the evaluation. We saw a significant increase in physical activity from baseline to week 1 and week 2. However, that is not all. Next, we examine users' collective performance within each group and compare it with the baseline. So as shown in that chart, there's an increase in activity level in both first and second week of intervention within the group comprising of people that have similar activity level. For example, although in SO1, we have people with low activity level, there's actually a 63% increase in activity during the first week and 20% increase in the second week compared to the baseline. On the other hand, looking at the other group that have people with mixed activity level, these are people with low activity, medium activity, and high activity mixed in the same group, we saw that there's actually a reduction in activity level for group comprising of dissimilar characteristics. So this further shows that in forming a group to motivate them to be for any behavior, matching people's ability level is an important characteristic. It might be better to think of bringing people together that are similar in terms of their ability level versus bringing people that are not similar, because that might actually lead to the motivation. Some people might not keep up with what is going on, might be demotivated by feeling like the other people are way higher than me, I cannot catch up, or the people that are high feeling that the other people are not performing as much as I would expect them. So they individually demotivate each other. So I'll be rounding up by showing what we are doing at the moment, or a recent one that actually progresses what we've done so far. So as opposed to what we have done so far, which is some of them have been on a static level, using a static personalization that assumes that people change their behavior. Once you determine people characteristics, that characteristic sticks and their motivation doesn't change over time. We actually try to see how to create some individual level and dynamic personalization that treats each user as a unique person, but at the same time, examine their current state and changing motivation and use that to reflect on whatever is being recommended to them as in terms of for behavior change. So in this particular application, I work with my collaborators from Carleton University, Dr. Ali Aliu. So what we did was actually to create a dynamic personalization model that is able to recommend an individual's preference for physical activity, uses some environmental sensors to know the weather, the time of the day, where the user is, their activities, and based on that, we are able to recommend physical activity to them. One thing that is important here, which I'm going to highlight, is that the personalization of what we call persuasion profile varies from time to time. It is not static model. This is a dynamic model that takes each person's current state into account, and based on that, make recommendation on what is important or what they think the person would actually be able to resonate with. And what did we see here? Based on 60 days long evaluation of 40 participants, we saw that people who used their personalized app became more physically active. As a result, they burned more calories, found the recommendation by the system to be more useful. They also engage more with the system, as shown by their daily conversation, than the control group. They also rated the personalization by the system to be more useful and more moderating and more engaging. So people generally find the system that uses the personalization more satisfying and preferred it, found it more useful compared to other systems. I'm going to end here, but before I do that, I would say that most of this work I've presented and some of the other ones are also being, you can find them in my profile. Some of them have been published. You can find them here. And many thanks to my collaborators that worked on some of the projects I talked about today. And my students, some of them, the pictures cannot be all contained here, but I want to acknowledge them. This wouldn't have been possible without them. And my funders as well. The take-home message from all this and what we try to do is that we try to find various ways to personalize systems. We argue that personalizing persuasive system increases their efficacy at achieving their desired objective. Any form of personalization is actually better than no personalization at all. It has consistently shown to be better to personalize system than not to. Thank you. I would welcome your questions and comments.
Thank you so much. Let's actually see if we have any question from audience. Yes, Daniel has asked, a lot of persuasive work here focuses on education and long-term change. What part does moment-to-moment decision-making play into this? And how do you think persuasive tech can help there?
Yeah, basically, persuasive tech actually do involve moment-to-moment decision-making. And apparently the last system I talked about, and the last one is about the dynamic personalization profile of the user, actually monitors the user moment-to-moment activities and decision-making, and takes that into consideration to recommend some activity level. So in that way, I do think that moment-to-moment decision-making can be captured in and used as part of what would drive decision in terms of the kind of intervention that will be administered to the user. So I do think it can be factored out, but most of the personalization profiles or models that is available right now or that I've used apparently tend to be more static. So what we are moving towards right now is a dynamic model that is able to capture that moment-to-moment decision-making, because we actually think there are so many factors that would influence what works for one, from one moment to another, including things like mood changes and other things that happen moment to moment. That's what we call the current state of the person. So if we're able to have that way of creating a dynamic model that constantly update the person's profile and use it to recommend activities or use it in recommending persuasion techniques, then that decision would be factored into the design of the persuasive system.
Thank you so much. Very nice answer. So sometimes the learning contents are pretty dry, right? So how do you make sure that if you want to make a game, that the game is still engaging and people can learn the dry content, but at the same time, they can play and enjoy the game?
Yeah, there's always that tension on trying to balance the fun aspect of the game and the serious aspect of it. The serious aspect is the aspect that has to do with the learning, right? And arguably, the main reason why people actually play game is to have fun. So because it is game, it has to be fun, but at the same time, you have to find a way to design it so that the fun element does not really cover up the learning that needs to occur. We have actually tried to do that in several ways. One of the ways you can keep the game continuously engaging, but at the same time, why people learn, is to do what we call incremental release. That's more like features, keep releasing making some changes, incremental updates of the game. More like, think of what they do in Pokemon Go, where they constantly release new features that actually make the game more attractive and engaging. And another thing we've done actually is trying to see how we can a bit separate not necessarily separate, or trying to integrate the learning as part of the fun. So as opposed to having a decoupled application where the fun aspect of the game is different from the learning that needs to occur. There are creative ways you can create the game so that what people need to learn in game actually is part of what makes the game fun. So in this way, it's not like two different things. They are one thing and the other. But yeah, I do agree with you that there's always that tension of trying to balance the learning and then the fun aspect of the game. But with a good design, the learning becomes some part of the fun that become part of the things that makes the game fun. But it involves some creativity and some iteration, trying to make sure that you arrive at that instead of designing a decoupled application where the fun is different from the learning that needs to occur.
Thank you so much. So we are reaching to the end of this session, and we're going to have a little break, and then we're going to come back at 12. Thanks so much, Rita, for the great talk. I'm going to give you applause, and I think that you have received a lot of virtual applauses on YouTube as well. So thanks so much, and we'll be back at 12.
Thanks.
Hello, Diane.
I think she's joining. By the way, we are on YouTube live stream.
Good.
Hello.
I think she's joining. By the way, we are on YouTube live stream.
Good. This will keep our comments clean.
Welcome back. We'll start our 5th paper session in a moment. This session is on the topic visualization and exploration. It includes 6 exciting papers, including the paper that received the best student paper in graphics and visualization. This session will be chaired by Carl Gutman, professor at the University of Saskatchewan. Carl, whenever you're ready, you have the floor.
All right, thank you, Ahmed. Welcome to this session. We're going to dive right into the first paper, which is called Exploring Alternate Methods of Visualizing Patient Data. And I believe we have several of the authors here to answer questions in the Q&A. So let's roll the video.
Hi everyone, I'm Rabia and my research is on exploring different ways of visualizing patient data. So healthcare providers use patients' medical records to support their decision on patients' care and management. But the quantity of data found inside of these records can be overwhelming for healthcare providers. So there's an opportunity here to organize that patient data in summary forms that will allow healthcare providers to access relevant information and manage their patients' care. So right now we have a system called My Health, My Record, which is a mobile application that allows patients to audio-video record their experiences in between visits to their healthcare provider. And currently that system actually lacks a method of visualizing the video data. So we're proposing 5 methods of summarizing that data. And we're looking into what are the acceptabilities and preferences of these visualizations and how do healthcare providers actually interpret them. But for the sake of this presentation, I'll be focusing on the first question. So before we move forward, let's take a look at the visualizations themselves. So first off, we have the word cloud. The word cloud basically takes all of the words that are mentioned in patient videos and displays them based on their frequency. So the most frequent word will be displayed in the largest font size and placed in the center, and the other words will be surrounding it. There's also ways to filter the information, so you can take a look at the 10 or more instances, for example, or physical health symptoms. Then we have the text graph, which was actually newly developed for this research. And it basically takes one word that was mentioned in the videos and stretches it out over a certain time period. So in this example, we're looking at the word pain and how it looks over 2 months. So the patient mentions pain in a both positive and a negative manner. Positive meaning that they're saying my pain is getting better, so that would be less pain. And negative meaning my pain is getting worse, so more pain. And there's also some points over here, like the white circle actually represents days where there were no videos created, and the black circle represents days where there was video created, but no mention of pain. Then we have these buttons, and these buttons would actually take the user to the associated patient video for that particular day. The user can also filter the information, so they can take a look at the positive only, negative only, or they have a choice between a monochrome and a colored graph. Then we have the bar graph. So the bar graph takes words that are mentioned in the videos as well, but this time displays them as bars. And there's quite a bit of options of filtering, so that you can take a look at physical health symptoms, for example, and choose from highest to lowest. Then we have the line graph. The line graph is very similar to the text graph, but this time there are no extra text features. And this particular line graph is actually only showing pain mentioned in a negative manner. These points over here will again take the user to the associated videos. Finally, we have the text summary, which is a point summary of what happened over a certain time period. And there's a choice between a general summary or a quantitative summary for more numerical data. So we evaluated the usability and visualization preferences with an online user study involving 48 participants. The participants were divided into 3 groups. So there was a first and second year medical students, then third year or more medical students, and finally healthcare providers with at least 2 years of experience. And one of the questions that we asked the participants was how useful was each visualization in extracting data on patient status and condition? So the text summary was rated to be the most useful, and that's probably because it actually resembled clinical notes, and that's something that healthcare providers are very familiar with. But the text graph, despite being something that participants hadn't seen before, was actually rated to be quite useful as well. And maybe that's because the text graph actually highlighted some of the important information for the users, so they were able to understand the pattern better. The word cloud was not rated to be as useful as the text graph and text summary, but it was quite useful as well. And maybe that's because the participants were more comfortable with the other two visualizations, but they were open to trying the word cloud as well. Then we had the bar graph. So the bar graph was actually the only visualization that had a good usefulness rating and no negative comments associated with it. And that could be because maybe the participants were familiar with the design, the layout, and the information it conveyed. The line graph was the least rated visualization, and maybe that's because it requires attention to understand the trend and investigate each point, so it wasn't as useful as the other visualizations for the participants. So in terms of design recommendations, the text summary, text graph, bar graph, and the word cloud seem to be acceptable ways of visualizing the qualitative patient data that we have in the MHMR system. The line graph is not as useful and can be given less importance in the MHMR implementation since it does not clearly convey patient information. That actually brings us to the end of the presentation. The funding for this project was generously provided by NSERC, and we would also like to thank the MHMR team for their time and effort on this project, as well as the participants for their time and generosity. Thank you.
All right.
Rabia.
Thanks very much, Rabia. And a reminder to people watching that they can type in questions into the YouTube channel. It takes 20 seconds for me to see them, so we'll pick them up as they come in. But I'd like to start with a question of my own, if I could. And this is really interesting work. And I wondered whether you thought about showing the visualizations to the patients that generated the data themselves. I assume this is based on self-generated patient data. And it's always interesting if the people generating the data can see how, sort of have control over how the physicians might be interpreting their data. What do you think of that idea?
Oh, definitely. So right now we were kind of focusing on the healthcare provider side of it and how they would interpret or deal with these kind of visualizations. But definitely the patients are most important over here. It's their data that's getting visualized. So they obviously should have some control over what they want to see. And we are working on like different types of filters in the system itself that would allow patients to like rate their video, or they can set the mood of that video. So they know like what's getting visualized is based on their data, and it's not just the computer's interpretation of what they are saying, basically.
I can imagine, if a patient really wanted their physician to know that they were in pain, you might just, repeat the word pain 1,000 times so that it, it inflates in the word cloud or something like that. That would be an interesting thing to look at in future. We got a question from Jody Mondal. He says, each visualization is providing summary information. Was there concern among participants about missing some of the information? Because of course there's lots of richness in these journals or in these data that are generated by the patients that might be lost. Is there a way to navigate from the summary back to the details of the actual journals?
Oh yes. So what happens is the videos are always going to be accessible to the patient or the healthcare providers. So at any point in the application, they can always go back to the videos. And even in the text graph, maybe it was too fast, but I showed like you can click on each point, and that would take you to the videos associated with that particular day. So let's say the patient said like, oh, I have a lot of pain today, and it was like the biggest font size and everything. Then they can look into those videos and see like what were they doing that maybe aggravated the pain or anything like that. So there's all to answer the question about missing information, yes, that's always a concern here. But we do try to allow the healthcare providers and patients to be able to navigate back to at least the video. So that's where the raw data is, right? So they can always go back to that and see if, like, what were the experiences of the patient at that point.
Okay, that's really interesting. So a question from Gulnar on YouTube. Was there any erroneous information introduced when transcribing or when sort of automatically inferring the text of the videos? What do you do about those errors when you're trying to do automatic interpretation of text or speech?
Yeah, so for this sample application, at least, or the prototype application, the videos that we had, I took away, we ran like a Python script on it, and I took away any like stop words that may have occurred in those transcripts. So like the, or how, or what, like those kind of words that don't provide any meaning to the information. So those were eliminated. And then the rest of the words were tallied up essentially and just demonstrated on the word cloud. We didn't take away any other words that were not particularly like stop words. So there were some cases where the word cloud actually said like side. So I think the patient mentioned sidewalk and the word cloud said side and walk together, like in that kind of sense. So those words were still there. And I feel like it kind of gives them the participants, or at least the users, a more general summary of like, they're able to kind of put together a story of what may have happened to the patient. So if they have like sidewalk and pain, then maybe they can make a connection between it. It's not to say like that's exactly what the pain was about or anything like that, but there's also that opportunity that you have all these words. So how do they connect to one another? And you're able to come up with those stories.
Okay, that's really cool. I'm afraid we're gonna have to cut it off there. Please send your comments to Rabia, and you guys can talk offline if there are further questions. But now we're going to move to the second paper in the session. And that paper is called Paper Forager, Supporting Rapid Exploration of Research Document Collections. And I believe we have Justin Matejka in the Zoom room to answer Q&A. So let's roll the video.
Welcome to our talk about Paper Forager. This was work done with Tovi and George in the HCI and Visualization Research Group at Autodesk Research, and I'm Justin Matejka. As researchers, we like navel-gazing, that is, doing research about research, or research on problems that we as researchers would like to solve. I'm one of those researchers, and I'm not ashamed to say that this is one of those projects. And one of those things that's of particular interest to us as researchers is literature review. Historically, we've had paper proceedings. With these, it is difficult to find relevant materials, but once you do, it's very easy to transition between scanning through the papers and actually reading them. Additionally, the pictures and layout of an article are visible while flipping through, and they may help you find what you're looking for. And now, of course, we have digital libraries, which greatly improve the process of finding relevant research through text search. However, there's no way for a researcher to use any of the visual qualities of a paper, such as the graphics and layout, to make a decision on whether to actually read that paper. And then to read the paper, we need to download the PDF, which can disrupt your literature review flow. If we break up the stages of the literature review process, you can think of it as having 3 stages. First, finding, or filtering the collection of all possible papers down to those you might be interested in checking out. Scanning, or making a decision for each individual paper about if it's one that you'd like to look at more. And then reading, or looking through the actual content of the paper for useful information. With physical proceedings, the finding stage is fairly separated from the scanning and reading phases. And then with digital libraries and even advanced faceted search tools, finding and scanning are quite well connected, but those stages are fairly separated from the reading phase. With Paper Forager, we wanted to build a tool that could combine all of these phases together seamlessly. So that's what we did, and this is what Paper Forager looks like. The sample corpus of papers we used to test Paper Forager consists of 3,640 papers from the CHI and WIST conferences. And at startup, the main collection view here shows a very small thumbnail representation of each of those papers. Using the search field, users can search for keywords, author names, or conferences to limit the number of papers shown in that collection view. The results can then be filtered further by adding additional search parameters or adjusting the year and citation count sliders, and sorted by either year of publication or number of citations. The top authors panel over here shows which authors have the most publications within the currently active collection of papers. Hovering over individual papers triggers a large paper tooltip, and clicking on a paper zooms it into Paper View. The Paper View shows all of the pages of paper at once. Users can flip between papers in the current collection using the arrow keys, and then clicking on an individual page brings that page into focus. The user can flip through individual pages until the end of a paper is reached. In the paper view, the previous and next papers are preloaded, allowing the user to quickly flip between papers. The side panel provides additional information and controls. A badge icon can be clicked to add the paper to the user's list of saved papers. Collections associated to the references and citations of this paper are also displayed to enable following trails through the citation network. From a technical standpoint, this dynamic style of interface relies on pre-processing the papers into very large images, combining all of the pages for a paper into a single image, and then taking that image and creating an image pyramid from it. This image pyramid is based on the same principle that is used with tools like Google Maps, where large images are sliced into different images of different resolutions, and then the correct part and resolution of the image can be loaded quickly as needed. This lets us see the previews for all of the papers in the overview without needing to download the full resolution image for all of the papers. We conducted 2 user studies, a qualitative lab study with 6 participants, and an external deployment with 153 members of the HCI research community. Both groups provided very positive feedback after using the system, and many users expressed interest in continuing to use Paper Forager after the study period was over. Despite the positive feedback, Paper Forager and systems like it have a number of challenges we weren't able to overcome. The first is ever-changing technology. We built Paper Forager in Silverlight, which was great, but that doesn't even exist anymore. So to revive Paper Forager, we need to start from scratch technologically. Next is keeping the system up to date. With new papers getting published all of the time, it's quite an ordeal to process everything to get it into the format Paper Forager needs. And the final issue is the limited number of papers. All of the WIST and Chi papers is a good start, but really for a tool like this, you'd want access to all of the papers, similar to what you'd get from searching in Google Scholar. Making a tool like this work for very, very large collections of papers will be an interesting challenge. That said, we think the idea of a dynamic paper tool like this is pretty interesting, and hopefully this will inspire more tools like this in the future. Thanks.
All right. The first comment that comes through from Derek is want. I think that's awesome. It's really too bad that Silverlight died. So maybe someday you'll be able to resurrect this in more modern technologies. But I'm going to start the questioning off. And as you might know, I'm very interested in revisitation and spatial cognition in these kinds of systems. Did any of the tasks that you looked at or did people's experiences involve going back to papers? Because I noticed that you rearrange the papers with every new filter. So what was it like to go back to something that you'd seen before?
Yeah, that's a good point. So I think what we often found people would do is they would want to go to the paper that looked like this, right? I know there was a paper that had a big figure up at the top. And so with this sort of thing, they're able to find that type of paper. If they were looking for a very specific paper in a different way that they couldn't detect visually, or they knew was over on the left of their screen, for example, then yeah, that wouldn't work so well. But it did allow for the sort of visual, refinding of papers that some other techniques wouldn't really support.
I think that, that the good thing about that, the overview of the full 3,500 papers is good because it's fixed, right? And that would be a good place to add sort of editware and readware when this thing gets resurrected in the next version.
Yeah, that's a good idea.
Okay, so from the chat, Jody has a question. Does this image-based approach allow selection of part of the text or highlighting it? What technological challenges would there be in allowing people to cut and paste text?
Yeah, no, that's a good point. Yeah, so we take what are in most cases PDFs and then turn them into images. So we lose, any of the text-based, any like the text selection-based ideas. I would think if you're doing this for real, maybe you wouldn't want to convert everything to images, or maybe you'd want to keep the PDF there underneath, so that at a certain scale, maybe you actually are looking at the PDF and you could do sort of the more direct text selection-y stuff that you could on a PDF.
Okay, cool. So another question in from Paul that has to do with citation counts. And every discipline has kind of a different normalization of what is considered a high citation count. So have you thought about adapting this to additional conferences or additional kind of use cases where those kinds of metrics are different?
Yeah, so in this case, the citations we were showing were just citations within the collection of papers in the system. So it wasn't a general purpose citation count, just a citation count within the papers that are in this collection. I think there's lots of interesting questions for how would you do this for, for a much bigger set of papers? And I mean, like I said, I think you'd really want to do this with all the papers, or at least a really, really large number of them, and then a lot of these challenges would become harder.
Do you think that the difficulties that you mentioned in the video about always keeping it up to date and stuff like that, is that going to prevent this from ever actually becoming a real tool? Like, do you think that those are too insurmountable? The interactional issues are ones that we can deal with, but that sort of daily grind of getting new papers in is the real hard part.
I mean, it's certainly insurmountable for me. I mean, I'm not going to be able to keep this up and running, but to keep Google Scholar or any of these other sites up and running, I assume is already a whole bunch of work. And maybe, doing this type of thing is only, a tiny fraction more work than what's already required to keep those types of sites going. So,
right.
Yeah, who knows?
That's right. Maybe Google's listening and we'll contact you after this. All right. Thank you very much, Justin. And we will move on to the next paper. If you have other comments or want to talk to Justin, please contact him or add it to the chat. Our third paper is called Perspective Charts, and I believe Mia's in the room to answer questions. So let's roll the video.
Hello, everyone. My name is Mia McTavish. I'm a master's student at the University of Calgary. I will be presenting my work called Perspective Charts, co-authored by Karayun Edemad, Faramar Samavati, and Wesley Willett. The volume and variety of data available worldwide has evolved rapidly since the invention of the internet. Bar charts are still one of the most commonly used data visualizations today, as they are simple and easy to interpret. However, bar charts are not perfectly suited to every type of dataset. For example, datasets with a large range with important variation at multiple scales presents a unique visualization challenge. Examples can commonly be found in population data, as shown here. A linear mapping between the range of the data and the height of the viewing space can result in undesirable compression of the charts, which makes differences between smaller values less readable. One potential solution is to use a nonlinear mapping, such as a logarithmic function. However, this type of mapping is difficult to read and understand in comparison to simple linear mappings. So how do we find a more natural solution to mapping datasets with large outliers onto a small viewing space? We propose a new technique that uses perspective projection. Perspective contributes to human perception of information. The concept of size constancy explains that the perception of an object's size does not change with the object's distance from the viewer. This is true even for two-dimensional representations of three-dimensional scenes. We use this feature of perception in the design of our perspective charts. We propose 3 novel data visualizations that use perspective projection and size constancy. Our first design, which we call the slanted perspective chart, shows a bar chart that is slanted backwards from the viewing plane, such that it is viewed in perspective. As the lower part of the graph appears closer to the reader, small values in the dataset become larger in comparison to a traditional bar chart. We use a simple 3D environment and predefined camera orientation for this design. The main problem with slanting a traditional bar chart is that large values in the dataset become compressed due to the perspective projection. This may make large values more difficult to read and compare. Our next chart, the stepped perspective chart, is designed to address this issue of scaling large values while also improving the readability of small values. In bar charts, space in some parts of the chart may be wasted due to large differences in values or outliers in the dataset. In these datasets, we can identify clusters of data separated by transitive regions. We can reduce the amount of wasted space by visualizing the transitive regions in an extreme slant. Each bar's value is still measurable in an area that is perpendicular to the view. This technique is comparable to traditional broken axis bar charts, which also address issues associated with large gaps between values in a dataset. However, broken axis bar charts have been shown to negatively affect the perception of scale in datasets. In the stepped perspective chart, the transitive region is still visible and the reader is able to perceive the approximate size of the gap. Our third perspective chart, called the circular perspective chart, is inspired by the impression of looking up at tall buildings and skyscrapers from a low vantage point. The horizontal axis of the chart is mapped to a circle, with the vertical axis extending away from the reader's view. This chart occupies a consistent viewing space regardless of the scale of the data or the number of entries in the dataset. Now that I have introduced our 3 visualization designs, I will describe the user study that we have performed. The study quantitatively measures the accuracy and speed with which users perform a series of tasks with various chart types. We also collected participants' opinions of the 3 types of perspective charts in a qualitative study. In our user study, we describe one hypothesis per perspective chart design, based on the concept of size constancy. The details of the study design are described in our paper and are available on the Open Science Framework. When comparing perspective charts to traditional chart types, none of these comparisons showed a significant difference in accuracy rate or task completion time for any of the evaluated task types. This suggests that due to size constancy, the use of perspective did not impact participants' ability to visually interpret values. As with the slanted perspective chart, the stepped perspective chart showed no significant difference in accuracy or timing compared to the traditional comparison method, in this case, the broken axis bar chart. However, participants were able to complete certain tasks significantly more quickly and accurately with the stepped perspective chart than with the scale stack bar chart, a recent state-of-the-art design proposed by Hlowacz et al. The circular perspective chart's comparison fixed viewing space visualization, the radial bar chart, showed significantly higher accuracy than the circular perspective chart for sorting and value retrieving tasks. Participant feedback about the circular perspective chart was also mixed. Some participants indicated that for larger values, the bars became too severely compressed in the circular perspective chart. However, participants also felt that the design was impactful and may be appropriate for artistic visualizations. In conclusion, results of our evaluation indicate that the use of perspective projection in data visualization is worth further examination. The slanted and stepped perspective charts particularly merit more in-depth evaluation as alternatives to existing chart types. Participants also felt there was artistic value in the circular perspective chart. Therefore, charts that utilize perspective and size constancy can be a viable alternative to existing visualizations. This concludes my presentation. Thank you so much for listening.
Welcome to our.
Thank you, Mia. So let's start with a question from me. I think this is a super cool idea. I noticed that many of your examples were sort of the classic good example for this kind of approach, where there were lots of bars at the bottom that need to be kind of looked at in detail, and then there are one or two outliers up at the top. Did you also look at what was it like to have a whole bunch of tall bars that have to be compared in that sort of visually compressed space, as well as the ones at the bottom?
Yeah, thank you for your question. Definitely the examples that we showed fit more closely with sort of the use case that we intend for our visualization. In our evaluation, we had a variety of data sets. We did focus more on our specific use case. And we did find that for data sets that had, like your example, like very large values to be compared in a more compressed area, the results definitely weren't as favorable. So we did acknowledge and notice in our user study that there's a bit of a trade-off there. So there's kind of more appropriate use cases and less appropriate. So we did definitely look at that.
Are there ways to kind of automatically figure out whether or not a given data set is appropriate for this kind of thing? Like, obviously, does it fit the idea of a bunch of things at the bottom that would be good in sort of the magnified view and then a couple of outliers? Like, you could presumably figure out whether or not that's a good fit.
Yeah, absolutely. So for our stepped perspective chart, we do automatically group those data sets as far as like determining which items are on the lower cluster and the higher cluster. So we could absolutely like perform some sort of analysis like that. We haven't necessarily found what the magic number is necessarily, but we could definitely perform some analysis on that.
Okay, cool. So there's some questions coming in on YouTube. Paul asks, were there considerations on the perspective chart that showed data towards the viewer as larger? And I know you talked about this idea of perspective constancy, but there is sort of this idea that they're just bigger. And so did that have any effect on the users?
Yeah, that was definitely one of the things that we were looking to examine in our evaluation, where does the effect of the perspective, is it just negligent, like because of size constancy, is there just no difference? Or is it because they're bigger and closer to the user? And, it's difficult to perfectly understand what exactly, if it's like a subconscious matter of human perception, it's hard to necessarily determine what is having that effect, but likely it is that they're larger. So you can, the magnitude is increased. You can have a bit more of a easier time visually making a distinction based on the scale line. So I'm sure it does have part of the effect on that.
Okay. Deb Fels has a question. Did participants identify any issues or problems reading the charts? You talked a little bit about how they were able to interpret it, but what did they think? Were there any sort of slight or small issues that came up?
Yeah, I touched on this a bit in the presentation, but the participant feedback was a little bit less favorable for the circular perspective chart, just in terms of readability. And they did indicate that some of the participants did indicate that they had a harder time reading the data in those types of charts. And my belief is that the circular perspective chart, it would be because it's showing a lot of the data at a much more extreme angle. So that kind of informs us that the effective perspective, it may be something that you can utilize in visualization, but there might be a limit in the sense that some of the more extreme examples were difficult for some of the participants.
Right. And so there are two questions coming in that sort of follow up on that. Is the idea of there are individual differences in things like visual perception and perception of perspective. Did you see particular, like you talked about some differences that individuals had certain comments, but were you able to categorize that this kind of a learner, or visual learners do it this way, or people who are good at reading maps or spatial cognition had differences in these kinds of interpretation tasks?
Yeah, that's a good question. We didn't necessarily ask them their opinions or their thoughts on what type of learner they are, or things like that. We did gather information about like which fields they work in and how familiar they are with data visualizations in general. And we didn't really notice a strong trend either way, as far as, well, people who rank themselves as more familiar with using visualizations in general seem to have a bit of an easier time. But like science fields versus arts fields, we didn't really notice a big discrepancy, but it would be something worth analyzing further, I think.
Okay, cool. I think that actually just perfectly brings us to the end of the 5-minute Q&A. So thank you very much, Mia. And again, if you have further questions, please do put them into the chat and Mia can take a look at that later. But now we're going to move on to the next paper. And oddly enough, this one also has to do with bar charts in a perspective reality. It's called How Tall is That Bar Chart? Virtual Reality, Distance, Compression, and Visualizations. And Diane Watson is here to participate in the Q&A. So let's roll the video.
Welcome to our How Tall is That Bar Chart talk. This was work led by Diane Watson while she was an intern with us in the HCI and Visualization group at Autodesk Research. And Diane is the expert here and on the call, so she'll be ready to answer your tough questions when we're done. So as VR technology continues to improve, we're seeing more interest and more great research looking at general purpose data visualization in VR. But as we make visualizations in VR, we need to look into how some VR-specific phenomena might affect our perception of these visualizations. One such phenomenon is called distance compression. While in a VR environment, when shown an object at a given distance, people tend to unconsciously underestimate the distance of that object. This is a well-studied and well-known phenomenon. This could, of course, be a problem for data visualization in VR. For example, if shown a very tall bar chart like this, would you underestimate its height in VR? Rather than just showing the distance compression affects visualizations in VR, we want to see if there are ways to mitigate its effect. To do this, we set up a study that looked at two variables that might affect the amount of distance compression experienced. The first is the depth cues used in the visualization, and the second is the scale of the visualization. So first, considering depth cues, the most basic chart in VR has no depth cues, no textures, no ground plane. However, the lack of a ground plane tends to make people nauseous in VR, so we did not test this condition. The first depth cue condition we did test is called few depth cues. In this case, the objects had a consistent luminance and no texture, and there's a simple textured floor plane underneath the chart. The next condition is called some depth cues, where the bars were given a slight texture and they cast shadows from the light. We'd consider this a best practices chart for designing visualizations in VR. This has potentially useful cues without anything too over the top. And then we have a third condition called rich depth cues. And in this case, the scene is augmented with objects that could be used to determine relative size, such as trees and cars and light poles. So in the other variable we're looking at was scale. And so to begin with, we have what we call personal scale. And so in this case, the entire visualization could be seen at one time while looking straight ahead. The next scale is called house scale, where the participant needed to look up slightly to be able to see the entire chart. And then finally, we have what we called skyscraper scale. This is an extremely tall visualization requiring the participant to look way up to see the top of the chart. And to study this, we had the task, and in the task, users were asked two questions. The first, what percentage of the large bar is the smaller bar? And then also we asked how tall is the smaller bar in real world units, so they could answer that in feet or meters or whatever they wanted. And so from this first study, the main interesting takeaways were that around 77% of all height evaluations were underestimates, which confirms that distance compression was indeed generally happening for height evaluations. And secondly, and sort of interestingly, the average error on the height comparison task was only 9.7%, which suggests that while distance compression was a large issue on the absolute value estimation task, it was less of an issue in the comparison task. When we looked at depth cues, so the style of the rendering in the charts, actually the performance varied very little across the 3 depth cue conditions that we looked at. However, interestingly, 81% of participants thought they performed the best in the rich depth cues environment. That's the environment with the trees and light poles and etc. So we ran two more studies beyond that first study. The second study is looking at how people could move around in a VR environment to look at charts. So having different platforms and elevators and set viewing locations to look at the chart. And the next was looking at different types of charts in VR to see if they have the same properties that we found with bar charts. And so from these studies, we were able to produce a set of 6 design guidelines for presenting charts in VR, which we hope will be useful for future designers and researchers in this area. Welcome to our talk about.
Thank you, Justin. And we have Diane here with us in the Zoom room to answer questions. So I'd like to start, Diane. Oh, hi, Diane, by the way. Nice to meet you. Nice to see you again. In the last video, we learned all about how size was constant in perspective. And now, is it really? Like, what's going on here? I thought size was supposed to be constant when you saw things off in the distance. What was going on in VR?
So it's really interesting how consistently distant compression exists in the real world. Like, it's just, if you're gonna make a visualization like as an art piece, you're gonna run into problems of like occlusion and how far back are you? And so this was really trying to look at that. And for all of the study, the comparison tasks actually didn't have a lot of error introduced. People were still pretty good at comparing, like, oh, this is half of what that is, but they weren't very good at, oh, that's about 1 meter tall, or right. So you would want to avoid like using a legend that says like 1 meter equals $100 or whatever.
And so were the bars always kind of perpendicular to the viewer, or could you see them actually were the bars at different distances from the viewer, which would maybe accentuate this problem?
So the bars were always the same distance from the viewer. In one of the studies, people could like walk around on a platform, but this is an issue in VR, is because although you can explore the space, you don't want people to like walk into the desk nearby or get nauseous and have to like sit down and stop. And so for the most part, they could like move around, look up and down, but they stayed pretty still.
Okay. So some questions now from the chat. Derek says, I may have missed this detail. Was there a difference in relative size estimation accuracy under the different scale conditions?
Yes. So as far as I remember off the top of my head, so the skyscraper scale was awful, basically.
Right.
Where the scale that was kind of as tall as you were and the scale that was kind of as tall as a building might be were about equally the same bad, but like the skyscrapers, as you would expect, was just hard. It was also really fun to watch participants just like look like way up and just.
It's a bird, it's a plane. So you talked a little bit about, or I guess Justin talked, but you wrote about the issue of having all of the depth cues like trees and buildings and stuff in there. Do you actually envision situations in VR where I need to know that that bar is about as tall as that tree, or that bar is taller than that building, or it's taller than a person, or something like that? Are those real world references actually valuable, or are bar charts really all about, what's the y-axis and in which bar is taller?
So because the relative comparison task was not really affected by distance compression, that's probably why the depth cues didn't matter. But there's a lot of things in the world that we take for granted when trying to determine how far something is. So like if there's tiles on the floor, we can see the lines. Even in games and such, like how close the textures are together gives you a sense of distance. And so the depth cues one was just like, if everyone had everything they had in the real life, would they be able to perform better? They didn't, but they did feel a lot more comfortable, in the environment when there was like grass and trees and a house behind them, etc.
Okay, so we'll take one final quick one. Paul asks, since the charts are shown in VR and you have control over them, did you think about animating them or any other kind of visual effects that might have helped people with these estimations?
That is definitely the next step. So this was very founded in some foundational work on paper visualizations, like actual paper, and was extending it to see if the same sort of patterns were there. But paper visualizations have come a long way now, especially with computers. So there is so much that you could do to just augment this experience for sure.
Okay, cool. I think we're going to have to wrap it up there. As always, please send your comments to Diane through the chat and she can follow up with you. But now we're going to move on to the next paper. It's called Visual Interactive Neural Machine Translation. And let's roll the video.
Hello, my name is Tanja Munz. I'm from the University of Stuttgart and I'm presenting our work Visual Interactive Neural-Machine Translation. Neural-machine translation is currently the most commonly used method for machine translation. It is computationally efficient, translation results can be impressive but might also contain errors. A common problem is over and under translation, when words are translated repeatedly or not at all. Additionally, the translation of documents from specific domains might be challenging. When the translation model was trained on general data, there might be words that are not known by the model or that have different meanings in different domains. Here, more background knowledge about the text is required to translate a document appropriately. Also, a translation might be correctly translated but not express someone's style or be appropriate for some occasion. Humans are slow but can detect and correct mistranslations. In a visual analytics system, both capabilities can be combined to generate high-quality translations. In our approach, a document is first translated with a neural machine translation model. We implemented an LSTM-based and a transformer architecture for this. Then it uses the tagged sentences for correction using filtering options. Next, sentences are visualized and can be interactively modified. After correcting sentences, user corrections are used to fine-tune the model, retranslate sentences, and improve translation quality of the document. After uploading a document, this is the overview that is provided to a user after automatic translation. On the bottom, the document view shows all sentences and their initial translations. Correct sentences can be marked as correct, or mistranslated sentences marked for further investigation. To detect mistranslations, sentences can be sorted and filtered. For this, we can use the metrics view on the top that shows some metrics that correlate with translation quality in a parallel coordinates plot. It is, for example, possible to filter for sentences that have a low translation confidence. Here is, for example, a sentence visible that was undertranslated and needs correction. Additionally, the key phrase view on the top right provides a list of words that can be used for sentence filtering. Key phrases are words that are domain-specific and were not often included in the vocabulary of the training data. Here, an example where each occurrence of a key phrase was mistranslated. After selecting a sentence, this is the more detailed view to explore, understand, and correct translations. The attention view visualizes the relationship between words of the source sentences and the current translation. The thickness of the connecting lines and the transparency of words correlates with the importance of source words for the translated words. This usually shows an alignment between translated words in different languages. It can be used, for example, to detect areas that are not well translated. This view supports interaction to analyze the influence of individual words. The beam search view on the bottom visualizes different translation possibilities as hierarchical structure and provides insights how the underlying translation model chooses the final translation. This is an interactive visualization that can be used for post-editing the machine-generated translations. Here, for example, we choose a different translation from the recommendations. This is an example where we select a different recommended word. Furthermore, users can type in words that are not recommended or included in the vocabulary of the model to improve the translation. After correcting sentences, our model can be retrained using the user corrections and the document can get retranslated. In the example from before, the key phrase is now correctly translated after retraining for only a few sentences containing the term. This is visible from the changes that are marked in the document view. We provide a source code of our approach and pre-trained models online. Feel free to try our approach yourself.
Awesome. Thank you, Tanya. And as always, please type your comments or your questions into the YouTube chat. I'm going to start us off. So this is super cool stuff. And the interesting thing is, I don't know anything about neural machine translation. Like first, is this what Google Translate does? Is this what all of the commercial tools do, or is that something different?
Yeah, their approaches also use this technique. That's correct.
Okay, so
it's more complex. They have much more data, and
right.
So.
Okay, cool. I wanted to know what category we were working in. The first question that I have is, what do translators think of this? Because I kind of see this as being more oriented towards professional translators who really care very much about whether this word is correct or something, rather than somebody just wants to know, is the store open or not? The sort of typical Google Translate user. Have you shown this to people who translate for a living? What did they think of it?
No, we didn't do this. We haven't shown it yet to professional translators.
Is that the goal? Like, who is the eventual user of this kind of a system?
Well, we kept the target group quite broad. So, for example, of course, professional translators, that they can improve the model to their own style and how they want to translate, but also for people interested in translation or want to translate something and also better understand how the translation is performed. That's also the reason we have these additional visualizations to better see what the underlying model did.
Okay, cool. Because I was looking through the examples in the paper, and they're translating German to English, and I don't speak German. So it was very interesting to see these ideas of over and under translation, where 3 words in German kind of all go down to 1 word in English. So, is that something that you think professional translators would use? Because as somebody who doesn't know the other language, I thought this might be quite useful for language learners to try and sort of explore some of the subtleties of the way that the different languages work.
We had, for example, really nice examples where we could see when the order of the words was different in the different languages, then the connecting lines really showed how the differences are in the languages, and that for the really big insight in understanding the translation.
Okay, cool. There's a question from Deb Fells. How are conflicts resolved if a user chooses different words for the same translation, or because there are always these opportunities to go multiple directions? What does the system do about that?
So when you want to choose a different word, you can either select it if it's already recommended or type in yourself, and then afterward the model uses the beginning as a constrained words and then translates the remainder of the sentence only. Okay, and another question that came up during the video is you showed one example in the parallel coordinates plots where an outlier, a visual outlier, was an indicator of an incorrect translation or an over or under translation. In your visualizations, are you finding that bad translations always end up as visual outliers? Like, can you reliably choose which sentences are not well translated by just looking at the visualizations? No, the metrics we choose, they can help finding mistranslated sentences, but it's not always true. And also often when the values are the metric values are good, there might also be translations. So this is just one approach we chose, but there has to be done more work to better find the mistranslated sentences.
Okay, cool. Thank you very much. That is all the time we have for the Q&A, but for everybody watching, if you have further questions for Tanya, please put them into the YouTube chat. And we will move on to our to the final paper in our session. It's called Contour Line Stylization to Visualize Multivariate Information. And as mentioned at the beginning, this is the recipient of the Michael Sweeney Award for the best student paper at GI. And let's roll the video.
Hi, I am Ghazi Hasnath, a master's student at the University of Saskatchewan. In this video, I will present my work on contour line stylization to visualize multivariate information supervised by Debojyoti Mondol and Carl Goodwin. Contour map is a popular way to visualize one variable's distribution using contour lines and contour bands. It also shows certain value increase or decrease using visual cues like color. Now that's one variable. In a situation where there are multiple variables, the challenge is to visualize all in a single view. The popular alternative of using glyphs suffers from visual clutter and base map overlap, whereas a grid view lacks geospatial connectedness and gradient information. Therefore, our goal was to see if the base contour lines, which are already present in the map, can be leveraged to visualize the other attributes. To do that, we created 5 designs to visualize 4 variables. Let's take a look. The first design is called parallel lines, where the contour lines of A are used to visualize B, C, and D in 3 parallel lines. The thicknesses of B, C, or D at a specific point is mapped from their corresponding values. In color blending, the thickness of the line depends on D, and the color at that point is a multiplication blend of B and C color shades, from white to red and white to blue, respectively. In pi, each of the 3 variables have 120-degree space allocated in each circle that they fill according to their values. The fourth design is thickness and shed, where B and D control the thicknesses of the blue and red lines respectively, and C controls the shades of blue. Finally, side by side shows B, C, and D separately, where the values control the color shades. Now, 2 most important parameters of a contour map are contour line width and the number of contour intervals. So we conducted our first 2 studies to investigate the effects of these 2 on visual interpretability. With the observation of those 2 studies, we conducted our final study, where each task was completed on both real-life datasets and synthetic datasets. The results reveal that real-life dataset has more accuracy than synthetic data, which is because real-life data has simpler spatial correlations. And design-wise, parallel lines and side-by-side have more accuracy than color blending and thickness and shed, where pi is a reasonable compromise between 2 groups. Interestingly, design performance also varies from task to task, making one design better than the other in one task, but the opposite in another. Let's see an example where we need to select the contour part with the maximum difference between B and C. In color blending, the solution is to select the contour part with the most red or blue in it. As we can see, the regions 2 and 3 have lighter shades than 1 and 4, so they are eliminated. Now, between 1 and 4, it's a bit hard to choose one because both are reddish. And moreover, as you can see from the diagonally placed boxes in the legend, a darker shade can mean equal or similar amount of B and C. Now, if we go to parallel lines, it's much easier to say that one is the right answer, as we can clearly see the actual values of B and C separately, making an easier difference calculation. Therefore, parallel line is the winner. Now, in the second example, we need to select the contour part with the maximum change in B values. In parallel lines, the question wants us to only consider the red lines and pick the one with the most changes in thickness. Well, we can easily eliminate 1 and 2 because they have constant thicknesses, but between 3 and 4, it might take more time for an user to detect the right answer. Now, if we go to color blending, it's easier to detect 4 as the right answer because it clearly shows more changes than 3. Therefore, color blending wins here. So finally, we generated a table that recommends designs to use for various task domains in 3 different environments. Each of our 5 designs was recommended in at least one scenario. Let's see a real-life application now. The left picture shows some red and blue lines known as fronts, which are detected by the National Oceanic and Atmospheric Administration using softwares or by painstaking inspection of the numbers plotted on the map. We try to visualize this using our parallel lines design, which readily reveals some of the interesting curves that match some of the detected fronts. This shows the potential of using contour line stylization alongside our traditional ways. Lastly, the final takeaway of the presentation is contour lines that are already present in a visualization can be leveraged to effectively convey information about other geospatial variables. Thank you so much for your hearing. Thank you all.
Hello, everyone. My name is Mia.
All right, thank you very much, Hasnat, and congratulations on the Best Student Paper Award. As the questions come in on the YouTube chat, I'll start us off with one, and that is, you used, I think you had 3 variables in addition to the contour lines. How many do you think that you could get? Could you do 10 different variables in any of these representations, or what do you think is the limit? You're muted, Ghazi.
Sorry. Right. Yeah. That's a very good question. Thanks. The thing is, it depends on the design first. Like, speaking of parallel lines, how many lines I can put? 3, 4, 5, but it depends on the number of contour lines as well. If there are like a lot of number of contour intervals or lines in a map, then we cannot put a lot. But that's a very nice way to study. Like, we can really study how many variables to put. Speaking of pi, where we divide the circle into 3 or 4 different parts, having 5 variable means 5 different, like 60 degrees with 6 variables. So it actually depends on the type of design, and that's a very nice way to know the limits of the designs, which can be a part of a further study. Thanks.
Yeah, that's interesting, and I guess it's interesting that the pi design doesn't take up any extra space, but it just means that the region for each of the variables gets smaller and smaller as you add one. So that's an interesting trade-off.
Yeah.
So here's another question, and about doing this in a real-world system. I love the picture of the fronts. So how much have you tested this with people who have real experience with, I don't know, with climate or with these kinds of maps? And what do you think would happen when they use them? Are they so used to one kind of contour stylization that they wouldn't understand this? What do you think?
That's a good question as well. Okay, so for our studies so far, what we did is we studied on the basis of participants who are not actually people from the meteorological side. It would be very, I would say, very interesting for them to see this. Some of these designs need a bit of learning, like thickness and shade or color blending, because they need a bit of learning to know how to interpret the values and everything. And again, some of these designs like the pi or the color, which have like similar encodings for all the 3 variables, B, C, and D, can be easily perceived by people. That would be a very interesting part as well if we talk to some climate experts or meteorologists with our designs. Yeah.
Okay, cool. Jody has a question from the chat. Can you comment on how much the background interferes with the visual color encodings, And could anything be done about these interferences?
Oh, okay. So speaking of background, in our studies, we also added some questions based on the backgrounds. Like we put some icons over the, icons overlaid by our visualization, and asked our participants to count the number of icons, I mean the landmarks of something. And we found out that width and contour interval interferes, and they have a trade-off. The thing is, if there's a systematic design where we can change the colors for the visualizations based on the color of the background, then it would be great. Because if I'm looking over a green map and my visualizations have green lines for any of the variables, it's difficult. So having capability of changing the way the visualization works with color would be a very good part.
Okay, and one final question. I love the idea that you're using objects that are already on the map, like these contour lines, and then making use of them. Could we do that with other objects that are already on the map? Like, could we color code the labels or the road markers or things like that in maps to do something similar?
Speaking of road maps, I think what we could do is we use Google Maps every day or something. Google Maps shows red for high traffic or something. With that red, we could show another parallel line, like number of restaurants or something like that, which would be very good as well. I think that's a very nice idea. Yeah,
that's cool. Yeah, because there are a lot of roads in many maps, so that could be a good idea. I think that we've run out of time for the Q&A, so thank you very much, Hasnat, and congratulations again. And this brings us to the end of the session, so I will turn it back to the chairs to move us to the next one. Thank you all.
Thanks.
Thank you, Coral, for excellent chairing job. We'll move to the next session, and Ali, whenever you're ready, you have the floor.
Thanks, Ahmed. So we reached to the sixth and final paper session, VR, AR, and 3D input. We have 6 great papers in this session, and Dr. Drake Riley from Dalhousie University is going to chair the session. The stage is yours.
All right, thank you very much, Ali. That was the shortest coffee break ever. All right, we do have 6 great papers, and we should get started right away. The first will be presented virtually by Hubert, who will then be able to take Q&A. I will remind you to post your questions on YouTube as you have them, so that we can see them right away due to the lag. All right, take it away, Hubert. Or virtually, Hubert.
Hello, everyone. This is a presentation of a paper called A Comparative Evaluation of Techniques for Locating Out-of-View Targets in Virtual Reality, written by me, Hubert, Joseph Malloch, and Derek Riley at Dalhousie University. In this paper, we created peripheral-based visual cueing technique to enhance target searching experience with limited field of view. For the first study, we compared the new techniques against flying arrow, a baseline technique. For the second study, we enhanced the flying arrow to be more like our new techniques, which are visually persistent and less obtrusive to use. We will now discuss the first study. Our first technique called BSU. BSU appears as a solid blinking ring. It is visually persistent because it is always visible to the user, and its position is user relative, which means that the positioning of the cue is based on the user's head orientation and the user's vision. You can see the technique in action in this video. Another technique is FSU. It is similar to BSU, except that it has a faint appearance. We implemented a faint appearance to also see whether we can make the cue as faint as possible or not. Flying arrow is a baseline technique developed by Grunfeld et al. It is simply an arrow that guides the user to the target. Notably, our version has some modification. For example, the arrow will not play any sound once it hits the target like in the original one, to make sure that our study is purely visual based. For our study, we recruited 24 people from Dalhousie University. Our hardware is Pimax 5K Plus. We used this piece of hardware to ensure that we could display SU peripheral-based technique in the user's peripheral vision. All the hardwares do not have enough FOV to do so. We also have 3 types of the scene or environments. A is the simplest one. B is the more complex one made using a realistic skybox. And C is the mixture of real skybox with a 3D animated model. The trial simply consisting of the use of the participants trying to selecting out the view targets using the help of the techniques. The results are as following. BSU and FSU are effective based on multiple linear regression on speed, as seen in the first figure. FSU, however, is prone to blending in with the environment, which reduces the chance of successful target acquisition, as shown in the second figure. The participant felt flying arrow is slowing them down in qualitative analysis. The technique is superior when it's come to subjective measures like comfort. The takeaway is that the peripheral-based techniques are viable, but they must stand out. We identify visual persistence and unobtrusiveness as the key properties for BSU and FSU, and we try to add them to flying arrow in this study. FA minus arc minus trail is the baseline version. It has the same behavior with the original flying arrow. The appearance is slightly different to make it more compatible with the further augmentation for the study. In this version, we added a trail to make the cue more visually persistent to the user. In this version, we make the cue orbits around the user instead of flying straight to the user to reduce obtrusiveness or when the cue is getting too close to the user. In this version, we combine both the arc and the trail behavior to reduce obtrusiveness and to maximize visual persistence. The results show that trails are helpful at increasing speed. Visual persistence can help the user to be faster at target acquisition. Orbiting is not helpful. However, we think that with more intelligent orbiting behavior, the user might become more productive. Trail can be used in case when the head-worn device field of view is too limited for techniques such as BSU or FSU. And thanks for watching.
Okay, great. So Hubert's here and he's ready to take some questions. I've got my eye on the YouTube chat. So as questions will come in, I'll ask a question just to get started. So Hubert, you mentioned that the visibility of the cue is really important for these peripheral cues. I imagine though also the you don't necessarily want every cue to be so prominent that it draws your attention away from what maybe you're what you're trying to look at, or your attention is always alerted with every cue, I suppose. Do you have any thoughts about trade-offs there, how you might design cues depending on maybe the activity or the media that people are interacting with?
Absolutely. I think one of the most important thing when designing a cue is also to keep what the cues be used for in mind. Like for example, even though the studies show that FSU, the faint one, is tend to blend in with the environment, but if we don't really care about how it blends in with the environment, or if we want to pose a challenge to the user instead, like making these cues harder to find on purpose, then that might actually be an ideal property that we may be looking for.
Okay, we've got a question from Debajoti. Can you comment on how much the background interferes with the visual color encoding and what you might be able to do about it? Sort of related to the previous question, I think, but.
Yeah. So I think that for the peripheral-based cue is that you want it to be as opposite from the background as possible. Initially, we did look into, I think, the concept of salience. So I think that one of the things that we should look at is to make the queue as salient as possible, so to better contrast with the background. And we found that in the case of bee zoos, why it works so well is that because it has a simple shape and it tend to go pretty bright, it tend to stand out in every single scenario. I think that the use of animation could also be helpful as well, like both type of the queues blinks, but that alone is not enough. It must also have it must also be visually distinct from other queues as well, or from the environment as well.
Okay, great. All right, so I think that's about all the questions we have at the moment, or is this another question from Richard Brath? I'm not sure if that was our question or if it was the previous session. Historic approaches to multivariate contour lines. That seems to be the previous. All right, so that's enough for this talk. Thank you very much, Hubert, and we'll move on now to the next presentation.
Hi, everyone.
Thank you.
This next presentation is Jiayi Hong, and the title of the presentation is Design Evaluation of 3 Selection Techniques for Tightly Packed 3D Objects in Cell Lineage Specification in Botany.
Hi everyone, my name is Jiayi Hong. I will present our work in collaboration with Farhan Ahjalagi, Alain Tubuya, and Tobias Ethenberg. Our work was about design and evaluation of 3 selection techniques for tightly packed 3D objects in cell lineage specification in botany. In previous work, most selection techniques were designed for datasets where objects were sparsely displayed like this one, or densely displayed like this one. However, things are different in our case where cells in the plant embryo are densely packed without any space between them. But in what scenario biologists will have to select these individual cells? Let's first look at this embryo, for example. It contains 4 cells, and as time passes, it may develop into 8 cells like this one. In the real scenario, biologists rebuild the embryos from the slides got from microscopes. For example, here are the illustrations of embryo spatial development. However, from the slides, we could only know the shapes of cells at a specific time. Based on these, biologists will trace back the history to better understand the embryo's development. To achieve this goal, they need to find the sister cell for every cell, which were developed from the same parent cell. Currently, biologists' workflow is to target at one cell and then check all its neighbors one by one. For each neighbor, they will check its shape and the shared surface between cells. They will continue this process until every neighbor has been checked. Then, based on their previous knowledge and experience, they will decide on which cell is the most likely sister cell of the target one. From this process, we extracted 2 essential parts of the workflow: discovery and traversal. Based on this, we developed a focused view to help with targeting and used associated numbers to simulate biologists' knowledge and experience for participants. We developed these 3 techniques from 1 dimension to 3 dimensions to solve the problem. For the list selection, participants could select all cells from the list by scoring it. As for the cross-section, we assumed that by moving the cutting plane, users could see the cross-section views of the embryo and select cells from that. However, since the cross-section view selection performed not so good in our pilot study, we excluded it in our formal study. In terms of the explosion selection, users could drag the slider bar and explode the embryo. Then, occluded cells could be seen from view. Thus, we included list selection and explosion selection in our study. Besides, we added a combination selection technique which allows to select both from the explosion view and the list. Based on this, we developed an interface to help with the process. The interface contains 3 main parts: instruction panel for providing guides, 3D view containing 3D cells, and operation panel for discovering cells and traversing its neighbors. We conducted a user study with 24 participants and evaluated these 3 techniques from completion time, accuracy, and clicking ratio. Here are our study results in comparing list selection with explosion selection. In completion time, some evidence showed that list selection was better than explosion for overall cells and cells inside. For accuracy, the results are similar to the completion time. In terms of clicking ratio, which is to see how efficient their clicking is to get the answer, list performed better than the explosion selection. We also performed a post-study interview asking participants about their preferences of the techniques. The results showed that most participants prefer the combination technique most. From the results, our main takeaways are, firstly, 3D interaction techniques work best for truly 3D tasks, like discovering specific cells in an embryo. Secondly, explosion techniques make it possible to access objects in such tightly packed 3D environment. Thirdly, the combination techniques seem to combine this advantage of the single technique, which are list selection and explosion selection. Thanks so much for watching. I'm ready to take questions. Hi, everyone.
Great, thanks, Jiayi. You're here now to take questions. I've got a question just to get us started. So are the techniques, do you think the techniques are impacted by the geometry of the biological element maybe that's being explored?
Yes, we chose these 3 techniques because these 3 techniques are from 1 dimension to 3 dimensions to investigate different dimensions of the cells. Like for in the list, we introduce this selection technique because users may be more familiar with the 1 dimension selection, and for 2D is more used in biology things because they used to watch slides from the microscopes. And we also included the explosion part because the 3D objects could maintain the 3D information of cells, which is more essential for the biologists.
Right, great. So I guess just to follow up on that, imagine there was a 3-dimensional biological, like a brain, or just a very spherical, like the example you showed in the video, a very spherical biological entity, right? Versus something that might be, spiral or long and thin. So the 3D structures themselves are different. And I'm wondering if the difference in the 3D structure might impact the efficacy of the different techniques that you studied.
Oh, yeah, it's a quite interesting question. Because right now, this embryo data set is exactly the real embryo data set we got from biologists, and the unique properties of this data set is that the 3D objects are tightly packed without any room between them. And we actually, we can think of some scenarios that have similar properties, like maybe for machines which are tightly packed, or for humans brain cells. And but we think it could have some influence on the shape about the shapes of the different objects, but we chose this data set because it is real scenario, and we could do some in future study. We could do some evaluation on how the shapes would have influence on the different performance of 3 techniques.
Great, thank you. Carl has a question. He's asking, is the explosion technique difficult when structures are coiled or spiraled or twisted? Which I think is similar to what we were just discussing, but.
Yeah, it's similar to that. The explosion techniques, the purpose is to explode the data set and to increase the distance between two cells, like if you increase their distance into a quite a large distance, you can see like these two objects will be divided in, so you can easily select from it. But yeah, I think it could have some influence, but the explosion selection works quite good when our participants are trying to discover one cell from the whole embryo, which are really inside, are totally occluded from view by other cells. And I guess if you increase the distance of two objects to a larger distance, you could make a good selection.
Great. Yeah, Carl is adding an example of a coil or spiral. Something's very tightly twisted, like a gene looks like a tangled ball of string, right?
Yes. Yeah, it depends on the explosion angle, I guess. For example, if you chose their shared center to be the explosion center, and you want to explode them to different directions, I think it could work. But if you are trying to drag them in the same direction as they develop, I think it will be more difficult. I think it depends on the directions you explode them.
Okay. Well, thank you very much, Xiaoyi. And we are now ready to move on to our next presentation.
Welcome.
And the next presentation will be presented, or Q&A will be presented by Fabian. The talk is Audiovisual AR Concepts for Laparoscopic Subsurface Structure Navigation.
Welcome, and thank you for your interest in this talk on audiovisual augmented reality concepts for laparoscopic subsurface structure navigation. My name is Fabian Jöris, and I'm with the University of Magdeburg in Germany. The work that I'm going to present in this talk is set in the field of laparoscopic kidney surgery. In laparoscopic surgery, the surgeons do not access the surgical area directly, but through small openings in the abdominal wall. More specifically, this work looks at laparoscopic partial nephrectomy. The goal of this operation is to remove a tumor from the patient's kidney while preserving as much healthy kidney tissue as possible. After the tumor is resected, the resection wound itself needs to be repaired. In particular, major lesions in urinary or blood vessels need to be repaired individually, and for major sutures, the surgeons need to make sure not to injure vessels that lie close to the newly created surface. When developing navigation solutions for this application, the challenge is that the resected tissue volume is not known. And that means that also the geometry of the newly created surface is not known to the navigation system. And thereby it is very difficult to determine which vessels have been severed and which vessels now lie very close to the newly created surface. And this work presents an audiovisual augmented reality concept that tries to target this challenge. The proposed solution is a tool position-based augmented reality concept which allows the user, i.e. the surgeon, to trace a surgical instrument over the newly created wound surface and which visualizes or gives feedback on the structures that lie directly underneath this surface. The first solution to this end is a visual augmented reality concept that uses pseudochroma depth visualizations to show the user which kind of vessels, that is either blood or urinary vessels, lie in which distance from the tooltip measured in the tool's axis direction. The second concept is an auditory display that maps the vessel type, so blood or urinary vessel, vessel density, and vessel distance from the tooltip to different sound parameters. We tested these concepts in a simulated simplified navigation task for which we placed a 3D printed kidney model in a simulated laparoscopic environment. In the evaluation task, participants were then shown a virtual model of the same kidney with some target points on subsurface vessels. Their task was to point at those target points in the physical phantom within the laparoscopic environment. Participants conducted these tasks under 4 different conditions, that is, with and without the visual support and with and without the auditory navigation. For each of these conditions, we measured the pointing accuracy, the time it took the participants to find the target points as accurately as they could, and participants completed the NASA Task Load Index questionnaire to assess the mental workload induced by the different navigation conditions. The results for the pointing error, i.e. the pointing accuracy, and for the NASA TLX ratings, so that is the mental workload, indicate that the visual AR support could significantly improve these measures, whereas for the audio navigation support, results are still inconclusive and the data point at potential interaction effects between the auditory and the visual AR support. The results also show that all AR navigation conditions increased the task completion time against the control condition. In conclusion, the evaluation results that I showed today are only proof of concept results with more evaluation pending. But with that in mind, visual AR seems to improve both navigation accuracy and the mental workload that is induced, while the audio navigation condition still requires further research into its effect on this task. And with that, I would like to thank you for your interest and your attention, and I look forward to our discussions in our live session on Friday.
And here we are in the live
Well,
session on Friday, and Fabian is here. And Carl's snuck in with another question, so we'll start with Carl's question. Is the visual workspace so cluttered that audio feedback becomes necessary, or are you thinking as an addition to the visual cue?
So the idea is ultimately that it would be an additional cue. We do have visual clutter in the operative scene, but we also have auditory clutter in the operating theater. So it is a noisy environment with beeping instruments all over the place, and also verbal communication between the team members. So in this very abstracted, simplified environment, we just wanted to look at how do the different modalities perform on their own and in combination to get a first feel for which of them might be a good idea. But when we look at the actual application and at the actual situation in the operating theater, we do have to consider both visual and auditory clutter or noise.
Great. Yeah. So maybe a follow-up. So your audio results were inconclusive. Do you have any ideas for how you might change the audio to make it more effective? Or perhaps there might be some learning curve involved in terms of being able to interpret the audio correctly, et cetera. What are your thoughts regarding your results with the audio?
So there are basically 3 questions that we're looking at and that are interesting points for follow-ups. The first one is the specific design of the audio feedback that we evaluated in the final test. So we did iterate through different audio designs, and then through some informal testing, this was the preferred. But there's certainly space for exploration of whether the specific design can be improved. The next question is the complexity of information that we encode in the audio feedback. So what we did here was we took 3 quantitative variables, or 1 qualitative, 2 quantitative variables, and encoded them in the sound feedback. And there's certainly an argument for trying to simplify that, to look at whether we can provide more abstract, simpler information and make the audio feedback simpler by that. And the third one is something that we didn't report in the results because it's sort of very exploratory, very thin data. But when we explored the data, it did look like the learning curve. So people had, I believe, 3 trials with each condition. So 2 training trials and then one in which we measured the final data. And it did seem that there was still a learning effect going on in the audio trials, a bit more than in the visual trials. But the data is way too thin on training effects and learning curves to make any definitive statements about that. But it is something that stood out to us and that we want to look at a bit more.
Great. We've got time. We've got an interesting question from Deb Fells, who's wondering how the augmentations that you've created might add or interfere with the tactile component of dragging the tool across the organ or the body, the tactile feel of the instrument interaction. What are your thoughts in terms of how that might interact, the information you're getting there?
So that is a very interesting question indeed. So one of the big challenges in laparoscopic surgery, or keyhole surgery is a common term for it, is actually that a lot of haptic and tactile feedback is actually removed that surgeons have in direct open surgery, where they might run their finger through the wound and feel where major blood vessels are sticking out of the wound, basically. I have not read anything, and in interviews with surgeons specifically about which information they use, which we did 3 years ago, none of them ever mentioned using sort of tactile feedback from running the tool over the surface. Thinking about it, I think it's unlikely that you can get this detailed structural information from soft organs with a very long removed tool that lies between the surface and your hand that actually detects the feedback. So I think I don't think there's much information that surgeons take from that.
I can see that. Maybe during the actual incision, you hit something hard, Okay, thank you very much, Fabian. We'll now move on to our next talk. And it's going to be, or Q&A is going to be delivered by Ji Li. The name of the talk is, the title of the talk is Bayes Gaze, a Bayesian approach to eye gaze-based target selection.
Hello everyone, I'm Zhi from Stony Brook University. I'll share our work Bayes Gaze, a Bayesian approach to eye gaze-based target selection. Selecting targets using eye gaze is challenging because of 2 factors. The first is the gaze tracking noise, and the second is that gaze-based interaction lacks an easy-to-use approach to confirm the selection, unlike using a mouse, where a user can confirm the selection by clicking a button. The most commonly used gaze-based target selection method is dwell-based target selection, where a user dwells at a target for a period, usually several hundred milliseconds, to select it. Specifically, for each gaze point, a target can accumulate the sampling time of the gaze point when the gaze point lands in the target. If the accumulated time exceeds the predefined selection time threshold, the target can be selected. However, in dwell-based target selection, the dwell time will reset after the gaze leaves the target, so the user needs to be highly focused on the target selection task, which may lead to eye fatigue. In this work, we propose Bayes Gaze. Instead of accumulating the sampling time directly, given a gaze point, Bayes Gaze accumulates the posterior for selecting a target, weighted by the sampling time. Specifically, we compute the posterior using Bayes' theorem, where the prior probability is computed by a frequency model based on the target selection history, and the likelihood is computed by a Gaussian function of the distance between the gaze point and the target center. Bayes Gaze also uses a threshold to determine the target selection. After the selection, the prior probability is updated accordingly. If we do not consider the prior information, that is to set equal probabilities for each target candidate, The Bayes gaze method is equal to the center of gravity mapping method, referred as the CM method. Another difference is that the CM method only maps a given segment of gaze trajectory to an object, and there is no target selection action defined. To use the Bayes gaze method, we need to determine 3 parameters at first, including a pseudocount in the prior, controlling the update rate, and the standard deviation in the likelihood, and the threshold theta. We adopted a simulation-based approach to determine the parameters. We first conducted a user study to connect the gaze trajectories for selecting targets. As shown on the right, we connected the gaze trajectories for selecting 1D target. The user initially put the eye gaze on the starting bar, then moves the eye gaze to the target and try to keep it within the target. The experiment is implemented on an Apple Pro, where the gaze tracking is enabled by ARKit of Apple. Based on the connected gaze trajectories, we simulate selecting a target at different locations in the layout. For example, the 3 figures shows the simulations for selecting the second, third, fourth target in 5 target candidates using the same trajectory. We recorded the target selection time and error rate in the simulation. We then use grid search to determine the optimal values of the pseudocount and the standard deviation, and we use the Pareto optimization to find the optimal value for the threshold, where we balance the success rate and selection time with equal weights, as shown in the left figure. We also optimize the parameters of the CM and dwell methods using the same approach. The optimal values of the parameters for the 3 methods are summarized in the right table. We then conducted a user study by using a 3x2x2 within participant design to evaluate Bayes gaze. We consider 3 target selection methods, 2 different target sizes, and 2 different frequencies of intended targets controlled by Zipf's law. In the experiment, we only evaluated the 1D horizontal target, as the horizontal bars are widely used UI elements on smartphones and tablets, for example, in the setting page. The left figure shows a screenshot of the experiment, where the user initially lands the eye gaze on the starting bar, then after the trial starts, the user needs to move the eye gaze to select the target shown in blue. The right figure shows the user is doing the experiment. The user study results show that Bayes gaze has the highest success rate and the lowest selection time among the 3 methods. At the same time, the CM method also performs better than the dwell-based target selection. Our research shows that incorporating the prior information and accumulating the posteriors are effective in improving the performance of gaze-based target selection. Thanks for listening. Hello, everyone.
Great, thanks, G. That was a really interesting presentation. We already have a couple of questions, so we can maybe start with Onoi's question, who says, interesting work. He was wondering how efficient the technique would be when there are several more closely packed targets instead of a 1D target layout.
So the question is asking for for selecting 2D targets.
For example, I believe, yeah, several more closely packed targets. I think so.
So actually, we didn't evaluate that in our paper. We only consider the 1D target selection. So I think our method can work also in the 2D target scenario. And so in 1D target selection, we use the likelihood function. We use the 1D Gaussian function as the likelihood function. And in the 2D target selection, we need to change the likelihood function to a 2D Gaussian function. So then we need to using the same approach to determine the covariance matrix of the 2D Gaussian function. So and the rest of the methods will remain the same. So I think based on that, our Bayes gaze method can work in the 2D scenario.
Great, thanks. So Carl has more of a technical question, interested to know whether ARKit is as accurate as, let's say, a very expensive piece of eye tracking hardware.
Yeah.
And the follow-on is, would more accurate eye tracking improve the technique further, do you think?
I think the technique can work with like high quality gaze tracking and low quality gaze tracking together. So I think the gaze tracking quality of the iPad is certainly a little lower than the commercial gaze-based commercial gaze tracking device. But one advantage of the iPad is that it is much cheaper than the other commercial gaze trackers, and so that people can easily to obtain it, and we don't need to buy an extra gaze tracking device.
Absolutely true. So Deb Fells has a question, actually a question that I had as well, which is, thinking about saccadic eye movements or twitching of the eyes and so on. Does your technique account for that? Does your model account for that, or is it impacted, more strongly, let's say, than a pure dwell-based technique? Could you maybe comment on the impact of random fluctuations of eye movement and how your technique handles it?
So I think the aim of our work is to try to minimize the effect of the eye gaze jitter, because in dwell-based target selection, if the eye gaze leaves the target because of the gaze jitter, the time accumulation will end. But in base case, we only consider the likelihood which is affected by the distance between the gaze point and the target center, and we don't have reset problem.
Great, thank you very much.
Thank you.
Okay, so that's it for questions for Xi. We're going to move on to the fifth talk of this session. Will be virtually presented by Hooman, who will be able to answer your questions afterwards. The talk is titled Simulating Mass in Virtual Reality Using Physically Based Hand-Object Interactions with Vibration Feedback.
Hello everyone, my name is Hooman Khosravi and I'm here to present the paper I co-authored with Katerina Etemad and Farmar Samawati. Our paper was titled Simulating Mass in Virtual Reality Using Physically Based Hand-Object Interactions with Vibration Feedback. Here we go. Virtual reality, or VR in short, enables immersive simulated experiences. Moreover, in VR it is also possible to interact with visual objects. However, virtual objects in VR do not have real masses, and it's difficult to sense their weight. Researchers have proposed different techniques to give a sense of mass to visual objects. One group of methods focus purely on vision-based illusions. For example, adding a velocity limit or tweaking the control display ratio between the user's actual and the user's virtual hand. Another approach is using haptic feedback, for example, using a motor or asymmetric vibrations to create a skin stretch effect. Now, our method for mass rendering is using a physically based visual hand. This visual hand is made from multiple rigid parts which are coupled using visual spring dampers with their corresponding parts in the user's actual hand. This allows a user to pick up an object without the virtual hands penetrating it. Now, picking up a light object requires less force. So when using this hand, you can use less fingers or maybe a bit more relaxed hand pose to pick up a light object compared to picking up a heavy object. We suspect such cues enables the user to get a sense of mass from the objects they're interacting with. One potential problem for this is, what if the two objects are both very light? It would be easy to pick both of them up, even though they may have a significant weight difference. Therefore, we propose a complementary sinusoid vibration feedback. When the user is grasping an object, the vibration renders at their index fingertip, and its intensity changes proportionally to the object's mass and acceleration. So the heavier an object is, or the faster they try to accelerate it, the more powerful the vibration will be. Also, the frequency of the signal modulates from 100 to 150 Hz based on the object's velocity. Our skin cannot detect the direction of vibration in these frequencies, therefore one actuator is sufficient to render the mass in all directions. To evaluate our method, we conducted a user study with 10 participants, in which they performed multiple sorting and comparison tasks using 3 different interaction modes. A control mode using a spherical cursor, the visual hand with no vibration, and the visual hand with vibration. For the sorting tasks, we split our mass range into a lightweight set and a heavyweight set to analyze the performance of our methods across a wider mass range. We can see the result of the sorting task in the form of 6 confusion matrices. From left to right, we have the results for the spherical cursor, visual hand with no vibration, and visual hand with vibration. Furthermore, the top row is for the lightweight set and the bottom row is for the heavyweight set. In these matrices, the higher the numbers in the diagonals are, the better the sorting accuracy is. Here, the green matrices show a statistically significant sorting results, and the red matrices means participants could not sort the objects meaningfully in those scenarios. As we can see, using the vibration feedback, participants were able to sort the objects in both light and the heavyweight sets. And with the hand and no vibration, they only could sort the heavier objects which are harder to pick up. Participants also expressed in the questionnaire they could perceive and discriminate objects' masses when using the visual hand with the vibration effect. Also, they found it to be more realistic and interesting in a gaming experience. But they were mostly neutral about using the visual hand without the vibration, even though data showed they could sort objects in the heavier weight ranges. To conclude, objects in VR do not have real masses, so we proposed using a physically based VR hand and a vibration feedback to complement it to render mass in VR. Using the physically based hand and the vibration feedback together, users were able to sort objects across a wide mass range and regarded the experience as realistic and interesting to see in a VR game. Thank you for your attention. That concludes my presentation.
Okay, Houman, that was really interesting work. I've got a few questions. I guess I'll ask one of them while we wait for other questions to come. So does the vibrotactile response take momentum into account? So how fast I'm lifting something?
So its intensity is proportional to the force that the user applies, which includes momentum as well. But in terms of velocity, we modulate its frequency according to the velocity. So in that way, when users like shaking it, it's very responsive. It feels a lot more responsive because you have that feedback for movement, basically.
Great. Yeah. So I guess a follow-on from that would be, what about so human physiology? So for example, if I'm picking up a 5-pound weight or flyweight, and I pick it up like this, there's less. I mean, I can detect its mass regardless, but it's more effortful to say pick it up like this as opposed to like this. Have you considered taking into account kind of the musculature or your human physiology in terms of the amount of feedback that you're getting to give a sense of strain?
That's a very good question. This study in particular was more focused on a simple pinch grabs and more simple movements in a smaller VR workspace. But even in that like smaller domain, what you said was still there. For example, how we pick up an object depends on how easy it is. Like if you're using disc grabs versus if you just like his hands is like this or versus like this is all like different. So the vibration could not really help with that, but what did help was the hand, the physically based hand, which since it's used a physics engine, it did account for those different in the anatomy of the hand and how we approach an object.
So maybe one more question from me. So, the first design, but like before you introduced the vibrotactile cue, you were sort of suggesting that, well, the number of fingers, let's say, that you use to pick up an object is somehow, or that you require to pick up an object is somehow indicative of its weight. So how do you, I guess, how do you influence a user to even try to pick something up with 2 fingers as opposed to, play it safe and just try to pick stuff up with their whole hand?
That is a good question. One of the phenomena we observed was sometimes for the because of the effect that you mentioned, users tended to use all of their fingers and a very strong grasp all the time. But that's why I think it did not perform as well during the lightweight set, because the difference that there were also light that you couldn't see any effect. But for the heavier ones, which were like closer to that threshold of what the hand could actually pick up, it still kind of showed of how still you could accelerate it, because if you accelerated it fast enough, it kind of dropped out of your hand, even though if you were using more hands. But kind of to fix that for that light objects, that's why one of the reasons we did complement it with the vibrations, that they sort of go hand in hand.
Great, thank you very much. That was really interesting work, Hooman. So now we're going to move on to our last presentation of this session and the last paper talk of GI. And it's going to be given virtually by Anna Ruda, who will be here to answer your questions. And the title of the talk is Embodied Third-Person Virtual Locomotion Using a Single Depth Camera.
Hello, I'm Anudito Britul from University of Nevada, Reno. Today, I'm presenting our paper, Embodied Third-Person Virtual Locomotion Using a Single Depth Camera. First, I'll talk about the commonly used locomotion techniques in virtual reality. Then I'll present our technique and the result of our user study. Finally, I'll talk about some of the limitations of our work and possible future research direction. Locomotion in virtual reality is often limited by the available physical space. For this reason, many VR applications incorporate some sort of artificial locomotion technique, or ALT. Common example of which are teleportation, walking in place, head tilt, etc. However, most ALTs are designed for VR experiences from the first-person point of view. VR experiences from the third-person view are rare. Unlike first-person, third-person experiences also have to decide on how the camera follows the avatar. Commonly used solutions to which are follow cameras and world-fixed cameras. Lack of presence and embodiment is often cited as a reason for avoiding third-person VR experiences. However, third-person experiences can help in creating a greater bond with the avatar, as well as allow the user to have higher spatial awareness. In our paper, we present a third-person locomotion technique that combines head tilt-based locomotion with real-time body tracking. This is done with the help of an Azure Kinect sensor. Our solution lets user make use of real walking for performing room-scale traversal. Larger distances can be traversed through head tilt. Full control of avatar's upper body is retained throughout the experience. We performed a 1x2 design user study with 14 participants. The 2 third-person locomotion techniques were traditional controller-based technique and our embodied locomotion interface. Users were divided into 2 groups to counter the order effect. Each user performed both tests with at least 24 hours gap between the sessions. In both cases, the users were asked to follow a path from start to finish while popping balloons and jumping over obstacles. Along with the collected performance matrix, each user filled out a usability questionnaire, embodiment questionnaire, and stimulator sickness questionnaire. First, we analyzed the test performance results. A one-way repeated measures MANOVA found a statistically significant difference between locomotion techniques on the linear combination of the dependent variables. Further, univariate test found statistically significant difference for total time, targets hit, and obstacles jumped over. There was no difference for percent of time spent on track. Next, for the qualitative results, we performed Wilcoxon signed rank t-test. We found statistically significant difference with accuracy, efficiency, learnability, and likability. For VR sickness, no statistically significant difference could be measured between the 2 methods with one-way repeated measures MANOVA. On the other hand, the embodiment questionnaire revealed a significantly higher level of ownership, agency and motor control, as well as embodiment illusion with our technique. To sum it all up, controller was found to result in better performance, which is in agreement with earlier findings. Familiarity and the significantly less effort required to operate a controller might be the reason for this. Controller also had higher usability scores. Again, familiarity can have contributed to it. Also, our experiment combined both locomotion and environmental interaction. So while using the embodied locomotion technique, the users had to move their limbs to interact with the controller. It was a simple button press. We also found some users struggling with the embodied locomotion technique because of the latency introduced by the Kinect sensor, especially while jumping. Finally, both techniques resulted in low simulator sickness scores. Unlike earlier findings where controller was found to cause VR sickness, we didn't find evidence for that. This could be due to the follow camera setup we implemented, which was identical between both locomotion techniques. The avatar thus might have worked as a rest frame for both cases and caused low amount of simulator sickness. As for limitations, due to the pandemic situation, the number of participants were relatively modest in our study. When it comes to the limitation of our technique, we should mention that it only works with non-IR based headsets. This is because the Kinect's IR sensor can get confused when there are other IR emitters in the room. And finally, although our technique is capable of locomotion with real walking, we didn't design our experiment to test it. This can be further investigated in the future. We'd also like to investigate the effect of point of view on VR sickness. That was my presentation. Thank you.
Okay, thanks, Aniruddha. So Aniruddha is here to take your questions now. I'll start with a question. I've done some work in motion tracking myself with older versions of the Kinect, and so the Azure Kinect I know incorporates it's a little bit snazzier, let's say, a little bit more accurate in some ways, or more robust to change. I'm wondering, did you find was it some aspect of the tool itself that facilitated development of locomotion interface? You know, in terms of the robustness of leg tracking, for example. Could you maybe speak to that a little bit?
Right. So basically, I've used the previous version not that much, but what I found is the model, I think, in this one is slightly more robust. So the tracking was obviously better. I cannot speak about the latency improvements. I think they're pretty much the same. One drawback is that with the previous versions, you could actually use multiple Kinect sensors on the same computer. With this one, it's still not possible. I don't know if there's any plan of changing that. Yeah.
So you said that in the talk that the results corresponded with prior work. Was that prior work for first-person locomotion?
Yeah.
Okay.
Yep.
Okay. So the third-person results are coinciding with the first-person results. Mm-hmm. Okay, interesting. So I'm wondering, have you tried other VR locomotion interfaces?
You mean in a comparative setup?
Sorry?
Like in a comparative setup, like with this new?
Yeah. Is that something you'd like to?
No, we actually haven't. We do plan on doing that, but well, obviously, like, all these studies are paused for now. But we do have plan for that.
Okay. And do you think that there may be, something about third-person locomotion that could be better served with some of the other techniques?
So there are certain cases where there are virtual locomotion techniques that combine third-person with first-person techniques. For example, I can think of a couple. For example, there was one paper called out-of-body locomotion. There was another one pretty similar to it. So basically, those combine, the locomotion part uses third person, while like you're interacting with the world, it tends to use first person. I think that would be a great user study to see like if our technique is better than that or not. Also, like there are some limitations right now, I've already mentioned. So I think that the latency is one of the bigger issues right now. We have worked on reducing the latency by incorporating the controller's positional tracking into this whole setup. That can help in reducing the latency. So yeah, we'll have to see.
But it really wasn't kind of interactive time. It was the lag was noticeable by most of your participants, I guess.
Yeah, especially like when you're jumping, I think it becomes quite noticeable. But like if you're interacting with like environmental objects, it's not that much of a problem.
All right. Well, great. I think if there are no further questions from the audience, we should thank all of our presenters for some really great talks in this session. And I will hand it over to Ali to close the session.
Thanks so much, Derek, for wonderful sharing. And I think we have a couple of minutes, but next session is gonna start, and Ahmed is gonna introduce our next speaker. Ahmed, the stage is yours.
Thank you, Ali. I think we can take 1 minute break while we're testing our cameras and everything, because our speaker just joined the channel. So we'll start in about a minute. Thank you. Welcome back. We had a very brief, about 1 minute break. Our speaker is ready. I'm delighted and honored to introduce our next invited guest speaker. And I've known her for many years, and really glad that she joined Graphics Interface, invited accepted our invitation. Dr. Shamsi Iqbal is a principal researcher in the Productivity and Intelligence Group at Microsoft Research at Redmond. Her primary expertise in the domain of attention management and interruptions. More recently, her work has focused on redefining productivity, introducing novel ways of being productive through leveraging micro moments, and balancing productivity and well-being in interaction design. Her work on driving and distraction has been featured in various print and digital media outlets, including the New York Times and MIT Tech Review. Dr. Shamsi received her PhD in computer science from the University of Illinois at Urbana-Champaign in 2008, and bachelor's in computer science and engineering from Bangladesh University of Engineering and Technology, commonly known as BUET, in 2001. Without further ado, let's hear from Dr. Shamsi Iqbal about her amazing research.
Thanks a lot, Ahmed, for that introduction. Let me start sharing my screen. Can people see it? Because
yes, we can see it.
Awesome, great. Thanks a lot. I'm Shamsi Iqbal, and it is my pleasure to be here today at Virtual GI to give a talk. This is also my first time being at GI, though I have had the intention of attending many times. It is a bit odd, of course, to be giving a talk to a computer, but almost after 16 months of practice, I think that we're getting used to it. And this is where I would have expected like polite laughter, and some people might be thinking, okay, what is she talking about? So that is my feeble attempt at making a joke. Anyways, so I'm going to start off this presentation by making this proclamation that hybrid work is the new future. Of course, there's nothing really particularly surprising about this proclamation. We all knew that this transformation was happening when we started to work remotely, teach remotely, learn remotely, attend conferences remotely, and even socially interact remotely. On the top right corner, my kids are doing basketball camp remotely, which I did not think was possible, but apparently that is also doable. So the flexibility that remote work offered to many people prompted top CEOs to make some pretty radical decisions to commit to being hybrid when the opportunity comes to returning to the workplace. And this is well grounded in where the trend is shifting. According to Microsoft's recent Work Trend Index, 66% of the leaders are considering redesigning their office space for hybrid work. 73% of the employees want flexible remote work options to stay. At the same time, 67% want more in-person work or collaboration post-pandemic. And this is exactly why hybrid future presents so many exciting challenges. There are two sides to it. We crave and need many of the in-person interactions. So as a researcher who has spent the past decade and a half studying multitasking, attention management, distractions, and productivity, and more recently balancing people's work, social life, and well-being needs, the core question that I am now grappling with is that what should an individual's experience be in hybrid work? This is not trivial, and this is because, to quote my good friend and colleague Sid Suri, productivity is personal. We may have similar aspirations and goals, but our paths to reaching those goals can be very different. And while the discrepancies in that experience have always been there, they have become far more visible during the pandemic. And so this is now why now we are talking or thinking deeply about how we can empower all individuals, because everyone's experience matters. To bring their best selves to work, people need to have the best support they can. I'm going to ask you to take a look at this slide with the lens of accommodating a large variety of personal circumstances that make the playing field extremely uneven. And some of these include considerations of how can individuals get work done within the constraints of their specific flexibility needs? How does work get recognized and valued, and especially when people are coming from different kinds of circumstances? How can individuals be supported in their well-being needs to manage their energy so that they can continue to do high-quality work? And how can we ensure individuals belong and have equitable experiences regardless of where, how, and when they work? So to this end, I want to deliver two key points. First, the definition of productivity has evolved. Rather than being about how much we can churn out in a given amount of time, productivity is gradually becoming about creativity and innovation. John Friedman, who is a CVP in Microsoft Design and Research team, termed energy as the new time management and connected energy as a conduit to productivity, which he sees as a function of creativity and innovation. And which then brings us to the equally important second point, well-being. Well-being is now the new currency, not only to get us towards healthier lives, but overall better selves. And this is because well-being is well beyond wellness. According to Calvo and Peters in their book, Positive Computing, constructs such as motivation, engagement, self-awareness, empathy, altruism, compassion, all are connected to well-being. While it's perhaps clear how the former three, like motivation, engagement, and self-awareness, are connected to individual productivity, the latter three, empathy, altruism, and compassion, are connected to more collective benefits. And this is why individual gains from balancing productivity and well-being can help organizations, workforces, society to become collectively creative and innovative. So this means that organizations too must care about well-being, because if we want to empower people, organizations must be brought into it as well. So I'm going to go back to the slide where I talked about empowering people. These are the problems that I constantly think about, and these are not problems that are going to be solved in the short term. I'm going to focus on this one because this is where we may have some solutions that we can bring in from our past work that might be applicable in the short term. So the core question that we are trying to answer here is that how can individuals be supported in their well-being needs to manage their energy to do high quality work? Of course, there are many ways of doing this. I'm going to provide 3 possible directions in how we can start doing this. So let's start with the first one, maintaining boundaries between work and life, which is something that always existed, but it has become much more important in the current scenarios. The second one is about integrating well-being needs during a workday. Again, as we're working remotely, this has become far more important than it was ever before. And the third one is something that we're all experiencing as we're remote working, interleaving work and personal activities. So let's start off with the first challenge. How can we maintain work-life boundaries? So at the beginning of the pandemic, Mary Chernsky, Jamie T. Van, Gloria Mark, myself, Gina Su, we wanted to launch a survey trying to understand how people maintained their, or how people adapted to remote work. And what we found from the data that we collected, and we found that a regression model on boundary control, which indicates how much people are able to maintain the boundary between their work and personal life, we found that work-life boundaries were worse with higher job demands, less sense of control in work, and more children under 18 in the household, which explain 20% of the variance. Again, productivity is personal. So I'm going to hone into one particular aspect of work-life boundaries. In the same survey, we found that a lot of people told us that they were happy to work from home because they didn't have to commute, which actually makes a lot of sense. Who wants to be in traffic 1 hour each way, where they certainly could put that time to good use if they just didn't have to commute? But there is a flip side to this coin. The commute does serve a purpose of putting some distance between your personal life and work life, both temporally and physically. And that is when kind of like these mental transitions between your work life and home life happens. So again, this is not a old problem. This is not a new problem. This is a pretty old problem. But again, it became far more important during the pandemic when we don't have that transition, that physical or that mental transition time anymore. So this led us back to some 2017 research that we did. And this research was led by Alex Williams, our intern, who is now a professor at University of Tennessee. And for that research, we were interested in how we could help people mentally transition between home life and work life and help them with disengagement at the end of the day so that they could be present with their family, with their personal life needs when they went back home. And similarly, when they came back home, how can we help them re-engage so that they can continue to be part of their work life without having to worry about lingering thoughts of home at the back of their mind? So we went back to literature in organizational behavior and occupational health psychology, and we found that, again, adequately disengaging at the end of the day and re-engaging the next day has positive impacts on productivity. So what we did is that we developed this tool, this digital assistant that would help people, that would ask people at the beginning of the day a couple of questions around how they felt about that day, how they did. Well, there were 2 questions, there were 2 sides. So there was one mode was the task-centric approach. And in that mode, the digital assistant would ask the person, what did the person get accomplished that day and what did they want to do tomorrow? And that was a disengagement part. And for the re-engagement the next day, that task-centric mode would ask the person, yesterday you said that you wanted to do X, do you still want to do it? And what is the first step in doing that? That's kind of like helping them get started. There was a parallel, more reflection-centric mode. And in that one, at the end of the day, the agent would ask, how did you feel about today and how do you want to feel tomorrow? And for re-engagement, it would ask, yesterday you said you wanted to feel X. Do you want to still feel that? And what is the first step in doing that? So what we found is that by interacting with this digital assistant, 61% of the participants felt more productive after a week's interaction compared to their baseline data. And then there was about a 12 to 15% increase in their self-reported productivity. But what was also more important is that there were some differences between the task-centric approach and the reflection-centric approach. On the task-centric approach, people got more done in the first hour of the day compared to the baseline week. But then it kind of like it tapered off, and it was similar to what was happening in the baseline week. For the emotion-centric reflection one, people reported similar ramp up during the first hour, but throughout the day, they reported sustained productivity. So this was, again, these were promising results, and it was promising because of the simplicity of the approach. This came back in a different way during the pandemic. And so folks at Microsoft were really thinking about, okay, so this is a growing problem. People are reporting that they are not able to transition back and forth between work and their personal life. And is there something that could be done to help them? And so this is where the virtual commute feature was kind of like conceived, and then it is rolling out. And it was based on this work that I just reported. And right now the feature is doing just one part of it. At the end of the day, it helps people kind of like walks people through a number of steps, helps them create to-dos so that they can kind of like download their lingering thoughts onto the tool, which reminds them the next day. And then sometimes just helps them through kind of like some deep breathing exercises and other stuff, which wasn't part of our original study, but it's actually quite useful. So this is an example of how research from the past that was conducted in a different context becomes applicable in a completely different context that we did not actually plan for. So I'm going to move on to the next challenge. How can we integrate well-being needs into the workday? And this is, again, very important. As academics, as people who are kind of like type A type of people, we want to keep on working, we want to keep on achieving. But this also comes often at the detriment of our own health, own well-being, and so on and so forth. So one of the things that we have been really interested in over the years, and especially partnering with Mary Sharonsky and Gloria Mark, we have been interested in understanding how people's interaction with non-work related technology helps with their productivity and well-being. And in particular, while most studies in the past had focused on characterizing focus and lack thereof because of distraction, there hasn't been really a lot that have looked at the effects of turning off distractions completely. And when I say distractions, I mean the interactions with non-work related activities. So what we did is that we designed this study where we had people use a tool called Freedom to block non-work related websites for 1 week, and we collected data from a baseline week. And we collected data about people's subjective perceptions over both weeks. We looked at focus and engagement using the cognitive absorption scale. We looked at productivity across multiple dimensions, including how effective people felt they were, how satisfied they were, how much they felt that they were engaged, the quality of their work, and so on. We collected workload data using the NASA TLX. We collected data on individual traits using the Big 5 personality scale. So what we found was interesting. We found that, not surprisingly, people had higher perceived productivity and they felt that they were able to focus more. But it also seemed that time passed slowly for them. So most likely they were actually not getting into flow. They also reported that they enjoyed work less. Which suggests that the importance of taking breaks and getting rejuvenated is important so that people can be productive and be happy about it. It turns out that the effects are highly individualized. People who report to have less self-control actually benefited from not having distractions. And these are people who reported that they were able to. So this is an example of how an interruption can actually occur during a talk. So yeah, just getting back to what I was talking about. So there were two types of people who are highly susceptible to distractions. These are more impulsive people, and they actually found that they could do work better. And people who were more conscientious and who were less susceptible to distractions, they got more done. And they also got very stressed because usually they were the ones who were able to schedule breaks and be very much organized about it. And once you take that control away, they could not deal with the stress that came with it. So this kind of like encouraged us again during the pandemic to think about the importance of breaks during people's day. And this paired with the survey results that we had about how difficult people were finding it to schedule breaks during their day. How can we help them? So we basically designed a Outlook add-in that would analyze people's calendars and then would find in empty spots where it could automatically insert time for focus, time between meetings, time for well-being breaks, and time to plan for the day and disengage. And this was kind of like taking literature from the past and as well as some recent work that we had done. So what we found is that time committed on the calendar protected that time from others, which became very important during the pandemic where calendars are blocked with meetings, and also signaled a commitment to self to follow through. We were really interested in how people were using these times that the tool automatically created. And we found that 48% of the focus time entries were used, 37% of the well-being breaks were used. And people in general, even though at the beginning they were a bit hesitant to kind of like use these times, once they start using these times for themselves, they saw the benefit because they were worried that they would actually not be as productive. And it turned out by taking time away for their personal needs, or they're taking time for doing physical exercise or time between meetings, these all help them be more focused when they went back to work. So challenge 3, and this is kind of like interesting because this is almost at odds with your work and life boundaries. And this is again, personal productivity is personal. Not everyone is able to create this very clean separation between work and life. And so interleaving becomes something that is very important. In the survey that we did, that everyone is interleaving personal and family responsibilities and work, especially people who have caregiving responsibilities. It was found that everyone had work sip into their personal time and personal work sip into their work time. So we know that user attention is fragmented, and it became even more so during the pandemic, but we are also used to taking advantage of small moments. We have our phones with us. We have different capabilities on the phone that allow us to do things in chunks. So this is not something that we are necessarily, it is not something that is new to us. And so this brings us back to microtasks and microproductivity, which is a concept that Jamie Tevan and I have been working on for a while. And the idea behind microtasks is that these are perceptual units of behavior. You take a big task and you decompose it into smaller tasks, and these tasks can be done fairly independent of any kind of context using short moments. And the concept of microproductivity is basically the transformation of these bigger tasks into a series of smaller tasks. So microtasking in today's world, where does it happen? Well, all of us actually do it. We do it when we are checking email on the go, we are browsing on the go, we are doing IMs, we are doing to-do lists, we are taking advantage of the time between two talks to quickly check our email. So we are already kind of used to this. But what we are not used to is thinking about complex tasks, such as writing a document or creating a PowerPoint presentation or doing coding, because these complex tasks are not compatible with micro moments. But again, in the hybrid work scenario, microproductivity comes back. And because our time is fragmented and we are continuously switching back and forth, this is an area where we can actually start thinking about how we can leverage the different devices that we have at our disposal for doing these kinds of interleaving. And that's why I look at the smartphone as an amazing example of where we could do little chunks of tasks without having to get fully engaged. And the smartphone affordances of limited screen real estate and limited attention usage, it also kind of like prevents us from getting too much sucked into it. So I'm going to give a couple of examples. So you could imagine that there is a Word document that you could edit on your phone. It is a painful task to edit Word or edit any kind of document on your phone. But we created this task engine called Playwright that could analyze a person's Word document. Then it would identify the microtasks and then present those microtasks on your phone. And these were tasks that were independently shown to people, very short tasks that could be done in 10 or few seconds. And then the results would be then integrated back into the Word document. And that way you could continue to do work in short bursts while even you're away from your desktop device. So similarly, you could imagine that, well, work microtasks could be embedded in other tasks. And here I use the example of some work that we did with Nathan Han, who was an intern with us at that time, where we had integrated microtasks into a person's Facebook feed. The goal wasn't to ruin Facebook for people. We just wanted to see how people would react to seeing a work task in a non-work related setting. What we found is that, well, people ignored the work tasks for a while. And in our experiments, it was about 2.5 minutes. And then once they started seeing them, they would do a few and then they would go back to their browsing and they would come back, and 20% of the cases they would return to the document. So this is a kind of like a lightweight way of engaging with activities that are backgrounded. And again, in a remote work, in a work from home scenario, you could imagine that you could integrate these kinds of microtasks if you need to during a non-work task. Then finally, some other work that we had done, we had looked at how we can integrate work-related tasks during a continuous attention task, such as driving. And this is a driving simulator experiment that we did. And we were curious that can we use a speech-based interface that has an idea of a person's cognitive load during driving and can safely engage with a person to help them kind of like continue with their productivity-related tasks. And what we found that, again, as expected, this is very much dependent on the driving task. There are certain moments in driving when, for example, in real life, you can engage in a conversation with a passenger. So similarly, you can engage with a conversation with an assistant and you can get certain things done. But again, it depends a lot on how you break down the task so that they're not cognitively loading on the person. So again, examples that are not for everyone. Productivity is personal. A person who has the luxury of having long bursts of or long chunks of time where they can get work done probably doesn't need any of these. But think of the mother who is doing 2 jobs and taking 3 kids different places. They need that kind of flexibility. And this is where these kinds of opportunities and workflows come into play. So I'm reaching the end of the talk, and I would like to leave with a few takeaways. I want everyone in the audience to think about how your research, your design can help empower individuals. What new innovations in design and technology can help support new modes of working while also prioritizing well-being needs? More importantly, what societal changes need to happen to make it acceptable to prioritize well-being so that we can prevent burnout and help people still bring their best selves to work? And how can we ensure that the need for flexibility in how we work does not disadvantage certain populations? We do not want to leave anyone behind because of where, how, and when they work. And that's all I have to say. Thank you very much.
Thank you, Shamsi, for the amazing talk. Your research could be summarized as kryptonite to procrastinators. So I'm a little bit scared of everything you're doing at Microsoft Research. We have some questions lined up at our YouTube channel. Dave Phelps asked that, did you ask any people?
Let me first stop sharing.
Okay.
Okay. I might have lost my sharing. Oops. I think I may have lost the controls. Anyways, that's fine. I can see you. Go ahead.
Okay, no problem. So Dave Phelps asked that whether your research involved people with disabilities, particularly people who are deaf, blind, and have reading disabilities. She writes that, I think there are considerable differences from hearing, sighted, and so forth people's experience.
That is an excellent question. While our research particularly did not look at the experiences of people with disabilities, we have a big team who are looking at these kinds of challenges, and especially, as I said, we want to bring everyone to their best selves. And so we have been closely working with the accessibility team to kind of like think about what should we be thinking about in the experiences that we develop. I mean, again, some of these things, sometimes speech-based interfaces work for some categories of the population better than others. Sometimes we need to kind of like ensure that they're screen readers and all of those things. So these are things that we are thinking about deeply. And thanks for bringing this up, because I think that this is a really important question.
There's a question from Fanny who asked that, can you tell us your thoughts about the cost of continuously switch context when doing microtasks that are unrelated?
Again, a really good question. I think that the biggest cost of switching in general is that the resumption cost. So when you switch from one task, you leave it and then you come back to it and then you have to resume it. And so that takes up some time, that takes up some effort. They're unrelated. The cost of switching between unrelated tasks are mostly when you have to resume more. So for example, there's a difference between tasks depending on when you switch. If you're switching in the middle of something, that is very different because you have to resume more. And then when you're at the end of something, that's where you don't really have lots that are kind of like stacked up, and it becomes slightly easier in terms of resumption. In terms of microtasks, I think that one of the goals that we do have, and it's kind of like one of the challenges also, is that how can we design them so that there isn't really a lot to resume when you go back to the task that was interrupted. And so it's kind of like, it depends on how you can develop these as being as context-free as possible, so that you can easily engage with them, easily disengage with them.
Right. That makes sense. We have a question from Carl Goodwin who asked that, I agree with we all do microtask, but if support for this was built into Teams, for instance, isn't that a huge risk that they now become required? For instance, your boss asking you have only done 5 microtasks today.
Yeah, I think that this goes into kind of like surveillance, and I mean, how do people show? Well, I mean, lots of people are really concerned about how they show productivity, and especially in remote work, and then it becomes much more quantifiable. My argument to that would be is that microtasks should be at the personal level, as with many things regarding productivity. I mean, my productivity reflection or the way that I do tasks, it shouldn't matter. I mean, people should be, instead of measuring things like that are tractable, like how many microtasks you are doing, I think that people should be measuring the outcomes. How I get to that outcomes, I think the outcome is less important. But this is also a great question, because there is always a danger of trying to quantify these things, and it could be used to the detriment of people.
Sounds good. Thank you, Shamsi. That's all the time we had, unfortunately. If you have time, maybe you could go to our YouTube channel and see the other questions that are posted. If you have time, if you respond to them, that would be great.
Yeah, absolutely.
Thank you again for accepting our invitation.
Thank you very much for the opportunity.
No problem. We're really happy and honored to have you here. Let's move forward with our next talk. Ali, whenever you're ready, the floor is yours.
Right. So it's my great pleasure to introduce our next invited speaker, Dr. Quang Nguyen, who is an assistant professor in the Department of Computer Science at the University of British Columbia. He's a member of the Computer Vision Lab there, and also CADA, UBC's Center for Artificial Intelligence Decision Making and Action. The ultimate goal of Quang Nguyen's research is to improve the quality of human life through smarter computer vision systems. He has been publishing some very impactful work that connects visual geometry with machine learning and allowing for a better understanding of the real world, with numerous applications for autonomous vehicles, drones, robots, and augmented and mixed reality systems. He's also part of the organizing committee for CVPR 2023, which I believe will be held in Vancouver in 2023, hopefully, physically. So thank you very much, Kwang Mu, for being here with us at GI 2021, and please take the virtual floor.
Thank you so much, Melis, for the nice introduction. Let me try to quickly see if the spotlight feature would work. I've heard that there's a delay, so I'm going to assume that it works for 20 seconds or so, and then try to change back to the presenter view if necessary. So today I'm going to talk a bit about our most recent work, which we named Correspondent Transformers. So it's a bit of a work about how we match things in images, and I will actually go into a little bit in depth about how we try to solve this thing, which actually relates a lot into graphics application later on, as you will see. So, oops, sorry. Yeah, you can see that I have a lecture set up and be using it, and that's why the annoyance. What we're interested in our group is mostly something about geometry. So what we want to answer is basically this question, given images and other sensory inputs, that whatever we can get our hands on. So here you can imagine like you go to a place with these sort of a building, and then let's say you took photos of that building. And now given these photos, can we actually understand how the world looks like in terms of geometry and how we took those photos in the first place? So in order to do that, we have to relate between images. But the benefit here is that once we are able to do that, we could create autonomous agents and all these things that could interact with the environment. And of course, there are many methods and many questions revolving around this. But today, the question that I'm going to talk about is based on this very traditional way of getting 3D geometry, which is finding points that correspond between these two images that you see here, and try to see if we can triangulate, and through these triangulations, get the idea of how those points in 3D are located, as well as how they were projected into your 2D images that you have. And of course, the core question that you need to answer in order to do that would be basically this: how can we find points which are the same across different images? So that's why we are interested in this question in this work, which is, where does the point go from one image to the other? So and of course, in this work, what we're going to do is, as many works do nowadays, we're going to use some machine learning things like the transformers here. But the very particular thing about this work that makes it unique is that we're going to basically try to transform this basic question that we're trying to ask into a mathematical formulation and into a machine learning framework that directly models this question. So like this. So imagine that COTR, the whole capital thing, is a function that is parameterized by a set of parameters, what you would call like network weights, right? And then what we're trying to do here is basically learn a function that does the following, which is taking two images over there as somewhat the conditioning variable, and then given a certain Cori point or Cori coordinate in one image, it just spits out the corresponding point in the other image. So it's really a framework that answers the question. So just turning that question into a machine learning framework is all we are doing here. But the very important thing that this sort of a view brings, this functional point of view brings, is that we're able to actually unify what we call sparse correspondences and dense correspondence problems. For example, for the sparse correspondences, all you need to do is, let's say we have that function, then all you need to do is plug those images in and ask Cori points that correspond to the points that you're interested in. For example, the red point over there that is related to the camera motion, or blue points over there that are related to some object motion, or maybe even green points that correspond to the pose change of something in the scene. And well, of course, the outputs are going to be the correspondences, and that's directly your answer. Well, that's normal. But another interesting thing is if you were to then plug in a mesh grid of coordinates as input to this COTR function that we're going to learn, then the outcome could actually be a dense correspondence map, like an optical flow map. It will be able to map for every pixel, where does the pixel go into the other image. And of course, if you have that, you'll be able to warp one image to the other image. For example, here you're warping the image on the right to the view on the left, right? So it's sort of a unified view of how we can view correspondence problems. And you can imagine that it's going to be quite useful for many applications, which I will show later. Now, the question becomes then, hey, we have this new view of how we view the correspondence problem, but can anything solve it? And why haven't people done this before? Well, the answer to that is quite simple. We actually need a very specific architecture for this to actually happen. So in fact, we need to consider what the complicated function, COTR function, needs to do, is that it needs to be able to relate between pixels on different images, right? Because if you are trying to find correspondences, you better be able to relate, for example, points on the window on the image on the top left should correspond to some other point on the windows of the image on the bottom left. So to do that, there is a sort of a trendy architecture that works really well for such relationship building called transformers. And we are, and the whole reason that this view works is because of that. So in more detail, what we do is, as usual in how people use transformers in computer vision, we first build these low resolution feature maps from like off-the-shelf backbone networks like ImageNet, trained VGG, or ResNets. And then what we do is we concatenate the two images side by side. This is somewhat very weird at first, but it's something natural, and you need to do it this way because the way that the attention is built in transformers is as if you were relating words and sentences. You need to actually have them side by side so that the architecture itself supports actual relationship building between the points in the images. So here, basically, we're relying on the self-attention mechanism in transformers to force our architecture to figure out which points in one image are related to which points in the other. And then once those relationships are built, we use them as context, and then we input the query point encoded into some positional embedding as usual these days. And as that gets fed into the transformer, it will then be related again with the relational context that we have, finally giving us the coordinate output as shown here. And one great benefit if we do it this way is that we are able to have a functional form of the correspondence problem, meaning that we can actually apply this to any modified version of the image that we're interested in. For example, more specifically, you could actually run this correspondence finding algorithm on a set of images, and using the results that you have, you could actually zoom into the regions that are potentially corresponding and then get even more accurate results. So here you see, for example, the points on the left two are being zoomed in to the points on the right two. And of course, we had a look at whether that sort of a zooming in heuristic actually helps. And this is a histogram built with one of the errors. When we look at the errors at each different zoom level, and we accumulate the statistics, it looks like this. And you can clearly see the trend of the correspondence estimation errors becoming more and more skewed towards having lower and lower pixel error to the left. And this is somewhat obvious, but it was really nice to check. And the important thing in this sort of a strategy is that if you look at the architecture we had before, we're actually using a lower resolution feature map to use transformers, because unless you do that, you're going to have memory issues because of just the pure memory requirement of transformers. Now, this creates a sort of a bottleneck in the spatial resolution that the transformer sees. But if we are to zoom into these regions, that problem effectively gets alleviated because, well, we are compensating for the fact that we're going to generate low resolution feature maps here. Okay, and of course, in addition, this zooming in strategy gives us another benefit, which is that we are able to look at the trend of how these estimates are coming out of our transformer. And if we look at those estimates and they're sort of drifting around everywhere, that actually is a great cue for us to know whether the estimates of our network is trustworthy or not. So we actually look at that and filter out points that make no sense. For example, if the standard deviation of the points and the errors that you're getting is just too large, then you can just safely disregard that point and just use the neighboring point correspondences to actually interpolate back this correspondence result. And of course, another thing that you could do is you could try changing the images left and right. Again, this is functional, so it doesn't stop you from actually changing the order of the images, and you can just query one point to the other image and then try to query it back. And if it doesn't form a cycle, that's also another cue for figuring out whether the network is knowing what it's doing or not. So these are some ways that we could actually filter out uncertainties as well. So that's how the whole pipeline actually does inference and estimates correspondences. Let me just talk a little bit about how we train it. I promise you this slide will be the sort of the only slide that has math, so don't fall asleep just yet. What we're doing is not fancy or too difficult here at all. So here, you see on the top, what we're doing is basically saying that the coordinates that you map with correspondence transformers, you should just simply be the same as the ground truth correspondence denoted as the x prime over there when you estimate it with the network. And of course, we're going to try to minimize this loss and change by changing the parameters of the network. And another additional loss term that we add is actually coming from the heuristic that we did before, which is saying that if you map one image or one point to the other image and try to map it back, you should form a cycle. So this is somewhat a regularization term we have to facilitate training a little bit more. And to train that, as you might have noticed, that you need a pixel level correspondence, right? So our losses are basically saying move one pixel to the other and make sure that that movement, that correspondence is accurate. And therefore, we need a data set with large amount of pixel-wise labeling and various changes. And what we use is something called the megadepth data set. And it's a structure from motion-based data set created with phototourism data. So you see there's a whole bunch of landmarks, and you see that there are some depth maps over here that allows you to map pixel level at a pixel level from one image to the other. And the catch here is that not all of the scene will have depth information, because not all of the scene can actually be used to build 3D. For example, let's say some person just walked in front of the camera in one image and it's not there in the other image, there's no chance of us actually recovering the depth. But still, this is actually quite good enough so that we can use the points we have the depth for to train our method. And this is the only data set that we use, and this is the only training that we ever do. And what we do is once our method is trained in this data set, we use it for all the other tasks. So off to some results that we have here. This is, of course, we trained on phototourism. The first thing we do is test on phototourism. And this is not on the megadepth data set. This is actually a different scene, although it's an outdoor scene made from phototourism similar to megadepth. And these lines over here are the correspondences estimated by COTR between the two images. And the green ones are the ones that we have correct correspondences. The red ones are the ones that we have wrong correspondences. And even the red ones are not too bad. But you can see that there are many, many, many green correspondences, meaning that we are going to be able to estimate the camera pose difference between these to images, although they are taken from different times of days, different seasons, or even with different cameras. And the accuracy of the camera pose estimation is about at the same level as state-of-the-art methods using key points. And now, well, that's not too surprising because you trained to build correspondences and you trained it for phototourism. Now here's the interesting part. So what we did again is taking that network that we have and we tried to estimate dense optical flow for the KITTI dataset, which is a dataset where you have images and then it's a driving scenario and you're supposed to estimate the flow. And this is the flow that we got at the middle. You can see that it's not that bad, or actually it's quite good. If you look at the error map you have on the top, besides the very fine edges on the car, the error is not too big. I especially like about where we have here, where you have two cars going in opposite directions, and we get the flow quite properly here. And what is important to note here is that we never trained for these scenarios. Our scenes are more like phototourism, meaning that most of our pixels that we use for training are coming from buildings, not cars. And still, it seems to work quite well. So when we look at this in terms of quantitative results, because qualitatives are always something that you can cherry pick, we did an analysis on the entire validation set of KITTI. And this is sort of the result that we get. Compared to various other methods, we do get state-of-the-art performance when it comes to evaluating the trustworthy points. And another thing that we did was we included points that were untrustworthy, and we just interpolated the whole scene with some random sampling and simple triangulation and interpolation. And it seems that doing that also gives us pretty much on par results with the state-of-the-art, or slightly better, but I would just call it on par. And this is another data set, not the optical flow data set, but this is something called ET3D, which is a bit more like handheld scenario of a video. And the rate here is how many frame difference do you have between the two image pairs. And in this case, this is for sparse face evaluation. And then here we get much better results than the current state of the art. And one thing I want to emphasize here is that for the raft, or for the optical flow methods like raft over there, those are for cases where it's like in the same time frame and same camera and so on and so forth. It's not for like different times of day, like day and night scenarios, which our method actually was trained for and still works as good as them, if not better. And this is actually one of my favorite slides or favorite figures from the correspondence transformer work that we did, which actually shows that transformers matter. So here, the third column over here is when we replace the transformer architecture with a simple MLP, multi-layer perceptron. Because the framework of asking the network where the point goes could be implemented with any type of network architecture, right? And so MLP is the easiest thing, so we tried it, and it turns out with an MLP, you sort of get a global motion of the scene, but not exactly correspondences. For example, you see the dome over here moves from right to left compared to the arc because of the perspective change. And that motion or that correspondence cannot be modeled well with the MLP on the third column, whereas with the transformer, it is done quite well. And this is still phototourism. So I have another example that is way different from phototourism. This is what the first author student actually quickly tried, and it worked so well that we put it on the paper on the last day of the deadline. Yeah, we got some lucky results here, which shows that if you try to warp the source image to the target using optical flow with our method, even when you just have water bottles and you switch the order, you can actually still do that. And again, I want to mention that this scene over here, in no way looks like phototourism, but it still works. So it really shows that using our architecture and our framework, correspondent transformer actually learn to correspond. So here are some demos. For example, what we are going to do is we're going to just track that frame and then augment some other photo of it. I have no idea how this was chosen, but the student actually seems to like this photo. So we could do that. That's not too hard. We just need the 4 corners to be matched and followed. And of course, I mentioned that we want to do this to get 3D. So here's an example of us trying to get 3D with correspondence transformers. We use the 2 images, and once they're calibrated, we can actually create a dense warping and create 3D models like that. And here's another example, completely different background. So the only thing common is the things in the middle. So that's what you get. And another interesting thing that we tried is, hey, since it seems to know correspondences, can we actually run it on something very, very different, like human faces? So what we did is we detected these things with an off-the-shelf landmark detection algorithm, and then we tried to track it throughout the video, and it seems to work quite well. So these points are actually just being tracked from the first frame, which was quite impressive. And finally, since our title is Transformers, we got this Transformers video clip from YouTube and tried to track that part over there. I marked as red. And to our surprise, this also worked. So really, you can use correspondence transformers to build correspondences on transformers as well. So in a nutshell, what I've shown is a framework that can solve both sparse and dense correspondence problems. Importantly, train once, apply everywhere. If you're thinking of Java, yes, I sort of got that phrase from Java, but it really works for our case. And here, again, the transformer architecture seems to be really critical, at least according to our observations. So we are interested in solving this matching problem, but that's not the only problem that we're interested in our group. We are interested in basically all the problems arising in this setup over here. And what we like to do, and a short ad for other questions, there are works that we show at CVPR, for example, where do we look at, or how can you render from 3D to 2D in an effective way using neural rendering, using decomposed radiance fields. So I would also invite you to check these out at our CVPR, which is happening in just a month. But I think that's all for my talk today. And of course, I would like to thank all the collaborators I'm presenting, but I would say it's the blood and tears of Wei and the far left, and with help from my fellows collaborators at Google as well. So all the code and things are already available online, so do check it out as well. Thank you, and I'll be happy to answer any of your questions.
Thank you so much, Hwang Woo. Really cool work. We have a couple of minutes for a few questions. A reminder for everyone on the live stream to ask questions using the chat. And while we're waiting, I'll get things going. It's interesting to see how the large-scale pixel-wise ground truth that you had in the Megadeth dataset enabled this work. And yeah, so I was wondering, were you in any way limited by the properties of that dataset? Is there some dream that you have of what a next-generation dataset for work that, like what you did, or future work would look like?
Yeah. So yeah, it is sort of I think a limiting factor. We did find that some of these correspondences that we get in our data set are not exactly pixel accurate. We had some look, and then there were some misalignments. Especially, it was really tricky for us to at first get this pipeline, reprojection pipeline to work properly, but we finally managed it. So one of the things that we're always interested in is perhaps we could bootstrap this, because these data sets are created with more traditional means, and we have better methods that now give us more accurate alignments and more accurate matches. I'm really curious whether this can actually go back to the methods data set and then enhance that and then keep on enhancing. But that does require a lot of resources, so I haven't got my hands to try it yet.
Got it. What do you think about synthetically generated data? Do you think that you could achieve similar results if you relied purely on simulated depth and pixel-wise ground truth?
Yes, so that's actually a great question. And maybe it's a great opportunity for me to also put an ad that one of the things that we're doing in our group is something called the Image Matching Challenge. And a part of that, one of our organizers have created a synthetic data set that is realistic. And we haven't had a chance to try it on that yet, but from what I can see, the rendering qualities are so good that I can't really distinguish them too well from like real images. So that would definitely be another direction as well.
Yeah, sounds like there's some interesting stuff that could be done there as well.
Yeah, so like trying to figure out whether the limits of the method currently that we have is because of the method or the data set is really an interesting thing that we would like to answer.
Right. So I think we don't yet have any other questions on the chat. And we are almost at time, so we can probably wrap up. Thank you once again. Thank you from me, and thank you from, I'm sure, all our virtual audience as well. Virtual applause coming from everybody. Thank you, Kwang-Woo, for taking the time, for joining us here at
Thank you for having me.
Virtual Graphics Interface 2021. Really cool work. Thank you so much.
Thank you.
Okay, so our next session is about our achievement awardees, and I'll be very happy that Brian is going to introduce them to you. The first one, I think, is Pierre Poulin. So Brian, please, stage is yours. You're muted.
There we go. That's the most common phrase of 2020 and 2021. Did you know that? Well, welcome everybody to the Achievement Awards session. I'm Brian Wyville. I'm the chair of the Achievement Awards, and I'm happy to say this is my last year, and I'm handing over to Michael van der Pan after this. Our two Achievement Award winners, one from officially one from each of HCI and graphics, is actually slightly different. First of all, we have a graphics person, we have Pierre Poulin, and then we have Tamara Munzner, who very much bridges the gap between those two disciplines in her work on visualization. So I'm very proud to present Pierre Poulin. I knew his supervisor well, and he was a young upstart for many years and developed as a first-class researcher, as we all expected. And after 30 years, he has made an enormous number of contributions to computer graphics. The list is very impressive. It's all on the web page, but it's things like anisotropic reflection models, linear light sources, virtual relighting, animation of water in its many forms, procedural modeling of buildings, surface weathering, image-based modeling, and the list just keeps going on. A huge diversity of areas of research, all of which Pierre has some great publications in. I have to say that also his contributions to CHCCS and the graphics interface community in Canada over the years have also been amazing. And he could well have received our service award as well, but we thought in many ways we'll honor his research at this time. So it gives me a great pleasure to welcome Professor Pierre Poulin from the University of Montreal. Oh, by the way, he's also chair. How does he do all this and be chair? Pierre, over to you.
Thank you, Brian. That's a really nice introduction, and I think that's a nice way of getting into my presentation at the same time. So just in case what I will be describing makes you feel like I have some mileage or some values to it. You can see behind, if you're lucky, you'll find some the ways we used to print to do our presentation, or write with pencil by hand, or do 35 millimeters, all the various types of submission of animations that we had to do on Betacam, VHS, and Video 8. So that should bring in some respect that usually I don't get much from the undergrad when I show them that, and they say, what's that? So anyway, let me start my own presentation. So it's a great honor. I mean, I'm extremely proud of the Canadian presence and the Canadian contributions in computer graphics. And if you look on the list that I put there, it's the previous award winner in computer graphics, and some of them are among my mentors and my idols. So being part of that list, or coming to be part of that list, is such an honor that I'm really humbled to be there. And honestly, this is kind of a shock, but great pleasure. And this comes not alone. I mean, definitely all this award belongs not to me, but to my graduate students, my numerous collaborators, and my mentors over the years. So that's definitely something that they should be proud of, being contributing. And if you look at the third person who've been on that list, the first, Alain Fournier was my supervisor, and I remember being there in 1994, and it was really kind of emotional to give his speech of achievement, and for me to get the chance of receiving this one this year is kind of extremely special. Alain was very curious, creative, and intuitive, and all of that. He sort of fostered the idea of reading, analyzing those papers, debating. Alain spent hours debating on everything. And the idea of how do we improve. For him, every student basically had to develop his own project with his guidance. So he sort of forced us to look at problems, to see a solution, and to develop our own unique angle on those problems. And so he brought us to be mentors for new graduate students and prepare us to be professors. And he was extremely strong, extremely kind, and quite funny. So being his student, or being a collaborator, or just meeting him, meant it was instant friendship, and everybody appreciated him so much. So he's dearly missed. And I sort of carry on his way of supervising students, and even when I went for a short postdoc in Princeton at that time with Pat and Ran, I had exactly the same kind of feeling of one graduate student, one project. And this is definitely, I mean, after so many years of being a prof, this is not the efficient way of supervising students. But it is definitely one of those ways of creating something new, to learn every day on something different. And so this is what I've been following for all those years. So usually when I meet a graduate student, we discuss about what is the goals of that he wants to have, what are the interests, the strength, the limitation, and then we run into proposition and investigations to find solution. I always say it is your degree, but it is our thesis. We're going to work together, and you're going to work with other students, and this is really important to us. So almost to the day, 1st of June 1994, I started as a prof at the University of Montreal. So that's 27 years ago. When I arrived, the Talman, Daniel and Nadia, who are also part of the list of the awardee for the achievement, had left already for 6 years. And 6 years in computer time means, nothing was really much usable for the graphics lab. So I had secure a fund of $60,000 to start a new graphics lab. So it was really exciting. So within the first month, I burned $60,000 with 2 computers. Indigo Extreme, Indigo 2 Extreme, and NND. And I had a list of students waiting at my door saying, hey, I heard that you're doing computer graphics. I really would like to do research with you. So I was fortunate that Tarna Studios in those days wanted to participate into sort of making donations to the lab, and they gave us 3 Indigos that make us survive the flow of students coming in. And so for about six or 7 years, I was the only graphics guy at the University of Montreal, and in fact, probably mostly in Montreal. So the positive side is that I was able to get the culture, the lab culture that I've been sort of appreciating so much in Toronto, in Vancouver, and even in Princeton. I had to build up my own teaching philosophy, and so people had no choice. It was me or nobody. And I had first pick on all those great students who wanted to do graphics. So it was really, really exciting. On the more difficult part, I mean, already having feedback about projects, papers, or grant proposal was not as trivial to do with email in those days. So I felt quite a bit isolated, but I sort of got around it and worked on it. So globally, I'm looking at my career, and I almost supervise about 100 graduate students. So we're talking about fewer PhD students. At the beginning, it took me a while to accept PhD student because it's an endeavor, and more master student, research master student. I also had a whole bunch of master 2 students from France being sent by their supervisor saying, well, you know, he's the greatest, best that we get. Can you train him a little bit so we can recover them to do a PhD later on? I had a few postdocs and visiting professors, but those are usually, I really work directly with all my students, and naturally to feed up the pipeline, I had to do a lot of internships, summer project with students, and that was very exciting. To pay for all those students would be almost impossible with what I had. I have a NSERC discovery since the beginning. I have a normal NSERC discovery, but I was so lucky that most of my graduate students were top students. So they had already fellowships. So they didn't have to go and find as much money as necessary. Still, I got some strategic CRD and various kind of funds. When the number of students started to grow and I could not handle the financial burden, grant appear. And so thank you to Kelly and all that kind of influx of topics and money. That was a great timing for me. So what's my career so far on publications? We have one book with Andrew, one of my best friend and best colleague, such a hard worker, and about 90 papers so far. I say journal and conference, but we all know that how conference became journal, that are really conference, but are journal. So, and as Brian mentioned, definitely service in computer graphics has always been dominant and really important. So we've been involved in so many conferences, organizations, journals. I did get the, let me see, yes, there. That's the Service Award in 2019. So I have the privilege now with Kelly Booth to be the only one to have 2 of those plaques. So that shows me much respect. And CSCAN is also there, and Grand and all of that. So to show you how old I am, those are, I call them my free mugs from SIGGRAPH. So every time you review papers for SIGGRAPH, starting a certain year, you get a free mug. But you have to go to the conference and you have to find the room where the mug is. So that gets quite a bit difficult. So you can see a few holes that are still necessary to fill, but I feel guilty of getting a mug there that has not come with reviews for SIGGRAPH. Anyway, so looking at the trying to find what would be the main contribution that I had for this to deserve that award. I went to the Google Scholar and have an H-index of 31 with 3,800 citations, which is reasonable, but not stellar. I look at the first top papers that are cited on Google Scholar. And so I get the survey on shadow, I get SPH in animation, physical animation, anisotropic reflection, so rendering, and visualization for, so it's very diverse. And I think Brian was really right into that. I covered quite a broad range of topics. Since every student work on a given project, I cannot say also there is one system that we built up and that we made distributed to people. So what are those topics? So I took the titles of my papers and I put them into a word map. And you can see that some words come a little bit more often, like light, illumination, shadows, efficiency, interactive, but it's a little bit all over the map. So so I look at the papers and I try to categorize them. I can see that definitely I have about 50% of my contribution in as pure rendering would get. And then I get divided equally almost into modeling, animation, and visualization. About 10% of my papers have some flavor of interaction in it, so which fits very nicely with the CHCCS community. So what did I do to improve rendering? Structures, hierarchies. This is usually the three words that I give to my graduate students when they start to do graphics with me. Hierarchy, hierarchy, and hierarchy. Definitely one of the most difficult words to pronounce for Francophone, and even worse when Alain used to pronounce it. So, and we had pleasure just to put hierarchies in our titles just for that. Hierarchies for light sources, for objects, for rays, for occlusion factor. How to go fast? Sampling in the right direction. So how we get those rays in the proper direction. I love rays carrying light. So all the specular light, the concentration of caustics that go everywhere, shadows that come from inter-reflection, global illumination, efficient bidirectional path tracing, and also some of those odd situations, primitives like a rounded edge, generalization of trees, how we can render subdivision surfaces, and Brian will be so happy to know that yes, I did some metavols. So I deserve much credit for working on metavols. But from the beginning till even now, I'm really working and highly interested in the appearance of surfaces. So that's what I call my micro, meso, macro, where you go from a reflection model where you don't see any detail, but you see the behavior of how light is reflected off surface. So I started my master's degree on anisotropy, and it's one of my strongest contributions so far. But how do we measure reflectance? How do we compress it? How do we fit into reflection model? How do we develop those reflection models? Or even how we invert them to be able to sketch or paint or some highlights or color points. So that's something that I've been working on for years, and I'm still so interested in that. As you move closer to the surface, then details should be appearing, but those reflection models do not give detail. They are smooth, they are filtered out. So how do you reintroduce with some form of textured information that you can use to get those details to make them apparent? And one of the strong contributions with Jonathan Dupuis and Eric Heitz was the leader model, where we go from these fine detail, the reflection models, how do we integrate them together with a distribution of normals, with shadowing factors, with the appearance, the color, the mixing of everything that, to do some kind of smooth transition from the scales of the dinosaur up to at a given distance. And that's something that always been very thrilling for me. And obviously, as soon as you get into GPU, procedural texture, perception of those details and all that, how do we use them to make things look older or torn, broken, and all that? And it goes up to how we go from real geometry, I mean, real objects, and try to find nice ways of approximating the global appearance as you move further away from the objects. And so now I'm working on cities with all the lights and all the interreflection within that. I also started my career looking also into real images to produce objects for computer graphics, to make it more real and more interesting at the same point. So we work on interactive system with Racon and PoMove to create some details, fine details. We're able to extract geometry, textures, some shading parameters, global illumination. I say radiosity because that's old work. I had two students, Emeric Epstein and Martin Granger-Pichet. Actually, those are probably the only two who work on the same system. And so they work one on space carving, the other one on structured light. And the idea was basically to have a handheld camera going around an object and having a projector projecting some additional information onto that system. And so, I mean, even carrying mirrors that we can have different views from the projection and from the camera. So that was really, really captivating. And that led to the creation of one company, a startup. Well, now it's 17-year-old, so I don't call it startup anymore, but it's been very successful. So I've been part of it. And because I was part of it, I stopped doing research to just not have any apparent conflict of interest between my research and what the company was doing. But they did so many amazing stuff. Just to give you an idea, Singapore National Day, you can see that on that slide, it's in a huge stadium, and you have probably a few, say 150 huge box, and they are tracked and projected them to give some special effects. Franco Dragon has been designing and creating entire buildings in order to get one permanent show on location. So they used our system for tracking, projecting live video. Roger Waters from Pink Floyd in the old days has been using our systems to do live shows that are moving from day to day into different locations. So I'm extremely proud of those guys, what they did and how they did it. And that's probably, as I'm getting older, but maybe my first retirement plan, just to slow down space. So procedural modeling came when GRAND basically was created. That was my emphasis. How can we add details on surfaces? And that's really important. That was really important to me. And basically how we create waterfalls, painting world, learning distributions, so we can have some kind of a palette of objects that we can understand and create more easily. Luc Leblanc was working on a block system, very nice way of creating objects where we know we have surface parameterization just by putting blocks next to each other and getting details and subdivision surfaces and parameterization on the surface. He used them for procedural modeling of buildings, entire buildings, where we know what's inside, what outside. How do we remove things, how we switch it. And he created a language to do interior and exterior fitting between those models. So I'm very proud of that work. I work also in modeling. I mean, we had some presentation on how important are the distribution of internal volumes for simulation into objects. So we had the conformal techniques, dihedral angles, work on geometry images or spherical representation with hill peaks, where we have even a high genus reduction. We could simplify thanks to that. During the wave of points, we had multi-resolution, that hierarchy again coming back to be able to add details, change things on the surface, and create things. Philippe Baudouin was one of my best PhD students, also was so motivated and so animated. The idea of taking long sequences of motion capture so we can compress them, but also create, recognize different motion and being able to build graphs with variations in it, but also transition within them. We did facial animation of driving real animations from points on the surface. With Marie-Paul Kenny, we work on hair, where we can have basically a wisp of hair with physical detection, the size depending of the motion and all that. Work on fluids, SPH, probably Simon Clavet is one of those hyper active and motivating master student. This is the second most cited paper that we have, where he worked on SPH and all those particles and properties that you would get from that. So that brought up also hierarchical methods from two of my recent PhD students, how we can do up-res, going from a lower resolution simulation up to fine details with procedural splashes, with machine learning between those two simulations. How do we control those SPH? By creating waves, by capturing the motion of a given simulation to put it into a new simulation. And that was, to me, that's very exciting. Hierarchies again into software. So when we have package that has different elements and all of that. So with my friend and colleague in software engineering, Wari Sarawi, we've been sort of building cities and looking at different problems in software engineering as queries into what can we get information on easily to somebody in software design or software correction and things like that. So that's something that has been very exciting to me. So if I look at my same thing, same strategy, the last name of all my co-authors, and I distribute them onto that word map, you can see that a few names come. I mean, Sarawi in the middle for the visualization, but also some of the colleagues, Ostromukov and Matthias Paulin, and some of my students. But you can see that there is kind of a few papers for each of the students, and basically that's about it. So that's a lot of students, a lot of colleagues and collaborators, and that's what I found so exciting to do when I was during all that career. So Wari Sarawi in software engineering. At Ligum, I was very delighted to have, at least for the time that they stayed within UDM, Victor Stromukov, who's now in Lyon, Derek now is Zarai. So Victor, talking about points, it's super exciting and so much of a pure scientist. Derek with so many students, so many projects everywhere. Bernard Tomaszewski, an intuition about so many problems that are so hard to solve, and then you get the SIGGRAPH paper and you say, wow, that's really impressive. And Misha Best myself, my new recruit and so far best colleague, of course. So I'm using the platform to do some special advertisement. We have a position, at least two positions, one in computer graphics that's going to be coming up, and one in HCI. So, older students getting ready to graduate, young professors or young researcher interested to join a very active and fun group. Please tell them to look for University of Montreal. So my outdoor collaborators, Andrew and George Urtekis from the the master's level we did. Marie-Paul Kenny, Fabrice Nérem, Miki Yoshimiya, since my master's degree, sabbaticals where I visited a number of people. So exciting to work with them. Eric Paquet, one of my first PhD students, now still collaborating with. So looking at the time fly, I will not talk to you how old I am and how terrible the progress has been between when I started in '87 and what it is now, because everybody knows this is unbelievably fast. And also how things change in academia in the sense of how many papers and code that is available in a multi-author, multi-site papers that are now possible. But I'm not going to talk about that. What did not change is the quality of graphics in Canada for all those years. We're still so, I wouldn't say dominant because this is not the Canadian style, but we're still such strong contribution in international visibility for computer graphics. And if I look at the young colleagues and the young students presenting, this is really, really exciting to see where we're going. What did not change? How time flies. This presentation, and also I'm sure that Tamara will be looking forward to for me to give her some lead. So this award probably due to my entire career. I must be getting older because I have 2 of those, so that's probably a good indication that that I've been there for a long time. Not as much as Kelly, but definitely a long time. But I still have a few years. I'm still hoping to be in shape. So my immense gratitude goes to the CHCCS Award Committee, the entire community, the Graphics Interface Conference and the community coming, all the funding agencies, and top of all my students, collaborators, and mentors. I really appreciated all those years. I'm looking forward to the next 27 years. And if you have any questions, good luck. But feel free to stop me anytime, anywhere. I'll always be very happy to chat about graphics.
Yeah, thanks so much, Pierre, for the great talk. We have one question from Deborah. So she says, must the people interested in your position be French speaking?
That's a great question. They must be interested in learning French to be able to teach in French within, say, 2 to 3 years. However, if you look at Michel, you can give him the microphone. He's going to be able to speak to you in French after a 3rd year. So he's top-notch and very impressive to see how people get to learn French. But I mean, very often the English side of the graduate course, the environment, the students are very often Anglophone. And as you can see, this is a large office. If somebody wants to be recruited to do computer graphics, that's not the size of the office you're gonna get. This is my last Friday as a department chair, and I'm gonna kiss goodbye to that great office, but getting a little bit more time for myself and my students, definitely.
Thanks so much, Pierre, and congratulations on the award.
Thank you.
Ryan, please, the stage is yours.
Thank you. That was very clever of you, Pierre, to go just that little bit over to avoid all the hard questions.
You can ask them to Tamara. She's going to be able to handle them.
Next up is Dr. Tamara Munzner. Tamara is our other CHCCS SCDHM Achievement Award winner of this year. And she, like Pierre, in many ways, has an extremely diverse career in terms of her research interests. As I said before, she bridges the gap between HCI and the computer graphics communities. She's solidly in the visualization community, but I'm very interested in one aspect of her work where she turned a sphere inside out, meaning she's obviously a topologist as well. In fact, in the 1960s, when I was still very much a small child, I attended at the University of Oxford, brought there by my brother to listen to a mathematician talking about a sphere turning inside out. Well, it's gone a long way since those theoretical days, and she made a magnificent movie on that. She's also interested in the development, evaluation, and characterization of visualization systems, a pioneer of a design study methodology, which has been widely used in fields such as genomics, evolutionary biology, fisheries management, and a lot more. So I am totally impressed with Tamara's ability to cover a range of subjects. So she and Pierre have that in common, and it gives me great pleasure to ask Tamara Munzner to give us a talk after receiving this prestigious award.
Thank you so very much for that kind introduction, Brian. To check, can you hear me?
Yes.
Okay, excellent. So many thanks for the kind introduction, and thank you also for this award. The physical award actually came by snail mail from CHCCS. It's an honor, it's a delight. And I really want to thank all of the many amazing people I've collaborated with over the past 30 years, because like with Pierre, this is all about the people I've worked with. I have worked with many people from the Geometry Center, where I made that video about turning the sphere inside out that Brian mentioned, and did some other things as well. And of course, my PhD advisor, Pat Hanrahan at Stanford, a shared academic father of Pierre as well. And there were, of course, other grad students there that I worked with. There were people at the Systems Research Center, where I spent 2 years in between there and UBC. And certainly a really major part of my own thinking was shaped in the last 2 decades of work with the many people in my own research group at UBC, and many, many other external collaborators as well. And I've learned from all of you. So thanks to you all. I'll start by talking a bit about the past and then move on to the future. So I like to do a mix of research across 4 themes to get an interplay between angles of attack. And I started out with technique and algorithm development. But I also care a lot about problem-driven work in collaboration with real-world users. And for both of those, we have to evaluate if things actually worked. So controlled experiments in the lab, field studies of deployed systems, mixed methods work. And then some of my highest impact work has actually come from synthesizing what I've learned from all 3 of these other themes into new guidelines and theoretical foundations. So I'll start by talking about 3 pieces of work that most resonated with the visualization community to reflect on why they struck such a chord. My nested model for visualization design and validation, it was originally written to scratch my own itch, but it's actually been cited over 800 times in the past dozen years. And the big challenge for me was how to think systematically about visualization, about evaluation. Not only how to do it myself, but how to teach other people about it. There are so many methods, and how do we decide when to pick which one? So I ended up coming up with an analysis framework that has 4 levels and 3 questions. And so at the top is the domain situation. So who are the target users? What's their background, their expertise? How do they think? What do they know about? Why are they even trying to look at their data? But we can't stop there. We have to move on to abstraction, because it could be that the people in physics and the people in finance are fundamentally doing the same thing, but using completely different language to talk about it. So how can we reason across fields? And that's why we have to get to translating from the specifics of domain language into a more domain agnostic, generic vocabulary of visualization. And I break that up into 2 things. What is being shown, the data abstraction, and why is the user looking at it, the task abstraction? Now, moving on from what and why to how, the how level is what I call the idiom level. Some people call this technique or method. And this question of how is it being shown, I also break up into two pieces. So the visual encoding idiom of how to draw things, and then the interaction idiom of how to manipulate things, how to manipulate that drawing interactively. Sometimes these are actually so entwined you can't separate them out, but sometimes there can be quite different areas of the design space. And then finally, I like to talk about the idiom to separate that from the algorithm level, which is, of course, how do you actually instantiate this efficiently in a computational context? So why did we bother with these 4 levels? It's because there's different threats to validity at each of these levels. So how can we mess this up? Well, a thing we could get wrong at the domain level is we could misunderstand what the user needs. Maybe you didn't even talk to them. Maybe you talked to them and that was necessary but not sufficient, because what they say they do and what they do, as we know, can be pretty divergent. How else can we get things wrong? Well, at the abstraction level, we might show them the wrong thing. So what does that mean? Well, if you're lucky, the really easy, simple case is they hand you the data and you draw that picture. But what's much more common is that you have to transform the data, guided by your understanding of their task, so that the transformed data becomes a thing, if you draw that picture, that it will actually help. If you get that part wrong, then the best visual encoding in the world can't solve the problem and actually help them. What about at the idiom level? Well, the way you show it might not work. It turns out, the eye is not a camera, the mind is not a hard drive, all kinds of very specific details about how the human perceptual work really matter for getting the idiom level right. How else could we mess up? At the algorithm level, your code could be far too slow. It might not scale to what you need to do. So what's the answer then? It's to use methods from different fields at each of these levels. And so here's a bunch of methods, but now we can actually think about them. Let's start in the middle, at the algorithm level. Now, this is well taught in computer science departments. Measuring system time and memory through computational benchmarks is sort of the bread and butter of computer science, or for the more theoretically inclined, analyzing computational complexity. And this is what I'm going to call technique-driven work. And it's crucial and it's interesting, depending on how you think about it. It's really where the field started, but it's not where we've ended. There's more to do. And so what about that idiom level? Well, before we build anything, we should really use methods out of the field of design to help us think, especially the ideation of multiple explicit alternatives instead of latching on to the very first thing we think of. Now, after we build something, how can we figure out if it worked? Well, we could use methods from cognitive psychology that come to us often by way of HCI, that then would help us with this question of running controlled experiments in a laboratory setting where we're measuring human time and error. But we're still not done. To actually deal with the abstraction level, that's where we have to steal methods out of the social sciences, out of anthropology and ethnography, and these questions about how to understand what people need through a combination of observation and interviewing and that sort of thing. And then in the end, to take a working system and deploy it in the field and watch how that changes the way that they work. That's a crucial idea. Again, out of looking at things in the field rather than in a controlled setting. So I'm going to call stuff that starts at the domain level and goes through domain, abstraction, idiom, algorithm. That kind of work is problem-driven work. Now, one thing that this paper was able to do was to really help avoid mismatches, because one thing I saw a lot of when I was reviewing papers that was really frustrating was people making a claim at one level and then validating at the wrong level for that claim. So if you're going to convince me that your new idiom is great, then telling me how fast your algorithm runs won't convince me of that claim. And a slightly more subtle one is if you want to convince me you got the abstraction right, that's very hard to do in a controlled experiment in a lab where you, the experimenter, tell the human what to do. In contrast, if you actually deploy things in the field and have realistic use, you might have a hope of understanding if you got your abstractions right. Now, this question of how to do problem-driven work led to another paper of mine that's had a lot of impact, and this was joint work with 2 former postdocs. Now, we often call papers on problem-driven work design studies in the visualization community. That's actually a name I came up with back in 2003 when I was papers chair for InfoVis and rewrote the call for participation. And at the time, both authors and reviewers were ultra focused on technique-driven work. And I wanted to encourage work on a much broader set of concerns: evaluation and system architecture and theoretical foundations, and this kind of problem-driven work. So the three of us reflected on this challenge of how to actually do it. And the part of the title, it was in the trenches, is that we'd actually done 20 of these papers between the three of us over about 10 plus years. And I personally started with a very technique-driven mentality where it was all about developing cool new algorithms. And that's not surprising because I came out of the computer graphics world. You know, I went to SIGGRAPH for 15 years in a row and I loved it. But even in the middle of that era, I'd also already started going down this other path of a different kind of work during my PhD with the constellations and the cadence papers. And I didn't even have a name for it yet. And I was really figuring it out as I went along. So in this paper, we came up with some key definitions, and we proposed a process model in the form of a 9-stage framework of how to do this sort of work. And maybe the most useful is we articulated these 32 pitfalls and gave a bunch of advice about how to avoid them. We ourselves had fallen into them, or papers that we had reviewed had fallen into them. And we also compared to other methodologies, particularly from HCI, about why is visualization not just identical from HCI? Where are the differences, and how can we get transfer of ideas, and where do we have to innovate? So I'm not going to go through all that today, but I will give you a teaser with the very last pitfall: premature publication. You might think, why is that something to avoid? And we introduced the metaphor that technique-driven work is like a horse race, and the threat is that other researchers are working on exactly the same problem, and they overtake you, and they publish first, and you lose. But in problem-driven work, it's highly unlikely that someone is working on precisely the same thing you are. A lot of the contribution comes from iterative refinement, getting the task and the data abstractions just right, and tuning the visual encoding and the interaction idioms until you've totally nailed it. And so your instinct here should be more like preparing for a musical debut. The big threat is you stepping on your own toes if you give a first concert before you've practiced enough. And so this paper also really caught on. It had over 600 citations in under 10 years. And most of these are from people actually following these guidelines. And then finally, the most ambitious synthesis that I've done was writing my book on visualization analysis and design. And I also wrote this one to scratch my own itch, to figure out how to convince people that visualization really can be thought about in a systematic way, in a unified way, and it's not just a grab bag of ad hoc techniques. And it was certainly a personal challenge to get that out the door for me. It would have been worth the 6 years of work just to help me clarify my own thinking. But seeing it catch on with such a broad set of people, both as an adopted textbook in classrooms and as a guide for practitioners, it's just this whole extra layer of wonderful. So I'm now going to transition from talking about the past to moving on to the future. I've been talking a lot about my own past work, but what about the field? And I would say that there's really been a grand victory, which has been the explosive growth of visualization. In the early 90s, it was really quite small in a very academic community. And by now, the main conference, IEEE Viz, well, it has well over 1,000 people attending each year. I've been very heavily involved with service at Viz. I started as volunteer webmaster, and then started the posters program, and then papers chair, and then steering committee, and then chairing the executive committee of Viz. And finally, the revised committee to sort of integrate our various conferences back into a unified whole. There's also a huge practitioner community by now. Like the Data Visualization Society just started 2 years ago, and now it's got over 18,000 members worldwide. There's industry success stories like Tableau from Pat Hanrahan. It's now a multi-billion-dollar company with over 110,000 people at its own user conference. There's open source software like D3 that has driven visual data journalism and interactive visualization in the browser into widespread use. So Viz has gotten much, much bigger, which is amazing and wonderful. So what's left? What are the future challenges? Now, when you think about grand challenges, I often think moonshots, but long-term efforts for lots of people towards a single huge goal. Okay, so going to the moon and building the nuclear bomb and eliminating polio. Closer to home for the graphics folks in the audience, there was the dream of a feature-length, completely computer-generated film. That started in the late 70s at NYIT, and it didn't come to fruition until like the mid-90s with Toy Story from Pixar. So what's left to do in visualization, or what's left to do in the world? Well, there's a lot of big things left. Cure cancer, reverse climate change, lots to do. Where does visualization fit into this? Now, it's of course not sufficient to get these things done, but I would argue it sure will be helpful. And so a different metaphor comes to mind. I think of a moonshot as a city, whereas an enabling technology like visualization is a road. And the thing is that visualization, it's like road building. It facilitates journeys to any destination. It's not just to a single one. And it's sort of even hard to argue that a particular kind of road building will only get you to one place. It'll get you to a lot of places. I mean, in that, I sort of think of it like statistics, which also is a field that's sort of serving externally defined goals rather than necessarily having its own moonshots that are understandable to the outside world. So I think we're going to help a lot with the moonshots of others. Having said that, I still think there are challenges in visualization. And so, it's maybe useful to think about what they are. Now, coming back to this question of validation, I think we could do better. And in particular, I think we could do better with controlled experiments. And so, for those of you who've been following the replication crisis all across the sciences with anyone that does any sort of experimental methods at all, you'll have been, hearing these rumblings about, well, which of our previous results are even reproducible? And, there's a lot of things that are now considered questionable research practices that, 10 or 15 years ago were absolutely normal and pervasive, and everyone was doing them. And so we're in the middle of this sea change. I would argue that the reason we don't hear a lot about problems with replication and visualization because we don't even try to replicate yet. And I think that's not just about visualization. I think it's also an issue in HCI more broadly as well. I think as soon as we try to replicate, we are going to be smack up against this same wall where we're going to discover there was, in fact, not maliciously, but a great deal of p-hacking. I think that techniques like pre-registration are going to help a lot, maybe even registered reports, which I don't think we have any of in our field. I really like the phrasing of Samin Vazir, which is, it's about the credibility revolution, which we'll have when we get to the other side of this phase change. And so I think we could really do better. There's a paper that recently came out after being a preprint for a few years now, putting the self in self-correction, findings from the Loss of Confidence Project. This is a group of psychologists who actually repudiated their own past work with a detailed statement of what they thought the methodological flaws were. I think it would be actually useful and amazing to do something like this in any combination of Viz or HCI. It would take a culture change. It's not something one sort of does solo, but I think it would help us get to a better place faster. So I tend to think of everything these days in terms of the nested model. So I've ended up thinking about a lot of the other internal challenges in terms of things at each one of those levels. Validation's about the whole thing, really. What about going from domain to abstractions? What I think we could be much faster about is closing that loop. So there's sort of an instructive story from one of my own past papers. There was a project called Overview that was aimed at investigative journalists. And the big question is, did we get the task abstraction right? So, we built a research prototype. Luckily, they actually had enough funding from the Knight Foundation. They were able to go off, build the system, deploy it, and have this robust thing that was actually in use by practicing journalists. And it was great. It was used by some people along the way towards a Pulitzer Prize. So that was all very amazing for a finalist on that. But then what we did is we went back and we studied it and we said, how did their task abstractions, did they line up to what we thought they would be? And the answer, of course, was no, not at all. It was quite different. And so, how do you go from just deployment to adoption? Did you get those abstractions right? That took years and years to actually get from the start to the finish of even beginning to investigate that. How can we speed that up? I think there's a lot left to do there. What about at the idiom level? Well, the good thing is there's actually been a lot of work on how to do faster rapid prototyping, but it's all been for a visual encoding within one single view. So that's something we're able to do much more quickly than we used to. But what's still really hard and time consuming and doesn't have good tool support is how do we do these complicated multi-view workflows, which are actually the norm in real systems, in real use. So again, here's another place where we hit up against this challenge in our own past work. There was a paper on matches, mismatches, and methods for analyzing energy use in buildings. And we had really a whole first phase where we did a lot of innovation and figured out what visual encodings were the right thing and so on. And then we had good tool support for that. And then the second phase of figuring out like how to fit these views together and how to get people using them to actually get work done, that was something that was much more ad hoc and without a lot of tooling to support. So I would love to see more progress on that. And then at the algorithm level, well, when it comes back down to it, you always need bigger. No matter what you design for, they always load in bigger data sets than you had in mind. They always hit up against the limits of the tools. And so with this one, again, here's a place where we ran up against this with our own past work. With the QSNE system, which was dimensionality reduction, we were able to actually get better performance for much larger data sets. We could actually load in like over 1 million documents from PubMed because we exploited the characteristics of these very, very, very high dimensional sparse document spaces. And that was a way we could get around some of the computational limits of earlier work where we were using things like GPU programming to actually do something that wasn't specific to the data sets. So I think that this will continue to be a theme. Pretty much as long as there's visualization, there will be algorithmic challenges with scaling up. And so I end where I started with this sort of algorithm level questions when I was originally working from a graphics point of view, even as I've also started wondering a lot about other HCI point of view things. So I'd like to thank people for listening. These talk slides are online if people are interested, and there's all kinds of other stuff on the page of my group and me myself. And I'd really like to thank you because having this award means so much to me. It feels like I was now embraced by Canada. I've been here for almost 20 years now, and I really, really appreciate it. Thank you so much.
Thank you so much, Tamara, for the great talk. Congratulations on your award. It's very well deserved. So is there any question from the audience on YouTube or the people that we have on Zoom? Sure, Ryan, go ahead. Yeah.
Tamara, I'm totally guilty of not following visualization very well. Too emboldened in my own, engrossed in my own sort of implicit modeling world, and I don't look out of it very much. As you probably know, I published a novel recently and have been really interested in, actually I've been writing some software for visualizing stories. And it occurred to me that the visualization of more abstract things like human emotions, stuff which you don't really have a proper metric for. I wondered how that is doing in the visualization world at this stage.
That's an interesting question. So there is actually some nice work on visualizing storylines. For those of you, I don't know if you're familiar with that XKCD cartoon that actually has these sort of, storylines of how the various characters from the Lord of the Rings went around. People have actually built software to try to do some things like that in a more automated way. There's one nice paper from Kwan Liu Ma's group out of Davis on that. And there also just last week was a couple of papers on, was it last week? Yes, it was last week. It was at CHI on visualizing, different parts about narrative visualizations and storylines, and they came up with a cool design space. I think these were out of Nan Cao's group at Tongji University, but they had two really interesting papers on sort of the interplay between narrative goals and like visual encoding approaches, and also one on visualizing on the sort of different narrative structures. Like, do you start at the beginning and go forward chronologically, or do you have a flashback and then go forward, but then go back again? So there was some cool work on that. So, I mean, in general, in visualization, people have thought a lot about these two purposes, which sometimes are similar and sometimes diverge, about exploration and presentation. And so they talk a lot about, using data for storytelling, but sometimes even the question of, how do you actually do storytelling with data? That's something that comes up a lot. My own group, I haven't done so much personally. I've gotten a little bit doing with some narrative stuff, with stuff about a design space for timelines for narrative intent, but a lot of that work has been done by other folks. But it's certainly sort of a hotbed of research. Also, I need to read your new book. That's great.
Thank you.
Okay, thanks so much, Tamara. So again, we're going to give you applause, and you have received lots of applause actually on YouTube. I'm going to give the floor to again. Thank you so much.
Thank you.
Give the floor to Manolis, and he's going to probably wrap up the conference. Thanks.
Thank you, Ali. Thank you, Brian, and congratulations to Pierre and Tamara. So I will have a very brief set of closing remarks to conclude this session, and then we will roll into the annual general meeting. So here we go. And bear with me for a moment while I adjust this. All right, so on behalf of the Graphics Interface 2021 chairs, I would like to close out GI 2021. A big thank you to everyone. Many thanks also for bearing with us through the technical hiccups that we experience in our virtual platform on occasion. Here I wanted to give some very quick statistics for how the two-day virtual conference ride went. We had 34 papers that were presented in 6 sessions and 14 talks, keynotes, invited speakers, and award talks. There were 372 registered attendees and a number, actually a larger number of viewers on YouTube for both days. Unfortunately, it's not easy to get unique viewers from the YouTube statistics, but here we have some numbers which are indicative of the viewership, and also a little plot throughout the day of the number of viewers viewing the streams. So thank you all for engaging with GI 2021 in this virtual mode. I hope it was a good experience. Here, I would also like to make the traditional announcement for next year's Graphics Interface 2022, program chaired by Sheldon Andrews and Deborah Fels, hopefully physically in Montreal next year. And I believe Sheldon and Deborah are here with us, so they can say a couple of quick words.
Hi, yeah, thank you, Manolis. So yes, the plan is indeed to hold GI 2022 in Montreal, Quebec next year, assuming that that's going to be something we can return to, conferences in person. And so the plan right now is to get back to a conference in person where we can engage each other, network, and really reinforce those aspects of conferences that I think we've all been missing over this past year. That's all I have to say. And then stick around for the AGM, because we have lots of points and topics that we want to discuss about preparing for the conference next year.
Great, thanks, Sheldon. And yeah, that was exactly a good segue into the last slide. I would like everybody to send a round of applause, virtual applause, for all the GI 2021 participants. It's been great to meet virtually. And everybody, please do join the CHCCS SCDH annual general meeting, which is immediately after this, in a separate Zoom meeting. You should have received the link through the Eventbrite system. It went out to all the registered attendees. So thank you all once again, and hoping to see everybody physically in the next year and in coming years.
Thanks, bye-bye.